Hello, everybody. Welcome. So it's my great pleasure and honor to welcome you here to the 8th edition of the International Workshop on Material Physics. The workshop is held in a historical building. The flourishing period of the current Ote Teleșanu domain begin in period of 1831 when, according to the legends, the estate of Cristache Vrana came into possession of Ioan Ote Teleșanu following a game of cards. Ote Teleșanu Castle, so this building, was built between 1834-1843. More details on the topic are available for curious eyes in the abstract book. Also, Christina, our workshop secretary, will be waiting for you. She is here, eager to give you a brief tour of the castle, maybe during the lunchtime. The purpose of this workshop is to act as an exchange platform where we can share new ideas and discuss the most recent developments in advanced materials. By creating this environment, we hope to entice prominent researchers into playing along and thus establishing partnerships and collaboration, which will result in joint publication, novel initiatives, and also personal exchange. With us aim to share the latest scientific results related to advanced materials and characterization techniques with an emphasis on heterogeneous catalysis. I hereby welcome our representative delegates from 12 countries spread out across 3 continents. As an overview, we are pleased to provide 19 invited lecture and 11 oral presentations that will certainly care for interesting conversation starters. We have the utmost confidence that you will find the content informative and you will be able to openly express your opinion among other like-minded talented researchers. For any other information regarding the workshop and our institute, my colleagues and I will gladly be of assistance. I strongly encourage all the participants to actively engage in your activities and in the coming days share their own experiences and lessons and be vocal and exercise your researcher skill. In the end, I would like to give the huge shout out to the organizing committee and especially to my lovely colleagues, Florentina, Julia, Anca, Cristina and Stefan for dedication and the work they put into organizing this workshop. Also, I would like to thank to my colleagues from the IT department, to Victor, Ciprian and Cosmin for helping us with this workshop. Through this channel, I extend my biggest thank yous to you. On behalf of the Institute, I wish you all a warm welcome to Bucharest, and may you enjoy this event as much as we did planning it. And as always, stay curious. I will like now to give the word to our General Director, Dr. Ionuț Enculescu.
Thank you very much. I would like to thank all of you for coming here and sharing your research, sharing your ideas, and maybe sharing your plans to the future. I really hope that this will be a fruitful event, and I really hope that this will be a starting point for excellent collaborations in the future. I don't want to keep you more, so thanks a lot for being here, and have a fruitful workshop.
I would like now to invite our first speaker, Javier Garcia Martinez, which is a professor of inorganic chemistry and director of the Molecular Nanotechnology Laboratory of the University of Alicante, where he leads an international team working on the synthesis and application of nanostructured materials for the production of chemicals and energy. Javier is the current president of the International Union of Pure and Applied Chemistry, IUPAC, and previously he served as a member of the executive committee and as a vice president of the division of inorganic chemistry. Professor Garcia Martinez has been awarded with a lot of prizes. Among that I can mention the King James First Award in his category of new technologies, and in 2015 received the Emerging Researcher Award from the American Chemical Society. In the summer of 2017, he was recognized by the American Chemical Society with the Catherine C. H. Award as the best U.S. entrepreneur in the chemical sector. Javier is a member of the Council of Emerging Technologies and Young Global Leader of the World Economic Forum of the Global Young Academy and Fellow of the Royal Society of Chemistry. Javier, please, the floor is yours.
The presentation. Okay, good. So thank you very much for the very kind introduction. It is a real pleasure to be with all of you here. Also, on behalf of IUPAC, I want to acknowledge the organization of a very timely Congress on a very important topic, and I'm pleased to see so many colleagues, not only chemists, but also physicists, together trying to make sense of material science, just beyond material physics or chemistry. Let me tell you a little bit of what we are, let me see how we can move this without, I don't think this is actually advancing. The first one is always the one that deals with all the technical glitches. So if you just let me know how to do it, it will be great. So basically, what we do in our lab at the University of Alicante is to modify the structure of porous materials. And today I'm going to be focusing on a new generation of zeolites, but also on the deep characterization of this material, which is not easy. They are very heterogeneous materials, and the characterization of these complex solids is very challenging. So, porous materials. We pretty much can do whatever we want. When I was a student, these things here seemed to be a dream. Now we can make chiral mesoporous zeolites with mesoporosity, but at the same time chiral zeolites with its own chirality in the structure. And of course, zeolites are not anymore just microporous solids. We also have mesoporous zeolites. And here I do want to recognize, some of you will recognize that already in the name of the zeolite ITQ, the contribution of Abelino Corma, who has been developing many of these new structures. But one realization is, from my side, is not sufficient to create new zeolite structures, because that's not how nature operates. It's not so much about the crystalline structure of the materials, but also about their morphology. And that's how nature is able to fine-tune the properties of many, many different materials, either they being silica or calcium carbonate. Now, of course, we have more than 250 zeolite structures, but also we have new morphologies that have a much greater impact than the crystalline structure in the catalytic properties. We can make, of course, nano-sized zeolites, very high quality these days, as the ones you can see there from the group of Svetlana Vintova in France. Those self-pillar zeolites, we published that a few years ago, again with a very interesting morphology, and of course now we can make also single unit nanosheets of zeolites, like bidimensional zeolites. So pretty much everything we want. And one of the reasons for controlling the morphology of zeolites is to control the Thiedel models, how much of the catalyst is being used. If you use very big crystals like these 17 microns MFI zeolite, you are making a very bad use of your zeolites, and you are going to be under diffusional control. As the diffusional path length of the zeolite gets smaller and smaller, you fully utilize your zeolite and you're making a much better use of your catalyst. But as I said to my students, catalysis is not about conversion, it's not about using your catalyst, it's about selectivity. And from this very nice review paper I highly recommend you, we can see some of the benefits of reducing the diffusion path length in zeolites. For example, we can significantly extend the lifetime of the catalyst by reducing the diffusion path length. That's one of the main benefits, but we will see also how controlling the morphology of the zeolite also allow you to improve their selectivity. In the last few years, many groups, of course also ourselves, have been developing new strategies to improve the diffusional properties of zeolites. Zeolites being microporous materials, they experience a lot of diffusional problems or limitations. So you can indeed now introduce mesoporosity in zeolites. I will be talking about that. We can also make nanosheets, or we can desilicate zeolites, or make nano-sized zeolites. So we can make many new zeolite morphologies, and the characterization of these solids is very challenging. Sometimes they are very heterogeneous solids, and it's not easy to understand things like acidity, for example, or defects in these materials. A few years ago, I developed a new strategy to introduce control intracrystalline mesoporosity in zeolites, almost making true the dream of making aluminum NCM41 crystalline, to use surfactants to produce crystalline mesoporous materials. The treatment is very simple. We just treat the zeolites in a mild basic solution with cationic surfactants, and what we postulated that it happened is that the attack of the base to the zeolite structure creates a negatively charged species which cause the attraction of these cationic surfactant. They need to have very small heads, they need to be cationic, and then when the local concentration of those surfactant is high enough, and if you provide enough activation energy, then you form micelles inside the zeolite, which is something very surprising because the micelles are very big. But that's very clear if you look at that through microscopy, because your material looks much more open after this treatment. And of course, in the isotherm, you go from a type 1 isotherm to a type 1 full isotherm. So the presence of mesoporosity is indeed very clear. Observing the formation of these micelles was very challenging, and in order to do so, we use a Raman spectroscopy to identify, one, the increase of the concentration of the organic, in this case the surfactant, inside the zeolite, but also the formation of the micelle by following the reduction of the polarity of the environment that we follow with time, as you can see here, and also at different depths of the zeolite crystal. So by using this Raman microscopy, we were able to directly observe the formation of micelles in one single crystal. So this is a very strong evidence of the possibility of crystal to rearrange to accommodate mesoporosity in their interior. Of course, we follow this transformation also by other more conventional techniques like in situ synchrotron X-ray radiation. This is our setup, very simple. This is a capillary when we have the zeolites, the surfactant, and the base, and we monitor what's happening with the zeolite as time goes. At the beginning, we have just a typical zeolite. This is the fingerprint of the fungicide structure, and as time evolves, there is the formation of this low-angle peak, which is related to the formation of controlled mesoporosity. Two control experiments. If you add no surfactant, the base destroys the zeolite, and it's very clear by the disappearance of the XRT peaks. But if you add no base, the surfactant is incapable of introducing the mesoporosity. So you need both. Of course, we follow that also very carefully by gas absorption. In this case, this is argon at 87 K. And this experiment, it was very important to show that indeed we were doing surfactant templating. In other words, if we use very short surfactants, like surfactant with 10 carbon atoms, then the mesopores are very narrow. And as we increase the length of the surfactant, the micelles get wider and the mesopores also get wider. That's very clear from the pore size distribution. The microporosity is maintained, but also as we introduce or we use larger surfactants, the second peak, the peak due to the mesoporosity of this material, increases. And actually there is a very linear trend between the mesopore width and the number of carbon atoms from the surfactant. So it's a very clear indication that this is templating. The big micelles produce big mesopores, small micelles produce small mesopores, and we can do that with sub-nanometric precision. So we can control both the size and the amount of mesoporosity very precisely. But of course, we had to prove that this mesoporosity is inside the crystal, because all the attempts in the past to introduce mesoporosity in zeolites by surfactant templating failed to introduce the mesoporosity inside the crystal. So what we did is to ultramicrotome a suspension of these zeolites in a resin, as they do in biology. So we were cutting very thin layers of these mesoporous crystals, and I don't know if you can see here, the resolution is not very good, but here you can see the crystal lattice of the zeolite, and also all those pale holes are the mesopores. That's the best we were able to do in Alicante, in my lab. Because we wanted to show this even better, we collaborated with Professor Shandong Xu at Stockholm University to combine rotational electron diffraction with electron tomography to investigate both the locations of the mesopores and also how that affects to the crystallinity of this one single crystal. Using this data, Professor Shandong Xu and her collaborators were able to reconstruct one single crystal of this zeolite with the mesopores that now very clearly you can see they are inside the particle. There is very little doubt that that architecture is inside the particle. And now if we reconstruct a small part of that crystal, we can have a better idea of how interconnected those mesopores are, which is very important for the catalytic applications. But because we have the electron diffraction of this particular single crystal, we can superimpose the crystalline structure of this zeolite and traveling through these molecular highways and seeing both the microporosity of these crystals, like this channel here, but also these mesopores that surfactant have created. And this is a very solid piece of evidence that shows that indeed the mesoporosity is inside the crystals. We of course follow that also by gas absorption as treatment goes. This is the parent zeolite, as you see, has actually a lot of microporosity and some large mesoporosity due to the steaming of the zeolite. This is a US white. This is an ultra-stabilized white zeolite. At the intermediate stage, you see the formation of some mesoporosity, and finally, this is the type 1, type 4 isotherm that I was mentioning before with the presence of mesoporosity is very clear. That is ex situ. We wanted to see this with our own eyes as it was happening. And of course, now we can do that either by TM at different times. We were collecting the samples at different times. These are the crystals as we get them. These are the thin layers, the slices that I was mentioning before. At short times, you see these big channels due to the steaming of the zeolite, and you can observe how the crystal rearrange to go from big channels to those very small, very controlled mesopores. But again, that is ex situ. Now we have techniques like liquid TM that will allow us, if possible, to see this process as is happening. We did that at Brookhaven National Lab when I told them I want to see this process, and I took my TM micrographs there to see if that was possible. They told me, no way. You have a lot of water here in this cell and there is a lot of scattering. So the formation of these tiny 5 nanometer mesopores is just not possible. But I wanted to achieve two goals. First, to observe one single crystal, to see if it dissolved or it rearranges. If it doesn't dissolve, but it stays there. And also, I would like to see how those big channels disappear with time. And this is the movie that we obtained there. It's only 9 seconds. Actually, it lasts almost an hour. It has been accelerated. But you can see here is one single crystal. So it doesn't fully dissolve during the process. But those big channels that I mentioned before, you see, they disappear. Of course, you will see a lot of noise there because it is a very, let's say, boring movie for over an hour, and this is only a few seconds. But I hope you can see here the same thing we observed by XC2TM, that the crystals don't dissolve, fully dissolved, and the preservation of the shape, but the disappearance of the big mesopores. And we were able to see that once again by liquid TM, the first example that liquid TM was used to investigate this kind of zeolite transformation. Again, we were very happy to confirm that the zeolite, one single crystal, doesn't dissolve during this process, and that the big channels go away during the surfactant templating process. You may wonder, are those channels needed for this process to occur? No. No, because we also use sodium Y that doesn't have any of those channels. These are very pristine, very nice crystalline zeolite with no mesoporosity. And again, we are able to introduce huge amounts of mesoporosity into this sodium Y zeolite. And this is the before and after that I told you before, from a really nice, what here I would like a dense crystal, to something that looks much more like a sponge. So there is a big change in the structure of the zeolite with this treatment. As St. Thomas, I want to see to believe, and here is not even seen but touching. So we used AFM to monitor the surface of the zeolite as the process goes on. Of course, we have to fix these crystals on the Petri dish, so they were glued to avoid any movement, and then we put the surfactant, the solution, we heat it up, and we followed that by AFM. And we saw there, let me see if the movie is here, is that at the beginning we have these big channels, like they are 10, 15 nanometers in size, and with time those big channels disappear to form the 5 nanometer mesopores I mentioned to you before. That is what I hope you can see here, those tiny holes that we were able to observe in situ in that movie, following the reconstruction of the surface with the tip of the AFM. And again, the size of the mesopore was exactly the same one we determined by gas absorption. We got a little bit bold here, and we were doing wet chemistry at the synchrotron. I guess the safety manager was not aware of what we were aiming to do here. We built this little setup with this little arm to allow for dumping the zeolite in this flask at the right temperature, so we can follow pH, temperature, and with this peristaltic pump to flow the slurry through this capillary to obtain X-ray data with time, and of course at different temperatures, because we were interested to obtain the apparent activation energy of this process. And this simple slide here summarizes 3 years of work. We determined the apparent activation energy of the formation of mesoporosity in Y zeolite by in situ X-ray diffraction, as I showed you a minute ago, but also by ex situ gas absorption. And in both cases, it was around 44 kilojoules per mole, which is exactly the same apparent activation energy which is required to crystallize Y zeolites. So the chemistry involved in introducing, chemistry, which means breaking and forming bonds, for this reconstruction is exactly the same that is required for the crystallization of this zeolite. So we were very, very pleased to see that. We also wanted to investigate the thermodynamics of this process, and we did that in collaboration with Alexandra Noborowski here to do drop solution calorimetry. And to make it very short, what I want to highlight here is that the thermodynamic penalty of introducing mesoporosity in zeolites, because yes, there is a penalty of introducing so much porosity into the zeolite, it's almost is only 3 kilojoules per mole, whereas the formation of the micelles is from 6 to 9 kilojoules per mole. So the driving force for the zeolite to reconstruct, to introduce this mesoporosity, is the formation of the micelles. That's really the driving force. And this is probably the slides that I'm more proud of, because this is not from my group. These are series of papers from different people that has been using our technique to introduce mesoporosity in all kinds of zeolites, in faugiasite, in mordenite, in beta, in ZSM5, in LTL zeolites. So now this technology works not only on faugiasite, but also in any of the most important zeolites. But does this work for catalysis? Yes, it does. And I'm going to highlight two very difficult examples that we are working on right now. And as you can see, we are targeting the conversion of very bulky molecules, because that's where the presence of mesoporosity in zeolites will allow us to replace very toxic homogeneous catalysts by zeolites. In the first example, we aim to produce this intermediate for the production of an antagonist for a glucagon receptor. And also in this aldol condensation, we aim to obtain this intermediate for the synthesis of this inhibitor for a leukemia cell. And these are the results. The activity of different catalysts, acid catalysts, were compared for the production of these two molecules that involve two acid catalyzed reactions. The original zeolite, the USY zeolite, commercial one, has very little activity because it's very acidic, but not mesoporous enough. Other highly mesoporous materials like aluminum NCM41 have plenty of mesoporosity, but the acidity is very weak. So it's only by combining the strong acidity and enhanced accessibility of our materials that you can convert these molecules and opening catalysis to very bulky molecules. Then we got much more ambitious and not only wanted to produce those intermediates for the pharmaceutical industry, but carry out very difficult reaction. This is a multi-component reaction that involves an Obenage condensation, a Michael addition, and intramolecular cyclation in one pot for the synthesis again of a biomolecule, and doing that under solvent-free conditions. So just imagine how difficult this is. We are replacing an homogeneous catalyst by a solid. We are using no solvent, and we want to do everything in one pot, all those reactions. And in addition to that, this reaction is not acid catalyzed. We want to use the zeolite as a base catalyst to make it even more difficult. And these are the results. I don't want to bother you with the characterization of the solids, but you see that the conversion significantly increases for the conversion of the production of this intermediate when we introduce mesoporosity. When we put all that mesoporosity, we can form these bulky molecules in the interior of these solids, even without solvents. That really opens the door to replace toxic homogeneous catalysts with these solids, with zeolites. And probably the most demanding of all these reactions, this is the cracking of hydrocarbons. This is a prop molecule, 1,3,5,3-isopropyl benzene. This is a very bulky molecule that doesn't fit into the zeolite. That's why the conversion is so poor. By the introduction of mesoporosity, we were able to significantly increase the conversion of the 3-isopropyl benzene, but more importantly, to double the selectivity towards the dealkylated product. And that's the key. The key, once again, is not about conversion, it's about selectivity. And by reducing the diffusion path length of this catalyst, we were able to extract the intermediates immediately and to prevent the overcracking reactions that deactivate the catalyst and produce undesired products. And the most recent work that I'm very excited to share with you here is about, again, a realization. I've been working on zeolites for all my academic life, and I've been always obsessed, like everybody else in the zeolitic community, with crystallinity. We wanted to make beautiful crystals. We want to go to the X-ray diffractometer and have very intense peaks. Now we enjoy the effects. We enjoy poorly crystalline materials because we are discovering that there is a new territory for designing better catalysts. So what we are doing now is to use old buildings, like what happened here in Bucharest, taking old buildings, say they're making with these rectangular bricks or these ones with these hexagonal tiles, and creating this hybrid, kind of like a Gaudi building made of bricks that don't fit very well. And we are doing that with a process called interzeolite transformation. Again, very well-known process in zeolite. You start with a very open structure, you put it under hydrothermal conditions, and then you can obtain all kinds of zeolites. And this is the magic of this process. You start with a zeolite like faugiasite that contains these composite building units, and then you can make many others like MFI that contains different building units. And the community still doesn't fully understand what's going on when you transform faugiasite into beta, because you don't have the same building units. So there is a moment when the building units of one zeolite are transformed into the building units of the other zeolite. And at that moment, there is a very rich chemistry. And that's the part that we are more interested in. So that's what we are doing. Again, we are taking a fully crystalline zeolite, and while it is being transformed into a new one, we are collecting the intermediates. So to do that, we just replicated a very well-known transformation from faugiasite to beta zeolite to collect these intermediates at the point that the units are being transformed. And we are doing also the same with surfactants to see if we can also control the mesoporosity of the intermediates. And that's exactly what we obtain. Look, if you just look at the evolution of the X-ray diffraction patterns, if you will be into the zeolite business, but pretty sure that all of you working with crystalline materials, at half a day, after 12 hours, you will not be very happy with that material. Probably you will throw it away, or you will be waiting for 2 days to get very crystalline solid. But when we analyze the intermediates, which are amorphous in terms of X-ray diffraction, we observe that they are highly mesoporous. And we were wondering about the acidity of this material. Do we still preserve the acidity of these materials? Because from the mesoporosity point of view, they are very interesting. And indeed, they are not only very acidic, but they also retain those building units. This is the Raman spectroscopy of those intermediates. We have the 6-member ring, the double 6-member ring from the faugiasite, already a very early times, or very early stages of the transformation, but also the 5-member ring of the MFI zeolite. So there is a moment when, yes, we can create these Frankenstein zeolites with units that don't coexist in any given zeolite. And this is what we are doing now in a very smart way with the use of these surfactants that also behave as structure-alterating agents. And again, I don't want to bother you with the detailed characterization, but we are interested in these ugly-looking X-ray diffraction materials, or diffraction pattern materials, with very nice mesoporosity, and either by Raman spectroscopy or NMR, we have been able to identify at what moment of this interconversion we have these Frankenstein solids. And just to finalize, this is my last slide. a big surprise, something that we couldn't expect. We tested these materials for 3 different catalytic reactions. One, very simple, is a Fidelcraft alkylation, again to the production of a very big molecule. Similarly, for a Claisen-Smith condensation for the production of these 2 bulky molecules, and then completely different but also acid catalyzed for the degradation, the catalytic degradation of polystyrene. And then we plotted the catalytic results as a function of the degree of crystallinity. So this was our proxy to indicate how much into that interconversion we are. And what we found is that for 3 very different reactions, the most active materials are the ones at only 15% conversion, when there is almost no crystallinity, but the building units are already there. We follow that by Raman spectroscopy. So these materials are organized at local scale, but they are not crystalline, they are not periodic. So that's why they don't diffract. In terms of catalytic performance, they are amazing, and they are very acidic. How do I know that? Because we also introduce aluminum MCM41, which have very high surface area, that is non-crystalline. This one is completely amorphous material, no Raman peaks, and that material again produce very low activity for any of these reactions. We were very surprised to see that again, same message from 3 different reactions. And just not so in terms of the science, but I want to tell you that this technology, we have scaled it up. This is the pilot plan we were discussing yesterday in Princeton. This is our spray dryer. This is our little pilot plan to produce this at kilogram scale. These are the data, the pilot plan data, the conversion of in this case, vacuum gas oil into gasoline. That, as you can see, you get significant increase in diesel, and more importantly, the reduction in coke formation. We partnered with Grace to produce this at very large scale. This is the Grace zeolite plant in Baltimore, in Maryland, in the US. And this is the first refinery where this zeolite has been tested. This is Alembic Spring in Texas. I'm pretty sure you have never seen data from a refinery, not because it's not your field of research, that I don't know, because refinery don't share data. So we were very happy that Alembic Spring allow us to share these results. This is the predicted selectivity for the unit and the actual numbers. Most importantly, probably the reduction in coke formation, but also the fact that we could produce more liquids and more olefins. If you are not impressed by the 2%, 10%, 3%, you can look at how much that means in terms of economic improvement. Just making these tiny holes in the zeolites, it goes from $20 to $50 million per unit, per refinery. Grace acquired this technology a few years ago, and now is being commercialized everywhere. So my final message, my conclusion is that these hierarchical zeolites are already a commercial reality. So they are not a lab curiosity, but something that is being used all around the world. So thank you very much for your questions, and I will be happy to take questions. For your time. Thank you. Okay, so again, the driving force is once you have the surfactant inside those channels, they self-assemble to produce micelles. And there is from 6 to 9 kilojoules per mole of driving force for that reconstruction. It's not so much that you are filling the channels with the small mesopores. This is more done at local scale. So you have the breaking of the silicon-oxygen silicon bonds, and then you create a negative charge, the cationic surfactant goes there and stabilize that position, and then the micelle is formed. Surfactant. Yeah. Yeah. So what we saw. Yes. Yeah. So, but what we were looking things through the liquid TM, the surfactant was still inside. So that reconstruction, the annealing of the channels happened because of the presence of the surfactant. When you provide enough kinetic energy, as we saw with this 40 kilojoule per moles, what you're really doing is allowing the movement of mass, if you want, breaking a creation of bonds at local scale that heals the structure. For example, the extra framework aluminum, which is a clear sign of defects in zeolite, it goes back into the zeolite structure, into the framework. So it's indeed, as you said, a healing process. And part of that healing process is the disappearance of these channels and the formation of the controlled mesoporosity. We saw that very clearly by Raman microscopy. It has been probably the strongest piece of evidence we have for that. That's an excellent question. We don't have a definitive answer, but we have seen some shape selectivity. So it seems like the molecule goes inside the channels a little bit. But there is a big controversy into the zeolite community of how much of the reaction happened on the external surface. And here we have a significant amount of the sites on the external surface and how that influenced the acidity. So I'm sure you are right that a significant fraction of the catalysis happen on the external surface, and that helps for the conversion, but we also see very significant increase in selectivity. So we think there is a little bit of catalysis also in the crystalline structure of the zeolite. Otherwise, aluminum NCM41 will give a similar conversion, and that's not what we see. So maybe it's a mixed bag. That's the best I can say. Yes. Okay, thank you.
So basically you've seen the recrystallization was besides making completely different styles. Many bonds are broken, many bonds are less sad. In terms of zeolite conversion, in the morph phase, they completely recrystallize. Interesting, you find not even halfway you found the highest. What about the zeolite synthesis by itself?
We are doing that right now. That's again a very good point. I didn't have time to go through the state of the art, but in the 2000, Professor Thomas Pinabaya was using nano-sized crystals and precipitating them with surfactants to do exactly that. And more recently, Valentin Balchev has been producing what he called embryonic zeolites, quenching the crystallization of zeolites at a very early stage, because at that point you already have enough acidity to catalyze these reactions and huge surface area, because when you have a big crystal, the Thiedel model I mentioned before, it goes down quite significantly, and then you have all the diffusional problems. So yes, that's what people has been doing. But I think it's unique about these Frankenstein zeolites is that you can put building units from zeolites that do not coexist in any given structure. About your first question, I don't call it recrystallization because in that incorporation of mesoporosity, there is no dissolution and there is no amorphization. And it's not a completely new structure, it's still faucesite, it's just a different architecture. It's the mesoporosity that we are embedding into the crystal. But yeah, language is important because it has created some confusion into the community. Good. Yeah.
the heart the body. Also suppress
Yes, we are doing a bleeding absorption now to characterize how much of Lewis acidity and Bronsted acidity we have. What we see is the more mesoporosity we introduce, it more goes to the Lewis kind of acidity, which is expected, but that kind of acidity is strong enough to catalyze this reaction, and thus we always introduce the control experiment with aluminum NCM41 that is not able to catalyze these reactions. So you both are absolutely right. Most of the reaction will happen on the external surface. The acidity of those sites are different because the aluminum probably is not tetracoordinated there. You will have a lot of synalol terminal groups. The acidity in the external surface of zeolite is a very controversial area in zeolites. We don't want to enter into that, but indeed it's able to catalyze the reactions, and you even don't need fully crystalline materials for that. This new class of Frankenstein zeolites, they don't even have X-ray crystallinity, they're able to catalyze these reactions. So as you said, we don't need to make so beautiful, so crystalline if we want to do catalysis. Okay, good. Thank you.
Thank you very much, Javier, for this nice presentation and discussion. So now I will introduce Professor Su. Professor Su, full professor in chemistry and the head of the Laboratoire de Chimie des Matériaux Inorganiques at the Namur University. He holds Chair Frankie of Materials, or Titre Belge, since 2012. Elected to the Royal Academy of Belgium on March 2011, Fellow of the Royal Society of Chemistry and life member of Clare Hall College, University of Cambridge, since 2012. Professor Su earned his doctorate from the University Pierre and Marie Curie, Paris, France, in 1992. After his postdoctoral stay in the University of Namur, his research stay at the Catalytica in California, he joined the faculty of Namur in September 1995, and now, as I said, is a full professor in chemistry. Professor Su has received a series of major awards, such as the Invention Award of Sinopec in 1992, the Adolphe Wetterms Prize of the Royal Academy of Belgium in 2007, and the IUPAC Distinguished Award for Novel Materials and their Synthesis in 2011. So, Professor Su, please, the floor is yours. Thank you.
Thank you very much, Michaela. So thank you for invitation. So this gives me the opportunity to come back to Romania since I think 15 years. So yeah, so before 15 years I visit very often Romania. Okay, so I will continue the story made by Javier. So I just modify a little bit the title because it is a catalysis workshop. So Javier gave already, in fact, how to introduce the mesoporosity. So here I just want to say how to introduce more porosities and what is the principal design for the for this kind of material. So I would like to thank my colleagues in Namur and also my colleague from Wuhan University of Technology. So I don't want to go further because Javier did a very good introduction to the zeolite. So zeolite, in fact, are applied in different areas, especially for the petroleum processing. So you can see each step we use, in fact, the zeolite. So we know, in fact, 40% solid catalyst at the moment in commercial market are made by zeolite. And we know in 2020, the zeolite market is evaluated around 26.8 billion. It is a big market. So in fact, the zeolite, so Javier introduced already, we have a lot of advantage. So however, we know, so he showed also the zeolite with the small pore, we have the problem of a diffusion limit. So this is in fact the great scientific challenge. That's why Javier would like to introduce the mesoporosity in the zeolite. And from another point of view, so he showed also, due to the diffusion limit, in fact, the efficiency of utilization of zeolite is very, very low. So in fact, due to the diffusion limit, the molecular, small or large, can penetrate, in fact, a very thin layer of zeolite crystal. So this is a big challenge. So because we cannot use totally, in fact, the zeolite crystal. So not only we cannot use with high efficiency, and due to the low efficiency of utilization, we have also low activity and also the low selectivity. And due to the diffusion limit, we have also the coke formation, resulting the very quick deactivation rate. So when we have, in fact, the coking, so we have to regenerate the zeolite catalyst. So this is time, raw material, and also energy consuming. So that's why how we can suppress the diffusion limitation, so we can, in fact, increase the activity and also the selectivity of zeolite catalyst, and we can also increase, in fact, the efficiency of utilization of zeolite. So how to, in fact, to reduce the diffusion limit? We can introduce, in fact, mesoporosity. This is one strategy. And another strategy, in fact, we introduced also since 90 of last century. So in fact, to reduce, in fact, the size of a zeolite crystal. So from micro-sized crystals to nano-sized crystal. So in this case, we can practically use completely the nano-sized zeolite crystal. However, so that's why, in fact, nano-sized zeolite crystal are not used in industry process at the moment. So why? Because when we have, in fact, the small crystals, we will lose the shape selectivity property. So diffusion limit, it is not good, but it is also good also for the selectivity, for the shape selectivity property. Due to the nano-sized crystal, we lost also the thermal and the hydrothermal stability. And finally, due to the small crystal size, it is very difficult to separate, in fact, nano-sized zeolite catalyst and also the product formed in the reaction system. So there are different drawbacks for the nano-sized crystals. So that's why nano-sized crystals are very good. However, it is not possible to use in the industry process at the moment. So how we can, in fact, resolve this kind of problem? So as I said, introduction of the mesoporosity is a one solution. So we go back, in fact, to the nature to see how to increase, in fact, how to resolve the diffusion problem of zeolite crystals. So in the nature, so we can see from a nano scale to the large scale. So at each length scale, we have a different material with a different porosity. So in fact, what we can see in each material, for example, diatoms, even the butterfly wing. So we have, in fact, a hierarchical porous structure. This means we have a different porosity, microporosity, mesoporosity, and even macroporosity. So we have, in fact, interconnected different porosity. So why the evolution make all the material with a hierarchical structure, and especially the hierarchical porosity exists and present everywhere in our living system. So in fact, we go to further to see all this living system with interconnected porosity. So this is in fact the common characteristic of all the living system. So this is due to the evolution. So why evolution makes hierarchical porosity in our body? So let's go to see one example. So when we see, in fact, the lotus, just a lotus leaf. So lotus leaf, in fact, lotus leaf, we know they have a very several clean property. But when we go further to see the structure by SEM, in fact, so this is the leaf. We have the presence of the cells. And when we see by SEM the structure, at first we will see the large porosity. So the large porosity is for the growth of the cell. So when we go further to see deeply in the structure of a leaf, we can see also other kind of porosity. That means we have the micro and the nano porosity. This kind of porosity interconnected for the, in fact, for the water and also nutrient transportation. So all the hierarchical porosity, they can provide different advantages for the leaf. At first, so this kind of material, this kind of structure have the excellent biocompatibility for the cells. And especially this kind of a hierarchical porosity provide the best, I said, best and optimized diffusion of a reactant and also metabolites. And also, when we have this kind of structure, it is also good for the absorption of light and also the CO2, etc., etc. So, due to, in fact, the presence of this kind of hierarchical porosity at different length scale, so all the pores are present at a different length scale, and also they are interconnected. So that's why, in fact, the lotus leaf is the best example to show the whole of the hierarchical porosity in living system. So in fact, we can conclude, in fact, hierarchically porous structure are present to maximize mass transport and the rates of reaction for the optimized function of life with the highest efficiency and the lowest energy consumption. So that's why, in fact, in zeolite, if we can introduce this kind of hierarchical porosity, so we can also have the function as the living system. So that's why in my laboratory, since a long time, we try to introduce different porosity in zeolite crystals. So microporosity, mesoporosity, and to keep, in fact, zeolite microporosity. So in fact, since 2000, so before to introduce, in fact, the different porosity at a different length scale in zeolite, we study already how to introduce, in fact, hierarchical porosity as we observed in living system. So here, I think one of the most important milestone in the field of porous material is, in fact, the self-formation phenomena of a pore hierarchy. So you will see it is a very, very simple reaction, very simple process, but we can use, in fact, the chemistry of metal alkoxide to generate immediately the different porosity. So in fact, we can use this kind of metal alkoxide to use, in fact, this very simple but also the most complex reaction in chemistry. So just use, in fact, hydrolysis and the condensation reaction to induce different porosity, and especially, as I said, it is a self-formation because we don't, in fact, introduce different force, and this reaction can generate different porosity immediately. So it is a very simple process. We just introduce a droplet, for example, in the laboratory, one droplet of metal alkoxide in water due to the reaction of hydrolysis and condensation, and by releasing, in fact, the water molecule and the alcohol, so we can generate immediately the micro, meso, and macro porosity, and even other porosity at different length scale in the material. So we can prepare all kind of material if you have, in fact, metal alkoxide precursors. So I just show you the result because due to time. So here I have also the video, but due to time, I just show you, in fact, the result. So in fact, by this simple reaction, simple process, and we can immediately to introduce microporosity and the mesoporosity very uniform and interconnected, and especially super microporosity, and even we can have the pore size less than 1 nanometer. So this kind of material, so we use only one-step synthesis process to obtain the bi-inspired, hierarchically interconnected micro, meso, and macropore metal oxide. This shows really the power of the chemistry of metal alkoxide. So not only, so we can use all kind of metal alkoxide to prepare, in fact, the metal oxide, so single metal oxide, binary, and even composite, so material. So however, so I have no time to talk about this. So when we use magnesium, silica, and gallium, this kind of precursor cannot lead to the formation of the hierarchically porous material. So we can discuss why. So due to the time, I don't want to go further, but I just want to emphasize this. Not all the metal alkoxide precursor can lead to the formation of the hierarchically porous material. So in fact, all this kind of material, for example, titanium, is used in the photocatalysis and also for the VOC abatement. So when we use, in fact, this kind of material, hierarchically porous material, due to accelerate diffusion of a molecule, and also due to the presence of the microchannels, so we can have also enhanced light absorption. So that's why, in fact, when we use this kind of material for the gas phase photocatalytic degradation of ethylene, so we can see, so this is just a titanium commercial P25, and this is a titanium with only mesoporosity. But when we introduce mesoporosity and microporosity with interconnected porosity, so we can increase, in fact, practically doubled the activity. This shows, in fact, when we introduce interconnected hierarchically porosity, we can increase really the reaction efficiency. So it is very good. So titanium, zirconia, etc., all the hierarchically porous metal alkoxide. So only when we obtain this kind of material, we obtain in amorphous phase, and it is not a zeolite phase. So that's why. So from, in fact, the metal alkoxide and even, for example, the mixture of silica and alumina, so we, in fact, from this, we try to introduce the crystallinity. So the process is very simple. This is for example, amorphous alumina silica composite, and then we just impregnate the surfactant, the structure directing agent, and then so we use also, in fact, we introduce also glycerol in the large channel, because if we don't introduce the glycerol, so when we make the hydrothermal treatment, so the transformation, the crystallization is too high, and then the large porosity will be destroyed. But when we introduce, in fact, the glycerol in the large pore, so we can keep, in fact, the large porosity. So in this way, we can keep the large porosity, mesoporosity, and also the microporosity generated by the formation of zeolite. So here, just one example, so we can see the formation of the transformation of amorphous phase of hierarchically silica alumina composite, and finally to get this kind of hierarchically porous zeolite. So we prepared, in fact, the ZSM5 beta zeolite, TS1, and also other kind of zeolite, and we used in different reactions, for example, for the large molecular cracking, and also for the selective oxidation of different molecular, and especially for the biodiesel synthesis. So it is also good because we can transform, in fact, the hierarchically porous metal oxide to zeolite. However, the mechanical strength, it is also a drawback. So that's why we continue in this field, and then we would like to introduce directly in the zeolite crystal different porosity as Javier did. So here I just show you zeolite single crystal with ordered and hierarchically interconnected different porosity for green catalysis. So here I just show you a Vexadyl templating and upscalable very simple zeolite crystallization process. So here we have, in fact, the zeolite precursor, and then we use, in fact, the hard templating. It is a carbon material. So this carbon material is made by polystyrene, and then we get, in fact, the inverse opal structure of a carbon material. And then we will fill all these spheres from inverse opal, and then to get the composite, and we make the crystallization, and after crystallization and after elimination the carbon template, so we can get, in fact, the single crystal of zeolite. So it is a very beautiful structure. I will show you immediately, and the process, it is also very simple. So this is the zeolite crystals we obtained. So in fact, it is just, in fact, a copy of the inverse opal structure, and in the zeolite structure we can have, in fact, all the micro, meso, and microporosity. So this is just one a single crystal. So you can see, so all the structure, all the zeolite crystal have the uniform morphology. So I just don't want to go further. So you can see all the zeolite sphere connected together to form really the single crystalline zeolite. So how to prove, in fact, the single crystalline? So this is, so first example we did with the synthesis of ZSM5 zeolite, and this is, in fact, the STM structure. So you can see lot of ordered porosity inside. So this picture to show, in fact, how the zeolite sphere connected together to form, in fact, the single crystalline zeolite. So here I can show you also the due to here you have two, in fact, two zeolite sphere. So these two spheres are interconnected by, in fact, the zeolite phase, and you can see we have the continuous crystalline phase. This is a direct proof of the single crystallinity of our zeolite. So here, just several scheme presentation how to form the single crystal. And when we use this, in fact, in the large molecular cracking, so Javier did also, because this is a standard reference reaction, so we can see not only, in fact, we can have, in fact, good cracking activity. So cracking activity compared to the nano-sized zeolite, this is a commercial zeolite. Another micro-sized commercial zeolite, so you can see we can increase largely the conversion due to the good diffusion property. This kind of material, this large molecule cannot penetrate inside of a commercial zeolite. So that's why we have not only the good activity, and especially we can have also the secondary reaction. This means the molecule can penetrate very easily in our single crystal zeolite. So not only, so we can modify, in fact, mesoporosity and also the large porosity of our single zeolite. So here, I just want to show, in fact, this zeolite. So even we can modify the mesopore and the large pore, but we found that this zeolite with this kind of porosity shows the best performance. So why? I will show you this later. So here you can see, so this is this porosity 48 and 120 nanometer. So when we modify, in fact, the mesoporosity and the microporosity, so we can increase, in fact, the stability. So this is in another reaction, methanol to olefin MTO process. So not only, so you can see also the ethylene and the propylene selectivity, it is largely higher than nano-sized and commercial micro-sized zeolite. So it is still this with the 48 and the 120 nanometer zeolite, this zeolite gave the best, in fact, the performance. And even for the coke formation, so also this zeolite, so all the hierarchically porous single crystal, they have the much lower coking formation compared to nano and the commercial micro-sized zeolite. And among all the hierarchically porous single crystalline zeolite, so this is best zeolite which gave the best performance. And not only, so we can see, so the reason why, in fact, our zeolite have the best performance. So when we make the measurement about the relative diffusion, so this zeolite has the diffusion rate, in fact, practically 10 times higher than the commercial and 7 times higher than the nano-sized zeolite. So this is a very important information to show not only when we introduce the different porosity in single crystal zeolite, and when we adjust, in fact, the mesoporosity and the microporosity, so we can get even more, even better performance. So that's why. So this is also example. Not only we have the whole of mesoporosity, but we have also the whole of microporosity, large porosity. So here, just to show you. So this is, in fact, we used as the commercial micro-sized zeolite. So the in fact, the utilization efficiency is around 47, and when we use nano-sized zeolite, so you can see even nano-sized zeolite, there are still small part of zeolite cannot be used. So we have the utilization efficiency around 60. But when we use our zeolite, in fact, single crystalline with hierarchical porosity, so we have the utilization efficiency around 87%. So this is very important. So not only we can synthesize CSM5, and I just show you several examples. For example, beta zeolite, we can introduce also all different meso and micro porosity for large molecular cracking, and also for the alkylation in liquid phase. And we can synthesize also the TS1 zeolite, and then for the effect to eliminate for the removal of sulfur in the petrol. So here I just show you several results. So I would like to say also, we also modify, in fact, look, the mesoporosity and the large porosity, mesoporosity, large porosity, but we keep, in fact, the microporosity from zeolite. So when we compare, in fact, different zeolite with different porosity, so we observe, as CSM5 I showed you, always this kind of porosity gives the best, in fact, the performance. This is just to show you, not only we have the less coke formation, and also we have the best efficiency for the sulfur removal from the petrol. So this is one question, in fact. So when we introduce different porosity, so we can increase the performance. But as I showed you, when we adjust mesoporosity and large porosity, why we can still optimize, in fact, the performance of zeolite. So the question is, what is the best microporosity, mesoporosity on the basis of micropore size of zeolite in one zeolite single crystal? Whether we can predict for this. So if we can predict this, so we will have already this design principle to get the optimized performance of zeolite. So come back, in fact, to the living system. So in fact, here I just want to introduce, in fact, generalized Murray law we developed and to establish, in fact, the hierarchy law of the nature. So when we see the kidney, our kidney, the kidney is, in fact, the very important chemical factory in our body, and in the kidney there present, in fact, there exist three kind of hierarchically porous structure. So I don't want to go further. There are three kind. So three system of porous. There are three porous, hierarchically porous system. So when we see, in fact, the leaf, at the beginning I show you. So in one leaf, so we have, in fact, different branch at different level. So they have a different porosity. So whether different level structure are randomly generated, or there are a relationship among these different level structure. That means the porosity. So if it exists, what is this relationship? So in fact, when we see the ice and even the river, you have also this kind of hierarchical structure, and even you can see. So we have also this kind of hierarchical structure, even when we go further to study the music. In the music, we have also the hierarchical structure. Without this hierarchical structure, the music is not very nice. So, in fact, in the nature, we have already Newton's universal gravity law. But in fact, as I showed you, we have also the hierarchy law in the nature. So, in fact, we want to find this law. In fact, in 2026, Murray so already found this structure. That means the large pore size has the relation with the next, in fact, parent pore. So, however, this law did not use, in fact, in the material design because due to, in fact, the problem. So, because this law did consider, in fact, the mass variation during the mass transportation. So that's why in my laboratory, we introduce, in fact, the mass variation during the mass transportation, and then, in fact, we design, so, and finally, by design the theoretical model, and finally, we found, in fact, in one material, when we have three hierarchical porous level, so the relationship between microporosity, mesoporosity, and mesoporosity, and microporosity. And finally, by this, we just synthesize the material, so for example, zinc oxide, and to have three kind of porosity, 1 nanometer, 18, and 1000 nanometer. And when we test in liquid phase, gas phase, and solid phase, and we can see, in fact, they have really the performance largely improved due to time. So I don't want to go further. So this is the result for the liquid phase. We have the large increase in the performance, and for the gas phase sensing, without porosity, 1 level, 2 level, and 3 level hierarchical porosity, and even for the, in fact, lithium battery, so we can see we have, in fact, the 25-time increase in the storage capacity. And so in the future, in fact, we would like to use this law and to design, in fact, other performance zeolite. So just last example, so when we use the Murray law, and when we compare one, in fact, one sample with this is follow the Murray law, and two others which are not respect the Murray law. So we can see, in fact, the sample obeying, in fact, the Murray law have the best property in the large molecular diffusion and also in the large molecular cracking. So finally, I just want to conclude my lecture. So to show you, in fact, in the future, so in the generalized Murray law, we considered only, in fact, the level of porosity, but we don't introduce, in fact, the angle between the different pore. This is also very important. So we have to introduce other descriptor in the generalized Murray law to get ready the design principle. So this is our perspective. So to introduce, in fact, different descriptor, different parameter in the generalized Murray law to establish really a design principle for the high performance material. So finally, I just invite to check, in fact, if you are interested in for this kind of material. So one review paper, recent another about, in fact, the synthesis, and finally about really the zeolite. So sorry for the time. So I just want to thank all the organization to support our work. And finally, thank you very much for your attention. Yeah. So in fact, sometimes we neglect the presence of a large porosity. The large porosity, in fact, play also a very important role in the diffusion. So I think in the zeolite, at first, the large porosity and the mesoporosity play the role for the diffusion. But zeolite, in fact, will play really the catalytic role in the reaction. Yeah. Okay, thank you.
Dr. Crăciun continues the research and development activities as a postdoc fellow at the University of Pennsylvania and as a Humboldt fellow at Ludwig Maximilian University in Munich, Germany. He is a technology manager for America's catalysis division at BASF Corporation in New Jersey, USA, responsible for various types of catalysts as a technical expert, being part of the global chemical catalyst business team. During the past decades, he published numerous articles in various impact factor journals, delivered over 36 oral and poster presentations at national and international symposia, and holds the principal investigator for 7 patents. He is currently the honorary consul of Romania in New Jersey, USA. So, Radu, thank you for accepting the invitation, and the floor is yours.
Thank you very much for invitation and for inviting me, and thank you for coming. And I would like to apologize that I will have to leave early because I had to catch a plane. It's a great event, and I congratulate the organizer having this great event. And it's an honor and privilege for me to talk and be a speaker beside so many valuable attendees from various great universities. Now, you saw some very interesting and very nice pictures of interesting materials, zeolites, and all these modified zeolites. This is great. This is academic research, and the imagination, the sky is the limit. Well, I want to bring you a little bit down to earth. And what I'm going to talk to you a little bit will be about industrial research and specifically industrial catalysis. You have some boundary in a way because you are driven by the market and the market needs. As I said, I'm part of the business team, so you're gonna listen a presentation which is a combination of technical marketing information. I'm gonna have some more deep dive into some interesting material, and because that's what I'm using to promote our catalyst to the customer, but it's gonna be a combination. I'm gonna tell you a little bit about where I'm coming from BASF corporation perspective, because BASF is a huge corporation, worldwide presence. It has a global presence, and our motto is that we create chemistry for a sustainable future. So I'm going to point a little bit about this part as well. When you talk about industrial catalysis, you have some challenges because you go from a couple of grams or a couple of 100 grams, which you can synthesize in the lab, to tons, hundreds of tons sometimes. And you have to thousands of tons, and you have to produce it continuously. I will talk briefly because it is a material science meeting, and I'm going to talk a little bit some interesting technologies which we develop, and we start promoting some new precious metal catalysts into the market, especially into the fine synthesis market. And we came with this near edge coating technology, which allows us to produce high amounts of precious metal catalyst, but in a very economical and sustainable way. The other thing I want to touch is this newer issue which comes with chrome promoted catalyst in the market. The chrome is a great promoter, but it has some down things because it is a toxic, and when you work with it in the high amounts, you have the exposure, worker exposure, either at the manufacturing site in our case, and then later on at the customer side when they're using this becomes an issue and a hazard, and of course it's dangerous. And And I will talk about how some technology which we developed in terms of catalyst testing. When I saw so many interesting structure, I think what I'm going to show you here is high throughput testing technology, which we have available even as units, and we sell it to universities. Maybe you get interested in, because we are cooperating, and it's part of our BSF corporation, HD GmbH, which is a company which offers these units. And then I will, if I have time, depends on my how fast I'm going to be able to go over, I will talk about a bit of this effort on alumina catalyst, where there's a big effort right now, both globally but also internally at BSF. So where I'm coming from in BSF Corporation, so as you can see, BSF has many divisions: chemical material science, industrial solution, nutrition, ag business is big, oil, construction chemicals is not anymore, it was sold. But I'm part of the surface technology team, and I'm active in BSF Catalyst division in US, in New Jersey. This subdivision, this division has several subdivisions. Of course, it has the mobile emission catalyst, catalytic converters, the chemical catalyst, refinery. So I think my colleagues from refinery would have been very interested to listen to some of the talks today, because they are using these zeolites a lot. Then battery material, which is a new, relatively new subdivision, and it's going to take off a lot. This will kind of fade away and make space for the business for material, battery material. And then we still trade pressure, metal, and recycle. So let's go into deep into the main topic, which I would like to present. It's a bit off what you have heard, because again, it's an industrial perspective. What you heard, it was the academic research. Now, how we are doing research in a big corporation, and what is the road of success? And the first thing which I want to mention, anytime when you come up with some very interesting idea or proposed catalyst or any other product, you really have to have a business goal. Meaning you have to make sure you have a place where once you produce, you invest so much to develop, design, manufacture. You have to have a constant and reliable market to sell it. Also, when you produce these new things, you have to make sure you have the raw material which is needed. Because when you produce tons, hundreds of tons, the availability of the raw material is important. You just don't go to Aldrich and order several grams of some raw materials. Anyway, here are some important aspects which we, as a corporation, industrial research, we consider. So I mentioned the raw material which we use, but also because you're a big corporation, you are liable for any pollution. So you really need to consider, especially lately, we put a lot of emphasis on the CO2 emission of anything which comes out from our plants. The other thing I mentioned, the market is important, and we have a very strong analysis of it's a must to have a good business case, meaning you have to evaluate when you design that product that you will be able to have a market which is a growing market, and you will recover what you invest. Another important, and this is crucial for a corporation, is to make sure when you develop that new product, you have an IP gap. IP stands for intellectual property. When you play a global player, you cannot afford to invest millions of dollars in some new product, which at the end of the day, somebody else comes on the market, like Grace is coming and say, hey, stop. We did this before you, so you cannot sell. That analysis is very important. It is also important for the strategy of the company and the growth in the future. So we put a lot of emphasis on this IP gap analysis and ensuring uniqueness, novelty, performance of this new product. Of course, you saw a lot of aspects before me that you can play with: shape, metal dispersion, morphology was a lot. Didn't see metal dispersion, but I'm going to talk about that a little bit. Then, in order to be able to go from the idea to the market, you really need to have a very fast testing protocol, and reliable. And I'm going to show you some of the tools which we have available for that. The new digitalization era, it's important, and we are using it as much as we can. Digitalization in our company, it's a key word. It's everywhere in the world. And I'm going to touch a little bit about that too. When you develop a product, you just don't sell it. You're not a responsible company if you just sell the product and then, okay, I don't care what's happening after that because I sold it. No, we kind of work with the customer and try to help them optimize further the process, and we work with them. And then, of course, we try to be helping them to optimize the process and to have ensure also our catalyst to be in their plan. And I mentioned safety. Safety, it's important part. It has to be user-friendly, and it has to be recycling. And I'm going to touch some of this. When you design a catalyst, most of the part, like composition, morphology, performance, you saw it's a lot of detailed lab activity. I'm not going to get too much into detail, but we also, when we develop new catalysts, we put a lot of emphasis on this part too. But what we need to have as an industrial player, we need to have a lot of attention into the manufacturing part. Meaning, when you have a new product, you need to make sure that product can be done in a very small amounts of steps, because every step costs money. And it has to be easily scalable up, so you can produce a large amount. And then to make it, it has to have as low as possible in terms of cost, manufacturing cost. You need to minimize the raw material. If you have a precious metal, you can realize how much a kilogram of catalyst would cost, even if it has only 5% palladium. I mentioned complexity, and when you are a player, industrial player, this regulatory factor becomes a big issue because we are responsible for our product. So you can see, beside all these other very nice and interesting aspects of developing a new catalyst, we need to worry about, especially on this part as well. I mentioned raw material. There is a lot of emphasis on biomass, and BASF, it's switching gears as well, and it emphasizes a lot the green renewable material. For no particular reason, we kind of closed several steam cracker, you know why? Especially in Ludwigshafen in Germany. And our upper management CEO came in just 2 months ago and said, we're gonna close the steam crackers, but we're gonna build another chemistry based on biomass. Biomass could be all fats, any carbohydrate. But what we will do, and it's going to be a strategy for the next 10 years, is we're going to develop an entire chemistry, an entire industry, like it was for the steam cracker, using the bioethanol. And the ethanol, you kind of have a dehydration step, or you can, and then you can start building on these ethylene oxide and all the chemistry which comes from there, and the biofuel and bio-based chemicals. It's again, whatever you can get from ethylene, from the oil, from the petrol, that's what you can get from ethylene, from the bioethanol. It's a biorenewable, and it's a CO2 neutral technology. We also work in trying to convert biomass directly into some direct into the higher chain hydrocarbon. But for now, it's one of the main growths. I'll talk a little bit about this CO2 reduction effort which we have at BASF. I want to point out this aspect. It was we did this calculation, and this number is being now very popular in a way in the industry, because it shows really what kind of pollution will come from using precious metal. So only to produce 1 kilogram of precious metal via mining, you generate anywhere from 24 to 35 million tons of CO2. That's so huge. So you can imagine any new callus, large scale, which is used in terms of of precious metal. Any reduction of that precious metal on your callus will generate huge reduction in CO2 emission. How can you do that? You can do, of course, you support this precious metal anyway, but you can play a little bit with the support. Yes, zeolites could be a great support for some of these precious metal. But what we are working, and I'm going to show you quickly our effort to develop some new callus, reducing the loading of the palladium of precious metal from the typical 5%, which is used in industry, to very little, 0.1, 0.5, without compromising activity, without, and on the contrary, having some better selectivity. And with this type of approach, you can reduce the metal content up to 90%, and of course, this equates to a lot of reduction of the CO2 emission, plus you bring savings to the customer. So just here, just one example. We have for one type of reaction, and I just put generic one, nitrobenzene reduction. You can think about this nitro group reduction not only in the into the nitrobenzene, but you can think that this nitro is in a more complex matrix molecule, where you need to selectively reduce the nitro to the amine, for instance. So we developed a new technology which when it's called a near edge coating technology, which is known, but we improve it, and it's kind of a new near edge coating technology versus the typical impregnation uniform impregnation technology which we use to generate this product, this callus. So when you have a uniform, you see the dots here, they are all spread all over, and then that ensure very good dispersion and uniform, and in principle that's what you wanted in the past. So here's a kind of a graphically shown uniform. Then the conventional edge coating technology, because I said this technology was known and developed in the past, and it is being using, and then the new edge coating technology. And what you see here is you can see how the palladium, in this case platinum particles, are spread only on the edge, on the surface, and it is fully utilized for the catalysis which you need. And this, because in many cases, especially when you talk about some bulky molecule, this inside the pores, a lot of these palladium, they are not being used. They are just spectators and they are there. So what you need a good platinum, palladium, or other metal on the surface. How is that reflected in the activity? And here's a little bit of actual data for one of the typical reactions. So when you have the uniform, you have a XPS palladium dispersion. It's uniform. You have a good signal. But you can see, because it's a surface technique, when you have a near edge, it's much better signal. So you see most of the platinum, it's well dispersed on the surface, at the edge. That's where you want. How is that reflected? It's reflecting ultimately with a better activity. In many cases, especially when you have powder, precious metal, you need to recycle, or you need several cycles to be using this. So you regenerate and put it back, and here's some effect of uniform. What's happening? You lose activity in the near edge. You still lose activity, but the level of losses is much lower. So I hope this, these graphs are quite relevant. What's the power of new edge coating technology, which we offer for the new precious metal catalyst. This is one example how we work, how we develop new catalysts, having in mind that we want to reduce CO2 footprint. Another example is going from the chrome-based promoted catalyst, which is an excellent promoter, to a chrome-free. There are a lot of challenges when you do these things, when you go from that, when you remove chrome, and you need to address them. And here's just an example for one of the syntheses, the butanediol to BDO. It's a big business, and then further on, this BDO is used a lot in a lot of other materials and industries. So the scope for this study, for instance, which we done in cooperation with the customer, was to go from a chrome-based catalyst, copper catalyst, to a chrome-free. In this case, the hydrogenation process is catalyzed by copper as a metal. This is the process, this is the reaction, and how do you do in a very fast and responsible way? When you player in the market, it's very important to go fast from an idea to have a product in the market. You don't have 2 years or 2-3 funding 2-3 postdoc or PhD to do the work. You need to do it fast. So what you see here, it's one of the unit which we use in cooperation with HTE, which are located in Heidelberg. This is a 16-fold high throughput testing catalytic testing rig. And it has a excellent reproducibility. You can play with the reactor size. You can have a huge infinite way of combining things or playing with the parameter. And then all the parameters from the reactor, from the testing, they are put into a supercomputer, and we use the most modern modeling and computer tools to play with it. And here's an example. In this case, for this particular application, where we play with two types of catalysts, and we start playing with the ratio of the two catalysts which are used for this process, then the residence time, and the way how it is filled. Then you need some reproducibility, so you need to make sure that it's reproducible and you stay in a certain variation of the data, so you are reliable. you have reliable data. So you can see this can be done in, depends of the space velocity you want to have, either in a week or 2 or 3 weeks. And then you get a huge amount of data. And you can see here some plots where you have the selectivity versus conversion, and for different type of the main product, the side products, the main product being video. And immediately analyzing this data, you can plot it, and then you use model. In this case, we use just a typical MATLAB, but we have more complex system but it was not needed, because you can see our modeling follows very nicely experimental. Good agreement for the screening. So what the message from these slides, which I showed to, is that as an industrial player in catalysis field, you need to have a fast way of testing, and very reliable. And I can tell you that this HDE, which is part of BSF, they are doing work for other company, even for our competitor, but they are firewalls, so we don't know too much. And then that's clear. But it's part of our business, and we need this kind of testing, because you need to go fast from the idea to the market. And just to summarize, you can see that we have a very reliable, very full of valuable tools in this high throughput system, where you can do this fast testing. The results are very good, and I showed you that the results which we get, it's in agreement with models, and we can model and we can understand exactly what's happening and how to optimize the catalyst or the process. It gets very fast to a commercial part. Okay, I don't have too much time left, but I'm gonna just 3 minutes. I will just rush through a little bit through this alumina-based catalyst which we offer. I mentioned quickly that the new raw material is bioethanol, and the key for doing the hydration, it's have a very good catalyst, and the shape of the catalyst plays a big role. And here it's an art. I mean, we have different shapes, from cylindrical to some fancy shapes. These fancy shapes, what brings is that it allows to have a much lower light up temperature, maintaining the pressure drop and all that, the conversion and all the selectivity. We use models. I will skip that, but just to summarize, because I want to leave at least a couple of minutes for discussions or questions. We, as a big player in catalysis, globally in commercial, we put a lot of emphasis on new idea, analyzing the IP gap to make sure we are there with novel things. We have very fast tools which help us to go from idea to the industrial scale. We put a lot of emphasis on the type of raw materials, on the emission. We as a BSF, we kind of stated that by 2050, all our technology will be CO2 neutral. So we will not be a polluting thing. We cooperate, and it's part of us, this high throughput company. If any of you is even at the university, because we sell this testing it to university, let me know. I'm going to put in touch with them. And one of the example which I talked a bit more, this new edge coating precious metal. It's really a new technology for those who are using this kind of catalyst. It really helps our goals with this, I think I'm done and I'm ready. And thank you very much to the HT team who helped me with put some slides. And my colleagues, the marketing, global marketing manager, and the team which I'm working BSF. And thank you once again for inviting me. It was a last minute, it fit. I could go now and catch my plane. And I will wish you a very nice and enjoyable stay in Romania. It's a great country. I love it. I promote it. Thank you for your attention.
Thank you very much for being here. Thank you for your nice presentation. So if we have questions, yes, please.
So it is part of our business model. We can offer the full package, including recycling. And our recycling technology is 99 point plus recycling of what we get, of course. The loss is not in our technology. The loss mainly is how the customer is using and sending back the recycling. But we also try to educate them. We go there and we'll say, hey, even when you wipe out the lab or the something with the napkin, you need to put that napkin into the recycling because you might have $10,000 worth of palladium. So.
The questions? No?
Okay.
If not, oh, sorry.
That's what I mentioned initially. Many cases, I mean, we have two, I would say just two main, let's say there are more, but the scientists can come with ideas to us, to the business team, and see is any need of this kind of catalyst on the market, and then we analyze it from the market perspective. I told you we put a lot of emphasis on it. That's one way. But we also, most of the cases, the scientists will look at us, and especially at people like me, because I'm a technical person, expert into the business team. And I mean, I need to see what the market or the commercial person doesn't see, meaning the technical challenges and how can those be addressed. I need to have a very good relation. I have a good relation with the research. I came from research, the business thing. So this is not the way of addressing what you asked.
Thank you. I have a short question. So you said you improved the deposition method for platinum for the
any palladium,
with a new
rhodium.
edge.
Rhodium is even more expensive. It's the most expensive right now.
Have you also tried to decrease the amount of platinum because you are keeping in all cases 5%?
Yeah, I mean, I just showed an example. We 5% of just for the purpose of showing it. But the ultimate goal and the product which we sell is instead of 5% is 0.1 or 0.5%. So it was just easier. I mean, I have data, but I just for the purpose of the message.
Yes.
Well, that's where it's our secret, because we are playing with the support. And of course, you're right. the support plays a role, and it's also an art. What kind of support and what's the source? When you talk about carbon powder, you have different one. And if the customer say, "Can you tell us what support you're using so we can do some studies?" and say, "No." So that's where it's part of the art. It's not only the technology, but also the type of support. And of course, you need, depends on where you use the platinum or the precious metal. Support can or cannot be.
Thank you. Thanks again to Radu and all the speakers of this session. So let's continue. We have the coffee break until 11:15. Thank you. Okay, so let's start. Let's continue this morning session. So it is my great honor to introduce Professor Andrew Rapp. Sorry. He's the Blanchard Professor of Chemistry, Professor of Material Science and Engineering at University of Pennsylvania. He earned his PhD Physics and Chemistry in Massachusetts Institute of Technology in 1992 and was an IBM postdoctoral fellow at University of California at Berkeley. He received several prizes, mentioning here only a few. National Science Foundation Career Award in 1997 to 2001, Alfred Sloan Foundation Fellow, and Dreyfus Teacher Scholar Award. He leads a group that creates and uses new theoretical and computational approaches to study complex systems in material science, condensed matter physics, and physical chemistry. So, Andrew, please, the floor is yours. We are waiting for your presentation. Yes.
Okay, good. Oh, good morning, everyone. I must tell you, I was really pleased to receive the invitation to come to this very special conference. And then I told a professor colleague in my department that I was going to Romania, and his name happens to be Virgil Percek, and he is himself Romanian. And now he tells me new information about Romania every day. I get another email, Romania news. And so I just got more and more excited to be here. I almost feel like I'm honorary Romanian a little bit. So I'm very happy to be here. And it was great to see that the previous session really has nothing to do with what I'm going to say. So it will be kind of a fresh start. We will share some ideas. And I hope to keep things a little bit general, so you pick up some new ideas. We don't have to get too much into the exact details of any one topic, you know? But I really want to share the idea of how can theorists think about heterogeneous catalysis. Heterogeneous catalysis is one of these complex problems that we've been working on for a century. So what is new? What progress have we made? What progress can we make? And what are some new techniques that allow us to get there and some new insights? Okay. All right, so I think that many of you already feel motivated that heterogeneous catalysis, especially for energy transformations, is very important. Over the last century or so, we have created a tremendous amount of carbon dioxide, and we will need to do something about that. And there are many sectors of our economy where this carbon dioxide is produced, and some of it is in transportation, and some of it is in industry. And those are the two key areas where heterogeneous catalysis can really help us a lot. And so some of the motivations for the topics I've selected today are ways of producing alternative fuels and ways of making green chemicals, and especially harnessing carbon dioxide. And but I think you'll see the insights are more general than that they could be applied to other catalytic problems. Okay, so first is the production of hydrogen through electrocatalysis. There's some interest in using hydrogen directly as a fuel. It has the great advantage that at the point of consumption, there's really no pollution since you just create water. It's not entirely practical, but I think even more important is that we're going to continue to need sources of hydrogen for all sorts of chemical transformations. So there are many reasons to want to understand how to produce hydrogen. So right now, we generally produce hydrogen from methane. And this costs quite a lot of additional carbon dioxide as we get the hydrogen that we want. But if we could do it electrochemically, this could lower the effective CO2 equivalent, the energy equivalent cost of producing hydrogen dramatically. Okay, so you know the idea would be to start with water and then have the reduction reaction happen so that the protons become hydrogen molecules. Okay, and so we can imagine these sorts of energy transformations in a closed cycle where we have dynamic interchange between different sorts of molecules, but that we produce fuels and then we store fuels and we consume fuels, but we don't let the carbon dioxide get away, and we can therefore achieve a carbon neutral economy. Okay, there are many different molecules that we could potentially be shooting for. This is an interesting graph. It takes a minute to, how many of you have ever seen a graph like this before? Okay, a few. So the idea is that this shows how much energy content different carbon-based sources have, and this is the value of them. So coal is still quite cheap, and it has a fair amount of energy. But like pure carbon monoxide is actually considered quite a bit more valuable. But so these are some of the products that are, really desirable because they're liquids at room temperature, and so they could be a potential next generation green renewable fuels. Okay, and there are many catalytic ways to do this, but a theme of my remarks will be when we get to the carbon dioxide harnessing section is, can we get to products that have more than one carbon? That's a big barrier to get over. That if you say I was able to produce carbon monoxide, okay, well, what do we do with that? You need a next step. But being able to produce multi-carbon products, that's really very exciting. Okay. So this is kind of, in a nutshell, what one of my big themes is going to be, and that is heterogeneous catalysts cannot be entirely specified by the composition of the bulk material that you acquire to use as the catalyst. That the surface changes quite considerably as a function of its dialogue with the environment. As you change the pH, as you change the voltage, various things happen. I will show it in a little bit more detail in a few slides, but this is more or less the same surface, but this termination is not active for hydrogen evolution, and this one is active for hydrogen evolution. And as I'm saying, it's more or less the same starting bulk material. And so our theme is that theorists can help explain the complex results that we see in heterogeneous catalysis, first of all, by solving what does the surface actually look like. If you don't even know chemically what the surface looks like, how are you going to be able to talk about the chemistry that happens on that surface? So that's kind of the way we're positioning that. And then I'm going to talk about ways of tuning the catalysis through essentially coadsorbates, but in a very, I hope, strange and interesting way that you will find thought-provoking. And then finally, I will talk about some new methods to predict the composition and therefore the properties of surfaces. Okay, so this is our outline. Okay, so begin on the left, looking at hydrogen evolution and carbon dioxide reduction reactions. Okay, so if there's a better place for me to stand. No, I think where I was is about as good as we're going to do. Okay. Yes. So basically, we're talking about electrocatalysis problems, and I'm going to introduce you to a class of materials that are metal phosphides. And I've just picked for us to look at nickel phosphides for today. The reason is that nickel is a pretty decent catalytic metal, but then it can be mixed with phosphorus in many different ratios. I didn't know this at the beginning. I thought, well, phosphorus is -3, nickel likes to be +2, so I guess I could figure out the ratio. No, it makes many different ratios. And the reason why that's possible is because these are all metallic compounds. They're not semiconducting compounds. Okay, so they're conductive phosphides. And so we're going to talk about a whole bunch of different ratios, nickel X and Py. And it turns out some of them are very active toward hydrogen evolution, and others, are wonderful for making multi-carbon products. So there's a lot to learn here, and we will talk about this. And it all comes down to what do the surfaces look like under different conditions, as I foreshadowed. Okay. So the first thing is, let's say we have nickel 2p. It turns out even nickel 2p is more complicated than that sounds. It makes a bilayer compound to get to the whole thing. There's a nickel 3p layer. Here, can you see? Nickel, 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 and phosphorus. But then the other layer is nickel, 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 phosphorus, phosphorus. So if you add up these two, you get nickel 6, phosphorus 3, and that makes the whole thing. Do you see? So the first thing you have to figure out is which of those two layers would even be the top layer. Okay? And that's a question that's answerable by the energetics. But then a lot of people stop there. They'll say, I took the crystal structure, I cleaved it. I either took this layer or I took this other layer. But the material can lose atoms to the reacting medium. and it can gain atoms from the reacting medium. So this is the beginning, it's not the end. So at the very least, we're going to annotate which layer is the most favorable one. And so what you can see here is we have a chart. You can see only nickel 3p2 occurs here. Now we're talking about the bulk material, nickel 2p, but this is the winning layer, okay? So in all of these, no matter what the conditions are, nickel 3p2 is preferred. And there's a lot of details here. You don't have to follow the details. But what you can see is there could be a phosphorus vacancy. It could be nickel 3p2. This is kind of like -1 phosphorus, +1 hydrogen. Then it could be nickel 3p2 just plus a hydrogen, or just plus 2 hydrogens. Then look at this, you could get an extra phosphorus, and then you could get 3 hydrogens. And there's a zoo of things that can happen, you see? So we're interested in the catalysis on all of those surfaces, because as you change the pH, as you change the voltage, you could shop around and you can get the surface that you want, that actually is good for the catalytic reaction you're interested in. Okay. So this is that picture that I showed you without saying anything about it before. This is this nickel 3p2 surface, and then here's 1 hydrogen. Can you see it there? Hydrogen is green in this graph, so it's just sitting in a nickel 3 hollow. And then this is another surface. Look, the phosphorus came first and occupied the nickel 3 hollow, and then the phosphorus bonded to 3 hydrogens. Are you getting what I'm showing you? At different conditions, either of those could occur. Okay. And then, so the point is, we find the stable surface termination, then we find from the Pourbaix diagram how much phosphorus or hydrogen we add or take away, then we figure out which ones are catalytically active, and then we can predict where are the good reactive conditions to get the reaction that we want to happen with a low overpotential. Okay, and so what we were able to do is look at a whole bunch of different phosphites. And that turned out to be great, doing this parallel study, because the same local structures kept creeping back in. So you might think, well, you have a crystal of nickel 2p, or then you have nickel p3. What's the relationship of those things? It's just one material or another material or another. No, but locally they have the same motifs, even though they start with different bulk. And so what you could see is this is one material, and here's a nickel 2p2 cluster. Here's a different material, and here's a nickel 2p2 cluster. Do you see? And so those offer very similar reactivity, despite them living in very different surfaces. But this also has an undercoordinated phosphorus, so it would have the reactivity of this and that, for example. And then here's yet another material, and it has that nickel 3 hollow that we noticed last time. But here's another guy that has nickel 3 hollows. But it also has phosphorus 3 hollows. So the zoology of these different local sites, it's almost like biochemists studying enzymatics. You see, the catalysis really happens locally. It doesn't globally figure out the composition of the material. It locally says, what am I bonding to? Does that make sense? So we're kind of finding emergent patterns that we didn't realize were there before. And then nickel P2 has phosphorus-phosphorus bonds. And finally, nickel P3 has a whole bunch of phosphorus-phosphorus bonds because they're phosphorus rich. You can see that. Okay, so here are the patterns that we find. There's a whole bunch of materials with nickel 3 hollows, and our conclusion is nickel 3 hollow sites, not good. Sure, they bind hydrogen, but too strongly. So you guys all know Sabatier's principle, yes? I don't have to teach you that, right? That you really want not that it bonds too strongly and not that it bonds too weakly, but just like in Goldilocks, it has to be the one where it bonds just right, okay? So these nickel 3s are useless. All they will do is grab a hydrogen, and the hydrogen will sit there forever. Then these nickel 2p2, they bind hydrogen too weakly. They're not so great either. The ones that we like are phosphorus sites that have phosphorus-phosphorus bonds. It could be a P3 hollow, it could be a P2 dimer, and those are the ones that the hydrogen bonding is gentle enough that the hydrogen can get on, and then it can find a second hydrogen and leave as hydrogen gas. It's the world's simplest catalytic reaction, right? H plus H. Come on, it doesn't get any simpler than that. But it turns out, therefore, tuning the energy of the adsorbed hydrogen is very important, and it's possible to have a wide range of control. Okay, so here is kind of our remarkable result that my students looked at 6 different compositions here in acid and base, and calculated what they thought the overpotentials should be. And they got these results. Okay, that's just a bunch of numbers, right? But then we looked throughout the literature and people had reported the overpotentials for all these different things. Now, unfortunately, theorists are good at looking at numbers. So my students are hoping you'll look at these and say, wow, they all look remarkably similar. But fortunately, we at least calculated the difference between theory and experiment. And you can see all of the differences are tiny. So we're able to quantitatively predict the differences and explain the differences in reactivity for the whole family of phosphides in acid and base. And so that brings a lot of rationality and understanding to this field. Okay, so you might want to know, well, who's the winner? It's this nickel 5p4 is the best candidate by far in acid and in base. And so we have a little graphical representation here. The diamonds are the reactivity in acid, and the squares are the reactivity in base. So you can see this nickel 5p4 has a very low overpotential in acid and a pretty low overpotential in base. It's the best out of all of these in base. Okay, so it's not as good as platinum, but it turns out it's almost the best thing other than platinum that's not platinum. And so it gives a quite remarkably high reactivity. Now, do you remember I said there were some sites that get poisoned? So it turns out that on a per atom basis, it's not quite as efficient as platinum because you first have to pre-populate all the poison sites, and then the sites that are perfect become perfect, and you get reactivity almost as good as platinum. But it's quite good. Okay, so now I'll tell you a little bit about carbon dioxide evolution, also on nickel phosphide. So now this should already surprise you. You say, well, if it does hydrogen evolution, why would it do CO2 reduction? Well, the cool thing is we're going to pick the nickel phosphides that were not the winners in the hydrogen evolution game. Okay, so those are the ones that have a good chance to do CO2 reduction. Okay, and so the mysteries I'm going to explain here are why does nickel 2p in particular form C3 and C4 products, which is really a great thing. That's what we want, because then we're getting close to molecules that could be starting reagents for chemical industry or fuels, and that's a promising direction. But we're going to show the selectivity is great. It makes the things that we want, but the activity is low. And for the first time, we reveal why that is. Our experimental friends have found that it's selective but not active, but we're able to show why that is. And then finally, how does it work? This business that I already foreshadowed about. How do you know when you get CO2 reduction versus hydrogen evolution? Okay, so this is the report. This is work by the group of Chuck Dismukes over at Rutgers. And this is really a great graph. What you can see here is that these tall bars mean that they're producing a lot of methylglyoxal, which is a C3 product, and some furandiol, which is another 1, 2, 3, C4 product. You see here? Together, that produces almost 100%. But as you change the voltage and make it more negative, do you see these stubby little discs that have almost nothing? All the rest that's not graphed is the hydrogen production, which we really don't want in this case. If we're trying to reduce carbon dioxide, generating hydrogen is just a waste on the side in this particular example. So the tall bars are the ones that we like. And so it's really only the voltages right near zero that are promising, and it's nickel P2 that's the winner, but there was no explanation for any of this, for how this all works. Okay, so we've been looking at this for quite a while, and so what we're emphasizing here is that it produces very little formate, which is not a desirable product, and it produces a lot of these C3 materials with great Faradaic efficiency. But do you see the turnover frequency? It's in 10 to the minus 6. That means you have to wait 10 to the 5th seconds per site per molecule. So not great, right? But nothing's perfect in life. And so we feel if we can explain why it's so slow, maybe we can get a clue into speeding it up. That's how theorists think, okay? All right, so we're doing the method that I showed you before. I won't go through it in detail. We're doing a Poirbet diagram to say, hey, if it's nickel 2p, which layer is preferred? Remember that part? It's the nickel 3p2 layer. And then what is the actual termination? This is called the Poirbet diagram step. So it acquires an extra hydrogen. And look, a hydrogen on a nickel-3 hollow site. Do you remember me telling you how terrible that was? But now it's good that it's bonding too strongly, so that's what won't make hydrogen. But the H will be there to attach to the CO2 as a hydride and start the CO2 reduction process, because we have to hydrogenate the CO2. So what we want is an H that's on there strongly enough that it'll still be there when the carbon dioxide comes through. Okay. So here's the first step, and it turns out the first step is the most important step. We start with carbon dioxide on the surface and this special H that I'm referring to as a hydride. That just means it's more or less like H minus, and so it's already been reduced by 1 electron to come onto the surface. And so what happens is, here's the CO2, it's just coming on the surface, and can you see the CO2 has become bent? It's sort of tilting toward the H. And then the reaction that we say is preferred is to make this this guy, which is formate, HCOO. We're making this. Now, the other thing that you might think we could make is HOCO, which is this pathway. But it turns out we're able to calculate that the barrier is higher, and as a product, it's higher. So this is just not the favored pathway. So we're going to wind up making formate. Okay, so now if you've been following along, paying attention, do you remember I said, gee, and formate is not a very valuable product, right? A lot of people feel that formate is kind of a dead end. And so why am I so excited about a reaction that makes formate? Well, I'll show you what happens next. So usually what happens is people make this, HOCO, and can you imagine putting another proton there? Then this goes off as a water, and at least you've made carbon monoxide. Okay, so this is a productive pathway, but only to single carbon products. So let's see what happens with formate. Okay, so this is a little bit more of a zoom in on what I was showing you. CO2, and it makes a bent version, and then it interacts with the hydride. Okay, I'm going to have to speed up a little bit. I'm doing okay. So here we go. We make this formate, but then you can hydrogenate further, and you make formaldehyde. And the formaldehyde cannot get off the surface, and it reacts with another formaldehyde to make C2 molecules and C3 molecules. And that's how you get this methyl glyoxyl and the other things that get produced. And so that's the trick, that this formate does not leave the surface, and so it continues to be reduced. That's what I'm emphasizing. And what I'm showing you here, this first reaction, remember this one, CO2 making the formate, this reaction is not voltage sensitive. The hydrogen's already reduced, it sees the CO2, it has what we would call a thermal barrier to get over. So if you say, well, just increase the voltage and it'll go faster. No, this step will not be accelerated that way. So we think this has to be catalyzed by a co-catalyst. And that's the message of this, that this is a great reactive protocol. And all the other steps are downhill to the C3 and C4 products. We just have to speed up this first step. So that's the message of our work here. And we think that's very possible. So that could open the door to multi-carbon product generation at a high Faradaic efficiency and a high rate, which would really solve a lot of our problems. Okay. Yeah, so I just said this. Why applying potential can't help? Because it's a thermal step. Oh, and if you apply the potential too much, you start making hydrogens. I think I kind of said that also. Okay. So we have ideas about co-catalysts, which I could discuss with you. And we actually have another, this is a side project that I'm not really going to get a chance to talk to you about, but copper is a pretty good catalyst for single carbon reactions, such as making carbon monoxide. But it's also slow because it doesn't bond CO2 very strongly. So the idea here is you make a dilute dual atom catalyst. So these are all coppers, but you put something else in here, and its only job is to capture the CO2 more rapidly. And we think that's a very productive step toward accelerating. That'll be more for single carbon products, but I wanted to tell you about this because this is a very recent result. Okay, so in the time I have left, on the bus today, we had a wonderful discussion about mechanochemistry. I wanted to at least raise your awareness that mechanochemistry is a thing. Okay, you probably know that even the ancients would grind minerals and they could make mercury in this way. There are other products that are made by grinding or made by high pressure, but it's really not used in chemistry that much because people feel it's non-specific, it's not controllable, who knows what you're going to get. So, but there's a small set of us who think, well, but what if we could figure out what you're going to get? What if we could make it specific? It turns out that there are cases where you can prove the mechanochemical product is different from the thermal product or the product you make through photochemistry or electrochemistry. And so that opens up some exciting possibilities. So I'm part of a team grant doing mechanochemistry in America, and there are some interesting teams here in Europe doing mechanochemistry as well. I think you'll see that that's a growing trend. And so if you're the kind of person who likes to get in on the ground floor of things, I would really encourage you to take a look at this. So this is a simple idea, but it'll give you a sense of how these things work. Imagine you take graphene, and so my student completely thought of this idea. So if you have graphene, there are ways to functionalize it. And you can functionalize it mechanochemically, and then you get molecules on the graphene. And it turns out, as a function of time, these molecules will diffuse. The question is, can we direct that diffusion and have the molecules travel where we want? And so what we're going to do is we're going to specifically rumple the graphene, and we'll see what happens. Okay, so these are analogies. There are other molecular systems where being able to definitively move a molecule or definitively rotate a molecule generates a known distortion that can give you mechanical actuations, everything from how muscles work to how enzymes work. And so these are referred to as molecular motors. So we're looking at directed diffusion on graphene as being in that class of systems where we're directing the chemical reorientation of a system. So here is our graphene from side view and top view, very plain. But suppose you start to curve the graphene, the p orbitals start off parallel to each other, but they don't remain parallel to each other anymore. And it turns out that we're going to find that for the molecules we're looking at first, they prefer to sit on the tops of the mountains. And so what you see here is that when you're near the mountain, the migration barriers are higher, and when you're near the valley, the migration barriers are lower, so you move faster. And so that helps you move from the valleys up to the mountains. And the simplest way to remember this is, if you're going to make a bond to graphene, you're trying to locally convert it from an sp2 carbon to an sp3 carbon. So you would need the other three ligands to bend down. So these are amenable to that kind of bonding, and the valleys are not. Okay, so this is the energy profile for the whole thing. If you start in the valley, it's not that big a barrier, and it's actually more stable. Not that big a barrier, more stable. And the barriers get bigger and bigger, and eventually it gets to the most stable up on the mountain. And so we've done some Monte Carlo treatments to figure out the profile as a function of time. Even if you start them all in the valleys, they'll eventually run to the mountains. And the speed depends on how curvy you make the graphene. So we think that's really cool, that you could specifically move the molecules where you want, and you could imagine rumpling the graphene over and over again to keep chaperoning the molecules around wherever you want. Okay, so that's kind of part one of our mechanochemistry story. Gosh, I'm almost out of time, aren't I? Okay, all right, then I'm just going to show you. Okay, so the cool thing is that if you have molecules that are non-covalently bonded, such as a benzene ring drifting around, it will prefer to go to the valleys. So we can have some things go one place and some things go another place. And that's valid over a whole bunch of non-bonded species. All of them will prefer to go to the valleys if they're non-covalently bonded. And so the idea that we're proposing is you could have an electron acceptor like this TCNQ, which would prefer to go to the valleys. And so you would have something come to the valley on the backside, and that would influence the chemisorption on the front side of something covalent. You see, you could do both of those things at the same time. Use your non-covalent bonding on the backside valley to influence the covalent bonding on the front side mountain. Okay. So I think I'm going to stop here. I actually had one more topic I was going to talk about. So if you have any questions about grand canonical Monte Carlo calculations to find surfaces. I can answer that in the question time. But thank you very much for your attention, and I'll look forward to taking your questions.
Thank you, Andrew, for this inspiring presentation. So we have time for 2 or 3 short questions, please. Luca?
For these calculations, we are just doing DFT methods, relaxing to the equilibrium structures, the local minimum structures. But then we also find reaction barriers through nudged elastic band. Doing molecular dynamics for catalysis is usually not practical because the barriers are so high. But when you talk about electrified interfaces, that's an interesting question. But because it's metallic, it cannot support a potential drop across it. So the main thing you would be doing as you change the voltage in an electrochemical cell is shifting electrons in and out and changing the Fermi level. And that's something that we can do. You see, so you wouldn't need to say what is the electric field distribution across the material. That would not have a significant impact. What we also do is include the dielectric environment of the solvent around it outside. So that's another electrical feature of the modeling. So those are 2 components of what you might be interested in.
Thank you. Other question? Yes.
Yes. I think that's a great point. So the last thing that I'm not actually going to talk to you about today is we can model non-equilibrium processes and we can model mass transfer into our system. So if we expose to a higher chemical potential of oxygen, you can see a surface gradually getting oxidized. And so what I will say to you is I showed you all the motifs that we were able to discover on the surface. There's this cluster, there's that cluster, there's this other one. So if we found that any of them was supremely active, then we would ask ourselves, what are the chemical conditions under which that type of site would be there in high concentration? But surely those sites are present through diffusion processes on the surface at low concentration for some of the others. But it's not enough to affect the rate very much just because their concentration is so low. So what we want is the most active sites in a pretty reasonably high concentration. But I agree, we want to keep increasing the complexity of the modeling so we have everything that the experimentalists have. That, you know, that's sort of a long-term goal.
Dario, the last question.
Yes. 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 It's kind of a coincidence, yes. I mean, we model it in acid, so we can say what are the active sites and how well do they do and how well does that compare to platinum. Then we go to base and we say now there's hydroxyls on the surface or phosphorus gets carried away. We redo the Pourbet analysis for a different pH. And so some of them were good in acid, terrible in base. Some were terrible in both. Some were good in both. So we just picked the composition that was the best in both. And I could report to you, that's the one that's closest to platinum-like ability. In acid, it's almost the same as platinum. In base, it's not as good as platinum, but it's the best among this family But we shopped around and I said, here, this one is the best. It's not for a magic reason. It's I ranked them and I told you which was the best one. Yeah. Sure. Yes. No. No, once we know all the intermediates and their energetics, we can do the forward reaction and its rate and the backward reaction and its rate. And especially for HER, there's only one intermediate. So it's the same intermediate forward and backward. So we can just read off those numbers from the data we have. If you're interested in HOR, we could tell you, we just didn't focus on that because we're thinking about, you know, fuel production and so forth. But yeah, it's all knowable. It's not like a new project. Yeah, yeah.
Thank you, Andrew,
Yes,
for this
thank
nice
you.
presentation.
Thanks, everyone.
So it's my great pleasure to invite the next speaker, Leonardo Aliotta, which is Director of Research at the Institute for the Study of Nanostructured Materials in Palermo, Italy. She is a member of the International Association of Catalysis Societies, member of the Management Committee of different cost actions, as well as of the Italian Chemical Society. She is also present in the scientific board of the Italian NRChem Interdivisional Group of Chemistry for Renewable Energy, and her research activities are related to gold-supported catalyst, synthesis, investigation of structure-activity relationship, and application in different reaction on noble metal supported on reducible oxides and perovskite-based catalyst and so on. So, Leonardo, please, the floor is yours.
So thank you very much for your kind presentation, and thank you very much for inviting me. I'm very glad to be here. It's my first time in Bucharest, in Magurele, and I would like to thank very much you, Mihaela, and all the organizing committee. So today I will speak just about our latest results on nickel-based catalysts for the dry reforming of methane. If we have a look at the recent literature, in particular articles published in 2022, we can see that there are really many reviews dealing with nickel and nickel cobalt catalyst for the dry reforming of methane. So different articles deals with the design of the catalyst, the effect of the support, the effect of the preparation method. Also, if we look at very recent article published in 2023, we can see that still we have a review on syngas production by dry reforming of methane, but also several articles are dealing with the use of photothermal reactions, since the dry reforming is an highly endothermic process. So many investigations are dealing on the use of solar energy in order to catalyze the reaction. Methane and CO2 are the most abundant greenhouse gases, and as already introduced by Professor Rapp, there are several reactions as the methane dry reforming that are very useful in order to transform such greenhouse gases into syngas that represent a very important building block for the Fischer-Tropsch synthesis, and therefore for the synthesis of many hydrocarbons, oxygenated fuels, synthetic fuels that today are very important. The Dry reforming reaction is a part of the so-called pre-reforming that actually consists in the steam reforming of methane, the dry reforming of methane, and the methane partial oxidation. Only the methane partial oxidation is an exothermic reaction, while the other two processes of reforming are endothermic, and depending on the amount, on the composition of the syngas, and therefore on the ratio CO plus hydrogen that we want to reach, it is possible to modulate the extent of such reactions. Of course, if we want to produce pure hydrogen, the steam reforming reaction, as here schematized, is the most interesting reaction, especially if a process like the water-gas shift reaction follows the steam reforming, and therefore a further step that is able to produce pure hydrogen and CO2 removal that can be used again for the process. In the literature, there are several articles, and there is somehow as a competition between researchers depending on their research topic, because, it's true that the steam reforming is the most interesting process in order to produce pure hydrogen. However, steam, partial oxidation, and dry reforming, all these reactions present some advantages and disadvantages. Just focusing on the dry reforming, that is my topic during this call. The dry reforming is a bit cheaper than the other two reactions. Also produce an hydrogen CO ratio that is almost equal to 1, and this is useful for the production of oxygenate by Fischer-Tropsch synthesis. And also what is very, very important is that dry reforming can be used the biogas, so is very useful from the conversion of CO2. But which are the problems related to the dry reforming of reaction, which are the metal the most used? Nickel, among that are here listed, nickel is active, is quite cheap, so for sure is one of the most used metals. And the problem, of course, as in all cases when we consider supported active phases, the problem is due to the sintering, and that can cause the activation, eventually to the oxidation during the process. Nickel is active as a reducing metal, and also the poisoning due to carbon deposition during the reaction. Indeed, as here it is schematized, the dry reforming methane involves several side reactions, and among them the side reaction that we have tried to limit are the reverse water-gas shift reaction that can lead to the decrease in the hydrogen-CO ratio, and among them the several reactions that can cause the carbon coking are the decomposition of methane, the disproportion of CO, also known as boudoir reaction, and hydrogenation of CO2 and hydrogenation of CO. In the literature, it is reported that during the reforming reaction, different types of carbon coke can be formed, depending on the nature of the support, depending on the active metal, depending on the dispersion and planes, crystalline planes on nickel. So usually in the literature is reported the formation of carbon nanofiber, of carbon graphite, or amorphous carbon. Among such type of carbon, the nanofiber, also known as whiskers carbon, are practically the most dangerous because nickel is disattached from the surface, is trapped into the whisker, and then the catalyst gets deactivated. In the literature, it is also reported a positive effect when nickel is supported over a ceria-based oxide or a zirconia doped by ceria. So, for instance, it is reported that in the case of nickel zirconia, the amount of carbon that is formed is around 1,000 times more than in the case of nickel supported over a support containing ceria that is a well-known oxygen storage support. The optimization of nickel catalysts for dry reforming on methane are based especially on several factors that take into account the ensemble size effect, eventually the presence of ligand effect that can modulate the dispersion of nickel, and also the strain effect. Moreover, the design of bimetallic alloy catalysts has been considered as a very good strategy in order to improve the catalyst activity and stability. So one of the papers that I have published in my research group was dealing with the bimetallic and trimetallic nickel catalysts deposited over alumina and alumina doped by ceria or magnesium oxide. And one of the aim of the research was the doping of nickel only for 8% with a very, very few amount of gold or platinum, or both platinum and gold. These catalysts, when investigated by TPR, temperature programmed reduction under nitrogen, that give us the possibility to investigate the extent of the interaction between the reducible species over the catalyst. From the TPR, by comparing the reduction profile of the monometallic nickel with the bi and trimetallic catalyst, we observed that the trimetallic was characterized by the so-called beta peak, that with a shape totally different with respect to the other catalysts. And on the contrary, with the nickel that shows a peak at very high temperature due to the reduction of small nickel oxide particles strongly interacting with the support. In that case, we observed a main peak that is usually reducible at the temperature of the reaction, and this peak means that there was a very good interaction between the nickel oxide catalyzed by gold and platinum. When we have investigated, these are by X-ray diffraction, these are a typical X-ray diffractogram that were carried out at laboratory scale. So these are only preliminary results, even if already published. In such a case, we observed that looking at the main peak of nickel 1, metallic nickel 111 and nickel 200, we observed with respect to the nickel alumina, we observed a shift or even the disappearance of the peak on nickel, and also the broadening of the peak suggested that there was some alloy formation or some decoration effect. Actually, just this part we are again investigating, and we will analyze by synchrotron radiation such a type of catalyst, because these are very, very promising for our investigation. By looking at the methane dry reforming results in this slide, you can see as the CO2 methane conversion curves increased with respect to the monometallic nickel in the presence of platinum and gold platinum. And also looking at the hydrogen yield, we observed that the hydrogen yield was much better in the case of the bimetallic and trimetallic catalysts. Of course, in such case, we have observed looking at the CO2 and methane conversion curves, we observed, and this is usual, often occurs, that the CO2 conversion was higher than the methane conversion. And usually this occurs due to some side reaction, like the water-gas shift reaction that is very favored in such a reaction condition, or eventually the CO2 dissociation. And also we confirmed our better results also of the trimetallic catalysts, also when we performed the longer run tests for 24 hours. Very interesting was when we investigated by transmission electron microscopy such nickel and nickel-doped catalysts, and just in the case of the nickel gold platinum, we observed a very, very strange carbon nanotube that we called as bamboo-like. In the case of the monometallic nickel of the bimetallic, we observed mainly some amorphous carbon along with some nanotube, much shorter, and then in the case of the trimetallic. So we are investigating just now more in details the effect of doping nickel with the platinum and palladium and the gold, sorry. Also, we observed that the particle size distribution was gives very small particles in the case of the nickel gold platinum, while in the case of the monometallic the distribution was much with particles much bigger. So here just there is the hypothesis that we have to confirm, and this hypothesis of the generation of such carbon nanotube comes from an article, published some years ago. Okay, and it could be that somehow just the geometrical and electronic effect due to the presence of gold and platinum can enhance the mobility of the surface carbon, and probably this favors the formation of some pentagonal rings that give rise to the formation of the bamboo-like nanotubes. Then we have investigated the effect on nickel over alumina modified by ceria or magnesium. It is known that ceria is an oxygen storage oxide, while magnesium it gives some basic properties to the catalyst, then favoring the chemisorption of CO2 and then enhancing the reaction and also the oxidation of the carbon coke. And here we have analyzed by X-ray diffraction our catalysts, and just in the case of the sample that was prepared by Sol-Gel method, we observed some peak due to the formation of cerium aluminate, and according with the literature, such species, such phase should enhance the reaction and also improve the catalytic activity and the coke resistance. So in this slide, we have somehow confirmed the superior behavior of the catalyst doped by Syria and magnesia with respect to the nickel alumina, and just comparing the catalyst prepared one pot by sol gel or by impregnation, we demonstrated that the superior conversion of methane and also of CO2 for the catalyst prepared by impregnation. Then also in this case, we observed that depending on the catalyst, on the support composition, the nature of the different type of carbon species that are formed was a function of the nature of the catalyst. Then I would like to move to one of the most recent results that is related to the synthesis of nickel lanthanum catalyst. In that case, we have prepared the lanthanum by using the citrate method, but we worked simply in two slightly different conditions that demonstrated a very strong impact on the properties of the catalyst. Namely, we have prepared the catalyst starting from lanthanum nitrate, and we have worked in one case in acidic condition, typical of the citric acid. In the other case, we have worked in a basic condition by adding ammonia. So the support was prepared, and after the calcination, we have deposited nickel and we have calcined. In this slide, I have summarized which are the main characteristics that are typical of the two supports prepared in different conditions. So we have deduced from different characterization that the lanthanum oxide prepared at acidic pH actually contain in the core some lanthanum hydroxide, and then in the external part there is some lanthanum oxide and lanthanum carbonate that is formed upon exposure to CO2. While in the case of the sample prepared in basic conditions, we don't have such lanthanum hydroxide, so we have mainly lanthanum oxide. And our explanation is due to that about the presence of lanthanum hydroxide in the core is that probably such lanthanum hydroxide that is formed during the reaction remains like entrapped in the material. Therefore, such two different supports, when impregnated by nickel, give rise to different nickel phase that strongly influence the properties of the catalyst. Indeed, in the case of the nickel lanthanum citrate, we observe the by X-ray diffraction, the formation of big particles of nickel oxide and nickel lanthanum perovskite. While in the case of the support prepared in basic condition, the impregnation nickel give rise to such a perovskite phase that is very well dispersed. Therefore, by X-ray diffraction, we have observed that nickel oxide in the sample prepared by citrate reach dimension up to 8 nanometer, while in the case of the lanthanum prepared in ammonia, the nickel lanthanum nickelite are much more dispersed. Again, we have applied the TPR in order to investigate the different interaction between the reducible nickel species in our support. supports. So in the case of the sample prepared with citric acid, giving rise to very big nickel oxide particles, we observed a strong peak at a relatively low temperature that was deconvoluted in different contribution, and this peak were attributed to the reduction nickel 3 plus to nickel 2 plus, and then nickel 2 plus to nickel 0. On the contrary, in the case of the nickel deposited over the support prepared by ammonia, okay, we observed also this peak that was due to large crystallites. There were anyway some, but the main contribution was at high temperature that was attributed to small crystallites on nickel lanthanum perovskite interacting with the support. Then, after reduction, we confirmed that in the case of the sample prepared at acidic pH, we have the sintering of some metallic nickel, while in the case of the sample prepared with the support prepared in base condition, the nickel metallic was very well dispersed. And we will see that this difference will strongly affect the performance of the catalyst. In this slide, we have reported the high-resolution time images of the catalyst nickel lanthanum prepared in ammonia condition, and in such a case, we have detected particles as small as 1-2 nanometer, and this confirmed the results by X-ray diffraction. And we also confirmed that the precursor of such metallic nanoparticles, very, very small, is the presence of such lanthanum-3 nickel-2O6 phase. On the contrary, in the case of nickel that was deposited of the support prepared in basin condition, nickel aggregate around 20-30 nanometer were formed, and also some metallic nickel particles up to 10 nanometer were formed too. Then we have investigated by methane decomposition before to perform the methane dry reforming the two catalysts, and we observed here we carried out the test of decomposition, and we observed that in the case of the support A, nickel lanthanum by citric acid, we observed a very important decrease of methane, along with the very important production of hydrogen. The behavior was a bit different and less pronounced in the case of the other catalysts. And how to explain this difference? When we carried out the reaction only with methane, we confirmed that in this case, the catalyst containing metallic nickel up to 20-30 nanometer was very active towards the methane activation and decomposition. But this was not so good, because a catalyst for dry reforming should activate the both methane and the CO2. So in that case, we observed by time very important coking poisoning. In this slide, we have analyzed by X-ray diffraction the catalysts after methane decomposition. We observed a very important metallic nickel sintering, and also here we have analyzed by time. We see that in both cases we observed some filamentous carbon. However, there is a very, very important difference. Look, in the case of this catalyst, catalyst, some nickel was detached from the surface, and this caused some catalyst deactivation. While in such a case, we observed some channels of carbon fibers here without any nickel encapsulation. And finally, when we performed the long run tests in the methane dry reforming at 650, we observed, and we were surprised at the beginning, we observed that only after 4 hours the conversion curve will get stable. In the first 4 hours, we observed a lower activity, so methane and CO2 conversion and also hydrogen yield in the case of the catalyst prepared in presence of ammonia. And this was to the fact that the metallic nickel particles at the beginning were very, very small, so only after 4 hours they get activated. On the contrary, the catalyst, this one, get deactivated during the reaction. Okay, and finally, when we performed the 10 high resolution image, we confirmed that in that case, we formed very, very big nickel particles, really sintered. The amount of carbon was much less in the case of the catalyst prepared in presence of ammonia. And also, this was confirmed by TGA. So here I have summarized the main remarks about the effect of platinum and gold on the structural and reduction properties. Also in the effect in the trimetallic of possible grain boundaries effect that we are confirmed with the synchrotron experiment that was now approved. And then the important effect of the support. Here is my research team and the people collaborating to the research. I would like also to remember shortly that this year the CNR celebrated the centenary, so was founded in 1923, and this is a very important year for us. We are in Palermo, and these are the main research field that we carry out. Thank you very much for your attention.
Thank you, Leonarda, for this nice presentation. We are ready to take some questions. I have one. I could understood the formation of the bamboo-like carbon tubes on the triple metallic catalyst, but how can you, you can comment on the formation of those carbon nanotubes on the material that you prepare on ceria and alumina by impregnation as compared with the sol gel?
Yeah, the question is that in the literature there are several mechanisms occurring in order to explain the formation of different type of carbon deposit that can be amorphous, that can be more or less crystalline, that can be bamboo-like. This is really our first finding for this type of catalyst in the condition of the methane dry reforming. The question is the nature of the carbon, depends also on the metal support interaction between the nickel particle size and the support. Also, we noticed that also in the case of alumina doped by magnesium or ceria, also in that case, if even the CO2 activation should be favored, but also in that case we observed such different species of carbon. The difference is that when we performed the very long rounds, we observed that finally the amount of the carbon deposited over the doped catalyst, doped in terms of a second or third metal, or doped in terms of the alumina modified or lantania, we observed that yes, such amount was much less, and also we were able to regenerate easily the catalyst. In the case of the three metallic, the nickel, platinum, palladium, such bamboo-like entrapped some nickel particles, because it's true, and such bamboo-like grown only over the nickel sites. But we would like to investigate some more the process, and for that we have again prepared the catalyst, and we obtained some time for experiment at the synchrotron we will perform in Grenoble in the next months, and also high resolution time and not only transmission electron microscopy simply, in order to investigate the effect of the second and third metal on the defective structure of platinum, and eventually on the growth of different plants, crystalline plants.
Thank you very much. I have another question. Please, Gabriela.
Hello. Yeah, the interaction, we would like to go deeper in the investigation, because from the preliminary experiments, it seems that some alloy formation occurs between nickel, gold, and platinum. However, we have prepared a catalyst that contains 4 weight% of nickel, and we added only 0.2 weight% of platinum or gold or both. So if we consider the molar ratio, the ratio is not exactly 1:1, absolutely not. So some alloy or dispersion on nickel occurs, and also the nickel was much more reducible in presence of such second, third metal. So our hypothesis is mainly not only an electronic but also some geometrical effect. It seems that we are really able to tailor the nanoparticles growth and then the position of the second and the third metal. And the moment since we obtained this time for experiment at the synchrotron, we plan also to investigate the reduction process, so of the nickel in presence of the hydrogen or methane, just to have some more information about the possibility to activate the both molecules, methane and CO2, and also if it is possible to limit the carbon deposition.
Thank you. Thank you once again to Leonarda for this very interesting presentation. So it's my pleasure to introduce the next speaker, Carmen Chotonea. So she obtained her PhD from University of Poitiers and Technical University of from Iași in July 2015. The PhD research was focused on development of materials based on non-metal with control of the metal. With the metal like nickel, copper, and cobalt, with the control of metal nanoparticle size. Currently, she is working as assistant professor at Engineering School Littoral Côte d'Opale, and she is developing the research at Unit of Environmental Chemistry and Interaction with Living Organisms within Catalytic Treatment and Clean Energy team. Her research is focused on development of advanced nanostructured materials with accurate control of nanoparticle size and localization, various functionalization of material surface, and advanced characterization. So, Carmen, please.
So thank you for your introduction. Well, as you may expect it, this presentation was supposed to be done by Sebastian, which unfortunately cannot be today with us. So I want to thank the organizer to accept to present in his place. So he was choosing a topic on supported transition metal catalyst with controlled dispersion as active and stable catalyst and selective catalyst for energy-related reaction. So first of all, I'm not sure that you are knowing the theme of Sebastian. So Sebastian is working in MatCat team. He's the responsible, and also is the responsible of AppCat platform. Is the place where I used to work in the past 10 years. So that's why I kind of know the topics on which he is working with. So as the name is saying, in MatCat team, we are, I was supposed to work on the development of catalyst with solvent-free synthesis by using most of the time biosource templates, catalyst based on, I'm trying to find a pointer. It's not this one, wait. Oh, here. So based on transition metal elements, so metal oxide on metals. So as iron, copper, manganese, cobalt, nickel, etc. Also, a special interest is focused on the upscaling of such synthesis and also of shaping. So that's why there are a lot of equipment in order to transfer the lab scale synthesis of the catalyst to the large scale, so in 20 liters autoclaves reactors and so on, and also to do the shaping of these solids, followed by the characterization either in the powder form and then in the objects that we are preparing. So now I'm working in a catalytic treatment and clean energy team from USEV. I joined this team as a specialist in material preparation and characterization. So in this team, we are working on the catalytic treatment and purification of several air pollutants and also energy recovery, mainly by valorization of CO2, either by methanation and reforming. So some of the facilities that are present in Chevron Institute and at the University of Lille. So of course, techniques for the characterization of the morphological and chemistry properties of the materials that we are preparing. Also surface analysis, NAP-XPS that was installed a few months ago is not functional, but we are hoping to use it very soon. And also access to Synchrotron Soleil in Paris. So we were using air beamline and rock beamline for the characterization of either in situ during the preparation of the catalyst or in operando during some catalytic test. So by the materials, catalytic materials that are prepared within MatCat group are the bulk catalyst. So bulk catalyst based on perovskite, hexaluminates, single oxide, mixed oxides. And the focus is mostly on using free solvent synthesis because we don't want to have low surface catalyst. So that's why we are using strategies as high energy ball milling and low energy ball milling in order to increase the surface area. And also we are trying to use strategies that are allowing us to do the upscaling. So I'll kindly invite you to visit the site. You will find there a lot of machines that allow us to do the upscaling and also the shaping. So here you have some example of synthesis that we were preparing on UpCat platform. So the SBA 15. So it's interesting that during my very first days of PhD, I started to do the SBA 15. So I was starting by preparing 2 grams of SBA 15. Few months ago, I was preparing by using the reactors 500 grams of SBA 15. It's more than I used during my whole thesis. So once the SBA 15 is prepared, it's keeping all the properties from the lab scale. And also we are interested in doing the shaping. So here you have the example of extrudes. Then also MOF type materials used either for the adsorption or transformed to be used for the catalysis. Now here you have the H-cast. Well, this synthesis was prepared in 3-liter reactor, then was also prepared in 10-liter reactor. So it's working very good. In this synthesis, we were trying to manage to have nanoparticles of H-cast. And also, we were doing the shaping, either in extrudes or spheres, and the main focus was to keep the specific surface area, which is quite high for the MOF type materials, after we are doing the shaping. So it was a success also in this case. And here you have the preparation of a catalyst, so the direct deposition of silver metal onto alumina extrudes. So here you have the example of the extrude shapes, but also at the platform there are machine which allows the preparation, the shaping of the lab scale obtained powder into granules, into objects by 3D printing, freeze casting, or spray drying. So the main focus in these studies, when we are hope with success, to do the upscaling and also the shaping, is to maintain all the chemical and morphological properties for the final objects. So we want to obtain the same thing as we were obtaining at the lab scale. So now we are going into the topic of this talk. So the supported catalysts that we are preparing, as I said at the beginning, they are based on transition metals. So today I will just talk about the use of SBA 15 as the support. So we are doing this also on mesoporous alumina, on mesoporous carbon, or other hybrid supports. So here you have the example of 10% nickel on SBA 15, for which one we managed to control the particle size from 9 to 1 nanometer, and also to control the localization. So to be confined, to be stabilized either within mesoporous or within micropores. So all of these syntheses are very reproducible, and also were prepared in a scale of a few hundred of grams. So even the 1 nanometer catalyst. So once we managed to stabilize with control size and control localization the monometallic catalyst, so we were going further because we know that in catalysis the synergy between 2 elements is important. So here we prepared materials with copper and cobalt with control shape. So you have the example of confined, full particle, hollow sphere, and thin shell. Then when you are working with catalyst, you know that the addition of some acid base is important for the catalyst. So in these examples, we were adding zirconia and iron on the support, and then we were preparing highly dispersed and small nanoparticles of nickel. So it was a success in both cases. As for the support of pure SBA 15, of bare SBA 15, we managed to obtain around 1 nanometer of nickel for the zirconia and iron SBA 15. So most of the time when you are preparing materials, you are focused in obtaining a fancy and nice results and beautiful results. in what you were planning to do. But when you are preparing catalytic materials, some beautiful materials are not working good as a catalyst. And it was, for example, the cobalt. We managed to obtain very small cobalt nanoparticle, but were not active because we had to reduce it at 900 degrees C. And when you reduce it at 900 degrees C, you have 40 nanometer of metallic cobalt. So it was not interesting for catalysis. So that's why when we are preparing the catalytic materials, we are in contact with our colleagues doing the catalysis, and we are asking them, what exactly do you need for a catalyst to be good in your reaction? And it's exactly what we are doing. So actually, we are combining different preparation methods in order to get, I'll say now, the perfect catalyst for an application. So we are combining conventional procedures. So here you have the example of incipient wetness impregnation and wet impregnation. So by far, impregnation is one of the most used preparation method for the catalyst. So even though it's well known and highly intensively used, so we manage to control the impregnation and the drying. I'm having two videos to show for you. So here you have the example of wet impregnation. So you see that the particles are grouped in patches, in large patches. They are still 9 nanometers, but they are not all accessible for the catalysis. And here you have the preparation by incipient wetness impregnation. So the same 9 nanometers nanoparticles, but this time the particles are well dispersed onto the support. And this only by controlling the impregnation step and following by the drying step. So another method that it's less used for the preparation of catalyst, it's by melt infiltration. So this method is not using any solvent. It's adaptable to a wide variety of supports and also of transition metals to be deposited onto the support, and also allow us to work either with calcine or S-made supports for SBA, for alumina, or other supports. So this method has to have a precise and accurate control of the diffusion. You will see the results now. And it's allowing us to go into mesoporous dispersed nanoparticles of about 9 nanometer. So we are considering these large nanoparticles. And also to go into a very small micropore confined nanoparticles. So here you have the results for nickel again, of melt infiltration realized without any diffusion. So as you can see, all the nickel oxide is outside the support. And then we are doing the diffusion up to 4 days. So if for zeolites, you want to see very intense and beautiful peaks, in my case, I don't want to see any peak. I want to see something very ugly and very broad, because this will indicate me that I'm having highly dispersed nanoparticles. Another method that it's used for the preparation of the catalyst, that we were using for the preparation of the catalyst, is by deposition precipitation. And this is due to the fact that we are using higher amount than for impregnation. Meaning for the impregnation, you are limited by the pore volume. In this case, you can go at higher than 25% amount of loading on your support. And also, the tricky thing is that we are using SBA15 and not the classical commercial silica support. So the SBA15 use the silica source will aim to the formation of the phyllosilicates. And the phyllosilicates are looking like these filaments. And we are using these precursors to be activated under hydrogen in order to get the metallic nanoparticles. And even for 40% nickel loaded onto SBA15, we reach to have 3 or 4 nanometer in size. And also a very good dispersion. So For the phyllosilicates, you can either prepare 1-1, meaning you have 1T, 1O layers, and you can prepare also 2-1, meaning that you have 1T layer, 1O, and 1T layer. Well, now let's go into some catalysis. So Power 2X strategy, it's an important component for the decarbonation. So Power 2X strategy, it's storing the energy into some key molecules. So here you have the example of syngas, the example of biofuels, the example of methane, and ammonia. So we will take the examples one by one, and we will see what exactly we will obtain when we will use supported catalyst. So first of all, dry reforming of methane. So we just had a talk on the dry reforming of methane. I will not go into the details. So here the challenge is to have a catalyst able to activate this reaction at low temperature, to be stable in high temperature, because for the dry reforming of methane you need at least 700 degrees C, and to be active, of course. All the time we want activity in catalysis. So in this study, we choose to use deposition precipitation, and this because we want to incorporate up to 40% of nickel. So you prepare the phyllosilicates, you reduce it, and you obtain the nickel nanoparticles. The phyllosilicates are well prepared, as the XRD is showing, and we don't have any nickel oxide. So I said that the tricky part in DP is because we choose to use SBA15 as silica source. And here is why, because looking at the textural properties, by using the SBA15, you retain up to 360 meters square per gram. It's quite a lot. Of course, we will destroy the order structure of the SBA15, but we get our phyllosilicates. And as I said before, the phyllosilicates are the filaments that are present all over the silica. Normally, when you are doing 40%, you are nickel onto silica, you are supposed, or you are in the same condition to prepare 2-1 phyllosilicate. And we were testing this. We prepare one material by hydrothermal, classical hydrothermal treatment. And here you have the reduction temperature obtained by TPR. So for sure, all our materials, including 40%, had just 1-1 phyllosilicate. The reduction is showing the presence of small nanoparticles. And then the catalytic results in dry reforming of methane is showing that when we are using the small nanoparticles, we are having limited carbon accumulation. And also, the images recovered after the catalytic test don't show the formation of the carbon, which was supposed to be in our reaction condition. So when we are working with dry reforming of methane, we know that the carbon, it's very selective, but it's not active. So then we said, okay, let's see if we are adding some cobalt into the formulation of the phyllosilicates. We will improve the activity and the selectivity in dry reforming of methane. So we did different formulation with ratios, with different ratios of nickel and cobalt, still keeping 20% of total amount of metal. And I have to say that when you are preparing cobalt phyllosilicate, you will obtain only 2-1 phyllosilicate. And when you are preparing the nickel phyllosilicate, so we saw you are obtaining just 1-1 phyllosilicate. So we were wondering if we are in the case of pure cobalt phyllosilicate. And it was surprising to see that we reduce a lot the reduction temperature when we are incorporating 50% of cobalt within the phyllosilicate. So these materials are showing a small nanoparticle size after the activation under hydrogen. Then we wanted to go more into detail for this material, and we were doing the in situ XPS. So after 700 degrees C, we don't have any phyllosilicate phases. We transform everything in metal. And it was interesting to observe that on the surface, we are having enriched nickel. And we wanted to know what's happening for each particle. So that's why we do TEM yields mapping, so on single particle. And we observe that for single particle, we are having 65% atomic percent of nickel and 34% of cobalt. So here you have the result in dry reforming for 12 hours. So the first result, it was for 5 hours. So after 12 hours, we obtain a few carbon. And by ATG showing us that it's about 3%. Then we used the nickel cobalt catalyst for 200 hours. So if you are working in dry reforming, you know that 8 continuous days of reaction, it's quite a lot. So we observe that we are having stable activity. We are not having any important sintering, but we have some carbon nanotubes. If you are working in materials, carbon nanotubes are nice, but for us, when we are seeing, it's not beautiful at all. We don't want to have it there. By ATG, we obtain 29% of carbon accumulation. It seems that it's a lot, but actually, after 200 hours of dry reforming, 29% is nothing. Well, that's it about dry reforming. Now we will talk a little bit about hydrodeoxygenation of bio-oil obtained from lignin pyrolysis. So lignin pyrolysis, it's used in order to valorize this part of the biomass. By the pyrolysis, we will obtain an oil with a complex composition, which is looking like this, with the composition which is actually similar as the oil. And by hydrodeoxygenation, we are focusing on metacresol and anisole molecules to be deoxidated and dehydrogenated in order to increase the specific heat, so to get more valuable biofuels. So in this study, we were proposing to use particles with 3 different sites. So by the methods that we are managing to use, we choose to have melt infiltration within the micropores, deposition precipitation to get that 3.5 nanometer, and melt infiltration into the mesopores to get the 9 nanometers. And the microscopy are showing that we successfully obtain these 3 sizes of nanoparticles. Then we use it on the dehydrogenation of metacresol, and it's interesting to find out that small nanoparticles are showing very good selectivity to toluene. We wanted to know what's happening for these small nanoparticles because was few investigated before in this reaction. So the DFT studies show us that larger the particle there are, we will concentrate the atoms on the terrace type, and we will favor the hydrogenolysis and the hydrogenation route. When the smaller particles are present, so we will have higher concentration of the atoms on edges and on corners. So this will make us favoring the direct deoxygenation route. So this is showing us that metacresol hydrodeoxygenation, it's a reaction that it's structure sensitive when we are working with nickel. So I told you that when I'm preparing a catalyst, I want to talk before with the person doing the catalysis, and I want to know what exactly it's expecting from a catalyst. So talking with my colleague Camila, which is doing the hydrodeoxygenation reaction, she told me if you can put some oxophilicity on some zirconia, it will help us to have better results. So it was what I did. I add just few zirconia onto the SBA 15, and I prepare by the same melt infiltration the catalyst. So we obtain smaller nanoparticles in both cases, with or without the zirconia. So the TPR results show us that we have a little bit of larger nanoparticles. I will use the term larger because actually they are 5 nanometer. They are not quite large. And these materials, again, were used in the hydrodeoxygenation, this time of anisole. And the reaction, it's showing us, the results are showing us that we have methane selectivity and also benzene selectivity when zirconia is adding by comparison with the monometallic nickel on SBA 15. So we are still waiting for the DFT results in this case. So unfortunately, I cannot present it for you today. And we will go further to the CO2 reduction. So the hydrogenation of the CO2, it's allowing us to obtain the methane. This reaction is highly exothermic, and like most of all the application of the catalyst in temperature, we will have sintering and coke formation. So again, the challenge is to find a catalyst which is stable. So in this study, we propose to use different nickel dispersion in order to improve the stability and the activity on the CO2 reduction. So we propose to prepare catalyst by classical impregnation. So here is the wet impregnation on commercial silica. We use also our reference, so incipient wetness impregnation to obtain 9 nanometer nanoparticle. And finally, our preferred, it's nickel with 1 nanometer. So indeed, the results are showing that we are obtaining what we were proposing, and the catalysis, it's showing that at T50, we have a significant improvement for the small nanoparticles. So we have about 270 degrees C for 1 nanometer, and here we are at about 350 degrees C. So this reaction shows us that we have a significant effect for the T50, but we don't have any selectivity for the CO2 reduction. Nevertheless, the materials recovered after the catalytic test show us that we are having limited carbon formation around the particles. So the materials are quite stable. Okay, and it's coming to an end. Finally, the ammonia synthesis. Well, the ammonia synthesis is produced in industry by using Haber-Bosch process. It's a process using high temperature and pressure. So it's a challenge between thermodynamics and kinetic. It's a compromise between the thermodynamic and the kinetic. In industry, they are using iron-based catalyst. The results are not quite extraordinary, and it's using a very high energy in order to produce this transformation. So here I show you the mechanism prepared by my colleague Amanda. Oh, sorry, I went too far. So in this reaction, the Langmuir-Hinshold mechanism is used. So in this study, we compare the nitride catalyst. This because the nitride catalysts are important candidates for the ammonia production. And working with bulk catalyst, we have to know that we are having limited access of the nitrogen, and we are having low surface area. So how are working the nitride in the ammonia synthesis? So the nitrogen atom from the nitride will be the reactant. We will create a vacancy in the nitride, and then this is regenerated by the nitrogen. Working with supported catalyst, all the time you are trying to do supported catalyst with all the elements. So we try to do the same thing with COMO and molybdenum, of course, nitrides. So how exactly we did? Firstly, we prepare COMO oxide dispersed on SBA 15. Then we did a treatment in order to transform it into the nitride. So here you have the results for the bulk common nitride and for the supported common nitride onto the SBA15. And we did some XPS in order to prove that we are having successfully obtained the common nitride. And indeed, most of the intermetallic nature of the COMO was within nitride. Then we did the catalysis. So the ammonia synthesis show us that we are having a lot of difference in the production of COMO nitride bulk and supported COMO nitride. And by comparing this one with monometallic molybdenum, so you see the improvement of the second element, so the synergy by adding the cobalt within the structure of the nitride. Finally, in order to explain these results, we did the test under hydrogen, and this allows us to conclude that when we are using the COMO nitride within the SBA15, we have full accessibility of the nitrogen, comparing with only 50% when we are using the COMO nitride. And finally, the acknowledgements. All of these results were not been possible without the help of my colleagues, of the personnel doing some characterization, and also the funding of different institutions from France or from Europe. So thank you for your attention. If you are not too hungry, we can discuss a little bit. So I'm waiting your question. Thank you.
The floor is now open for discussion. If you have any questions, please.
So I didn't present in detail the mechanism of formation of phyllosilicates here, which was proposed by Boratin in '98. So when you are using the SBA15, you will either absorb the hexacation of nickel onto the surface of the silica. Either you will form the acid silicon like outside in the solution, and like this you will form filaments apart from the silica. So of course you will have more filaments around the SBA15. You will have some filaments within the pores because they are mesopores, so they are quite large, and you will have filaments apart. But for sure we are not obtaining nickel or cobalt outside the support, or even copper. Well, the inside particles are because the filaments were inside of the SBA15. So actually you are just sintering from the filaments when you are doing the reduction.
Thank you. Let's thanks again Carmen and all the speakers for this session. We will continue the discussion during the lunchtime. I have two or maybe three announcements. So Christina is waiting for you in the main hall for the one that wants to learn more about this building. So it's a tour that will take 10 minutes if you are not too hungry. The second one is that at the reception there is a list, a table where you have to sign. We didn't prepare it in the morning because we were in a rush. So please go to the reception and sign that table, administrative things. And the third one, after the lunchtime, I will wait for you here to make a photo, to take a picture. There is a joke in Romania about this. So okay, so please, Christina is waiting for you, and we can enjoy the lunch in the main hall. Yeah, it's a politician that said every time I talk about we are joking.
can start. So I'm very honored and very pleased to introduce Professor Michel Barsou, who is a distinguished professor in the Department of Material Science and Engineering at Drexel University. He is an internationally recognized leader in the area of max phases and more recently to this is labeled MX scenes, which are derived from max phases. Most recently, he also discovered a new universal mechanism, reblocation, in the deformation of layer solids. He is on the Web of Science highly cited researcher list in 2018-2020. He is a foreign member of Royal Swedish Society of Engineering Science and a fellow of the American Ceramic Society and the World Academy of Ceramics. In 2020, he was awarded the International Ceramic Prize for Basic Science by the World Academy of Ceramics. This prize is awarded quadrennially. I don't know if every 4 years, and is one of the highest in his field. The prize was awarded for outstanding contribution in opening new horizons in material research, and specifically for his pioneering work in max phases and their derivatives. And today we are hoping to see some new materials. Michel, you have 30 minutes of good program.
Do I really need the mic? All right, we'll try it. Why not try it without and tell me if you can hear me. Okay. Yeah. Thank you, Florentina, for this kind words. So what I want to talk to you today is something new that maybe it's a year and a half or 2 years old. And so I'm from Drexel University in Philadelphia, right across the street from Penn. This work was funded by DMR, Murata Corporation, and the Army. And I want to acknowledge the funding. And of course, the organizing committee and Mihaela, Stefan, and Florentina. Can't thank you enough, not just for organizing this great meeting, but also especially for your hospitality. Really is outstanding. Yes, okay, so let's just give you a little background. In 1996, we discovered what I labeled the max phases, and they're layered hexagonal transition metal carbides and nitrides, where M is an early transition metal, A is an A group element, and X is either carbon and or nitrogen, and they come in many flavors. N is 1, you get 2 layers, N is 2, you get 3 layers, N is 3, you get 4 layers, and they're laminated at the atomic scale. And here is the periodic table. So Hans Nowotny in Vienna in the 60s discovered the following. There were about 50, discovered these. Then only one of these, and then these have come later. We were the first ones to make the prototype of the 413. Anyway, so what is really very, very unique as a ceramic, so this is titanium silicon carbide. You can machine it with a manual hacksaw. You can throw it in water from 1350 degrees C, it doesn't crack. And it has they have very interesting combination of metal and ceramic, somewhere in between. So we've had a lot of fun with these materials over the years. The original set is 50. Today there's over 200 max phases. So, if I told you this was a picture of wood, you'd say, yeah. And this is one of my favorites. So this is a titanium silicon carbide large crystal that deformed, and it did this. Now, you don't associate that with silicon carbide or titanium carbide, but this was actually titanium silicon carbide. And for the longest time, we assumed that, like everybody else, that basal dislocations were playing a role, and it's not. So this new concept called replication, think of ripple and interrogate, that's what we have. I don't have time to talk about them, but I'd really like these micrographs. This was published in 2013, and the second edition of my textbook came out in 2020. So it's a very good textbook. Everybody should have about 2 copies. Or you can download it for free from the internet. All right, so then in 2011, Michael Naguib, who was my PhD student, did the following. He took titanium aluminum carbide, put it in HF for 2 hours at room temperature, and we went from 3D to 2D through the magic of chemistry. And this paper, well, it was the first publication was in 2011, and it was published in Advanced Materials. Okay, so how does MXene come from? So you all know now what the max phase is, and so once we get rid of the A layer, you get rid of the A, and then you put E and E to make the connection to graphene and other 2D materials. MXenes have absolutely exploded. So this is up to 2022. This is the number of papers a year. It's up to 5,000 now a year. And in all kinds of fields. Again, the numbers are pretty good. And they're being used in just about everything. The only thing they can't do, unfortunately, is grow hair. So anyway, all right, so let's come to the main event and hydroxide-derived nanomaterials. So these pictures were taken by my postdoc, Greg, and they were artistically rendered by Patricia Lyons, who also happens to be my wife. And so I'm going to show you some pictures, and I won't comment on them. The only thing I'm going to say about that is they certainly look organic. Okay, so what are these? Well, before I start, just want to make sure that, titanium has been worked on for a very long time. It's a fantastic material. There's thousands of papers on it. Again, one of the largest products is TiO2 pigment for paint, etc. And so I don't have the time to go through the review of the literature because I want to show you some new stuff. So Saint Badru, who was at the time funded by Murata Corporation. Murata Corporation is this huge private Japanese company that makes 3 billion capacitors a day. 3 billion a day. All right, they make 1 trillion a year. So we found a paper in the literature that says if you take them, what they wanted, and they still want, so if you find the solution, let me know, they want to do this without HF. For obvious reasons. So we found a paper in literature that says if you take a max phase, put in HF for a short time, and then you put it in TMAH, you get MXene. We heard about TMAH a few times earlier today. So the question is, what if we did this without the HF step? So we did, and we got this. And we were very excited because now we can make MXene without HF. But they were not very conductive. MXenes are metallic, the first sort of metallic 2D material known. These were not very conductive, and the titanium ratio is just low. So, and we didn't get the signature peak in XPS. So then we sat on this for about a year, and then one day I asked Hussein to throw these in separately in TMAH and tell me what happens. By the way, this is TMA, and it's a very simple molecule. Most of you know. So the process cannot be simpler. Okay, we take a plastic bottle, we put our precursor, 25 weight percent TMH, in a polyethylene bottle on a beaker, on a hot plate, and we do that, depending on temperature and time, but something of the order of 3 days at 80 degrees C. Then we bring down the pH by washing with ethanol, and then we wash with lithium chloride to get rid of the TMA. And what we end up with beautiful 2D filtered films, as you can see here. And what's really fascinating is every titanium-containing material we throw in there converts to these one-dimensional lepidocrosite, except for TiO2. Okay, so it's a form of oxidation. So this is the first time you do, 1D material starting basically with rock salt structures. And here are the films. Like I said, if you start with TiO2, it transforms into nanoparticles, which is interesting in its own right. But we were not interested in the TiO2 nanoparticles. Again, these quartz. Oops, sorry. Yeah, it's almost like the universal solvent. And just as an aside, so for a while we were calling them quad-derived nanomaterials, and then now we know that all we need is just a high pH. We can do it with sodium chloride, sodium hydroxide with hydroxide. Anyway, so we started looking at them, and here is a classic XRD diffraction of anatase. And these are two different batches. And now what I superimpose, I reproduce this, and the X-ray diffraction signature of our 1DL is the absence of 104 and the 105 peaks. So as I'll show you as we go along, you'll get a very big peak here because of the nanofilaments self-assemble, and then you have the 25 and the 48 and the 62. And here we go again. This is a typo. This should be 010, and then we get the 25, just like an anatase, and we get the 48, and then also the 60. And this is the Raman spectroscopy of it, and it's clearly anatase, 152, no doubt. Okay, and again, doesn't matter what you start with, you will get anatase, or so we thought. That's more interesting. So this published in Materials Today. It was a very large effort with a lot of people, most of them in Europe. And then we sent Daniel, a collaborator of mine. He said, "Why don't you send me some material? I'll look at them." So we sent them, and he found this, and he sends me an email. He said, "I don't know what you guys are smoking in Philadelphia, but this is not anatase, it's lepidocrosite." So, we were puzzled for a couple of days, and then Daniel calls me again. He says, "I figured it out. Actually, by putting the laser on the material, actually transforms from lepidocrosite to anatase." So, Houston, we have a big problem because now we have a high visibility paper where the word anatase is in title, and it's not anatase. Minor little detail. This is Murphy at a very high level. All right. So anyway, this is now DFT work that we did with my colleague, and so this is what we think we have, and I'll show you evidence in a minute. And so we get these very thin filaments that are roughly 5 angstroms in thickness, and they stack along the B direction. Yeah, so this is correct. 010, 020, 4050, etc. And again, these peaks are crystallographic. These peaks will not change positions. These peaks, you can move them like you do in a 2D material. Maxines, you can make them larger, smaller. Right, okay. And so, and this is now, this is the paper that came out, in January to correct the first one. This beautiful picture, TM picture. This is with folks in University of Illinois Chicago. I'll have the names in a second. And what you see here, this is a TME material, and what you see here are these beautiful little individual chains, if you will. And we got the fast Fourier transform. We used our DFT, and we get very good agreement between DFT and theory, or DFT and experiment. The only variable we allowed here is just a distance between two layers. And here's a higher, with Francisco and Robert Clay. And you can see here, this is the signature of this nanofilament. You see these are atoms, and so what you see are individual atoms. So if you now look at it from the edge on, so it's going in, it grows in the 10 direction into the page, and it stacks. Oops, yeah, and it stacks along the B, and the cross section is roughly 5 by 7 inches. So in January of this year, we corrected our mistake. Okay. So now you have this, what I call spaghetti. And this spaghetti, as I'll show you in a few minutes, or I'll show you, it just self-assembles in all kinds of different ways, depending on the solvent, depending on which solvent, whether you use water, or ethanol, etc. So here's a freeze-dried colloid. Oh, by the way, so when we wash all the stuff and we get pH 37 and then we put water, zero potential, it's minus 50 to minus 60, so they're very stable. Anyway, so if you just freeze dry them, you get this, I don't know what you call it, but it looks like a lot of paper, little, maybe that's the stuff you get after you shred a document. And however, if you take the colloid and filter it, you get what really looks like 2D materials. Again, this is a higher magnification of the freeze dried, and again, these 2D flakes are not 2D, 1D self-assembled, and this is another example. It's sort of fascinating material. Now, the hierarchical stages are pretty high, right? Because first you have to make this one multi layers, and you make a bundle, and then the bundles form microfilaments, and then the microfilaments self-oriented all kinds of different pathologies. If you want the classic plate of spaghetti is right here. You just take a drop of the stuff and drop cast it on a substrate, and you get spaghetti. And within the spaghetti, in some places you can see there's some order, and the rest is pretty amorphous. And the values we get from the selected air diffraction line up perfectly with the ones we see in XRD. So we're pretty confident that we understand this. Here's another nice example. So this area is completely amorphous. This area, you can see something coming out of the mist. So we also see arcs in the TM. Again, really the one-dimensionality of the material. Okay, AFM, the thinnest we got is about 15 angstroms. So we think that they're so lower than that, but at the very least they're 16 or 15. And then depending on how you make them, you can also, if you cook them for a very long time, you get nanoparticles. And now what's fascinating, if you take these nanoparticles and dilute them very heavily, you end up with 1DL. We'll go back. Okay, now what if you don't want to wash in water? So you wash in alcohol, and then you just let the alcohol evaporate. You get this fantastic mesoparticle that is just, this is what I was showing you at the very beginning. Again, this is completely, we don't do anything. Just let it dry, and this is what we get. So, we have this, I think this is significant because now we have a free-flowing powder that comes out. So the problem with nanomaterials is, you make them nano and then they aggregate, and then you have to work a lot harder to make disaggregate them. This is almost like you have your cake and eat it too. And we can ion exchange the lithium, so this is lithium chloride, and here are the peaks. So the K0 peaks, as I mentioned, they are a function of the distance between the filaments, and that is a function of the cation between the filaments, and these are negatively charged entities. We did some Zanes in Grenoble, and we convinced ourselves that titanium oxidation state between 3 and 4. We also did some EPR work here where we confirmed EPR. I'm going to pass on this. So if you take this material and you do TGA, you lose about, I don't know, 10%. And this is the mass spec. So around 150, you lose most of the water. And then the second step, which is about 4%, you lose another different water. We think this is maybe some water associated with the cations, but and then only after 400 degrees C do you get CO2, and not much. What was one of the biggest surprises was that the band gap is about 4.1. Now, in P25 in titania, 3.2 is the number everybody gets. However, if you take a 3D material and you exfoliate it and you make 2D sheets of lepidocrosite, the band gap goes up to 3.7 because of quantum confinement. And then if you go now by 5 by 7, you now go to 4 eV. So this is, as far as I know, a record for titanium. And it's an indirect band gap, and we believe it's due to quantum confinement 1D. Here showing the same thing. Doesn't matter what you do, you're always going to get around 4 eV. Okay, so what can you use this for? Well, the first thing is a lithium-ion battery. This is with Michael Naguib, who is now in Tulane. He's the guy who discovered vaccines. So we showed, you know, they're respectable. They're not going to break any records, but it works. Lithium sulfur, same thing. These numbers are pretty good. I mean, around 1,000 milliamp hour gram per hour per gram. And of course, I'm only showing you 300 cycle numbers because cycle number 301, it crashed. That's one bad thing about sulfur, lithium sulfur batteries. We can make composites out of them. As you can see here, so this would be the original material, the polymer, and when we reinforce it as well. This is now very, very new work on dye degradation. So you start with a dye, in this case, it's like, I forget, it was a crystal violet, huh? Sorry, yeah, you know what I mean? So when you have your suspension, and then as soon as you add the rhodamine, the flakes basically aggregate and form these large visible the naked eye, and you can see here an agglomeration of these flakes. And again, if you zoom in certain areas, you certainly will always see the one dimension to it. So it really, it's almost a gram per gram in terms of absorption. It's a very large number. It's double that of the highest absorption place. And we have, if we take the number, you know, the number of dye molecules that have been absorbed, and you back calculate the surface area, we're getting surfaces of the order of 2,000 meters squared per gram. The theoretical surface area for a 5 nanometer, for a 5 angstrom 2D sheets is around 1,000 meters squared per gram. And that's for the titanium containing material. Okay, I mean, these numbers are usually associated with carbon because it's very light, or SiO2. And then if you shine some light on it, you know, you basically bleach it out. And we decided to really push the system, so we're using a 1-to-1 weight ratio. And again, after you can see here the Tyndall effect, and again, most of it is amorphous, as you can see here. There are some regions look like some ordering, but again, this was a freeze dry. Now comes the real surprise. So, you know, it's a band gap of 4, right? So it's not going to absorb a hell of a lot. So to our surprise, so this is the rhodamine. So we compared it with P25. P25, for those of you who don't know, is the standard everybody compares their work with. So in the UV, if we only use UV, our one-dimensional lepidocrosite is pretty much similar to P25. However, at room temperature, P25 is completely inert, and we are basically destroying the dye. The same thing with crystal violet. Again, in the UV range, P25 does a little better than our material, which is this and this. And in the visible, however, again, P25 is inert, and we are destroying the dye. So why is that? So this paper just got published with a group of Titova and Grimm at WPI, and they basically figured out the electronic structure of this 1DL material, and it's shown here. This is the band gap. They measured B like we did. But now you know where the conduction band and the valence band is. So what's going on with the sensitization, these are the energy levels of the dye, CV or rhodamine. And so now this can absorb in the visible region. Electron goes here, jumps into the conduction band, and then falls into an adsorbed oxygen and forms a free radical oxygen, which then destroys the dye. And this is the best part of the talk. This is work with the three people I mentioned at the very beginning. And this is hydrogen yield under 1 or 2 suns, shown here. 2 suns, you get more than 1 sun. What is remarkable about these results is that they were interrupted by long periods of 1DL in water. And so at the end of the day, basically there were 800 hours in the water. And out of these 800, 250 were under irradiation. And you can see here, there's no change in hydrogen evolution, none. So I believe that these are, in fact, thermodynamically stable in water. And this is water, sorry, I have to be careful. This is water methanol, 20% methanol. In that solution, they are very stable and they continue giving you. So if they're, if they're thermodynamically stable, then we don't need to worry about anything else. Okay, so that basically sums the work on the 1DL. So, so what else can we get to do this stuff? So we started throwing every compound that we have in my lab. Hussein would throw it in, cook it a few days, take it out, X-ray it. And again, 80 degrees C or 85 degrees C, it doesn't matter. Again, you get beautiful colloids, beautiful films. And here again, the precursor is not important. Okay, no matter what you start with, you'll end up with, show you what that is, which is basically bernicite. You end up with MnO2. So again, you notice that the process involves an oxidation step. So if you start with the highest oxidation state, you're not going to get anything. And again, in this case now, we did that also with titanium. You can use any, well, not just any quad, but again, I don't have time, but we've also done it with lithium, sodium hydroxide and lithium. And again, here now this is a classic 2D material. Again, beautiful flakes, highly ordered, as you can see here. Really beautiful XRD. So this is horizontal, and to convince ourselves that we really had bernicite, we X-rayed vertically, and that basically gave us these 2 peaks that are exactly where the peaks of bernicite appear. Again, really, really highly crystalline. This is, I have to say, this is unusual because this is done at room temperature. So I'm going to pass most of this. So at the end of the day, we have MnO2, which is somewhat oxygen deficient, but it's ion exchangeable crystalline. Pass all that. Oh, yeah. So the band gap is exactly what's in the literature for bernicite. Applications include supercapacitors. This was a supercapacitor paper. This is work I did with the colleagues in Linköping. We can make, we have ORR and OER. And again, if you see this was the precursor was MN304, and you can see the precursor is not great. Once you convert it to do 2D, now you get you get very nice OER. If you take FEB and you put in TBH for a couple of days, you convert it to a very fascinating material, which is basically Fe3O4 magnetic nanoparticles that are roughly 20 nanometers. And again, even I can make these in the lab, which is saying a lot. It is almost foolproof. You just put it in, make sure you put a needle in the plastic bottle so it doesn't explode. Off to the races. This paper just got, it's almost accepted, but we make these Fe3O4 nanoparticles, and there's very little Fe2O3, and there's very little anything else. This one's fascinating. So you take silicon, metal, semiconductor, you throw it in TMH, and you get a material that has a surface area of about 570 meters squared per gram, and you can see the particles, again, they're about 10, 20 to 30 nanometers. The most fascinating thing for me, however, is we get a band gap of 5 eV. Does not exist. If you have silicon carbide, it's about 4. If you have silicon, so this is a new animal. The only explanation we have at this point is, and we have some evidence for it in XPS, that we are now incorporating some carbon into. Most importantly, we 2 years, a year and a half after discovery, we can make 100 grams in the lab. It took Maxine's 10 years to get to that level, and of course, it's cheap. So to summarize, we take flour, we put it in a special sauce, and we get spaghetti. And if we just add alcohol to the spaghetti, something I want to try someday, you get these, what I call spaghetti balls. However, if you wash in water, you get lasagna, but it's an interesting lasagna, because it's a lasagna made out of spaghetti. So you can take this lasagna and go back. So at the end of the day, really, and with the picture I showed at the beginning, this is a truly inorganic polymer in spirit. So why is this important? Again, cheap, massively scalable, non-toxic, near ambient conditions. I think that's the first ever 1D, sub-nanometer TiO2, that are extraordinarily water stable. This is exciting because of the work we did here. And finally, a large range of morphologies can be very easily obtained. And finally, this is my group, and this is what I do in summer, and I must like you very, very much, because usually I don't go anywhere in summer. But this is Hussein. He's the one who made the discovery. And with that, be happy to answer any questions.
If there are any questions, yes, please. Yes, thanks, Professor Basmani. Now it's my pleasure to introduce Professor Marius Andru, which is the Vice President of Romanian Academy and President of the Chemical Science section of the Romanian Academy. He was also Director of the Department of Inorganic Chemistry of Faculty of Chemistry at University of Bucharest, and currently is the Director of the Institute of Organic and Supramolecular Chemistry, SIDI Nenițescu of the Romanian Academy. Through his research, Professor Marius Andruch has contributed in the field of magnetic properties of polymetallic complexes, homo and heteropolynuclear complexes, chemistry of polynuclear coordination compounds, crystal engineering, metallo-supramolecular chemistry, and so on. Professor Andruch has a notable list of honoris causa titles and prizes, and is also a member of several chemical societies. Last but not least, I will mention that Professor Andruch is the president of National Chemistry Olympiad Central Commission, and he has a great contribution in the education of high school students. Professor Andruch.
Organizers for the invitation. Today are starting using so such compounds are the very good magnetic materials. So this compound we make activity and the very first step of the in a rational way combine two different spin carriers. Actually, compounds contain one kind of spin carrier, the common mechanics system or the common spin completely are rather rationally we have control the spin carriers, the nature, strength, the action. 30 years ago, so that we can combine all kinds of spin carriers. We can combine a radical with a single metal ion, 4D, a radical lanthanide, two different single metal ions, so 3D and 4F metal ions, and so on. So this generates a quite rich chemistry, and this chemistry can be excited for those which are involved. On the other hand, we can also imagine systems combining three different spin carriers, either three different paramagnetic metal ions gathered together in the same molecular entity, or two different metal ions and a radical, and so on. From the synthetic point of view, this is quite challenging, and actually we can understand this chemistry at two levels. The first level is to enjoy synthesis, because it is not so easy to put in the same molecule three different metal ions, all of them paramagnetic. Moreover, you have to control the topology and the nature of the interaction between them. On the other hand, the second level is to add a new property, because beyond the beauty of the synthesis, you have to show that bringing together three different metal ions, they work together in order to improve the magnetic properties of the similar systems which are constructed using only two different spin carriers. So that's why this is what we try to illustrate in these two cover pictures of our papers. So this is like music. So this is the score of chemistry quoting Jean-Marie Levy. So we combine different sounds here. The sounds are the building blocks, and then we compose the music of our compounds. On the other hand, if we have, for example, here three different metal ions, the idea of this picture is to show that they interact with each other, they are connected, and they can lead to new products. So 30 years ago, it was discovered a family of very exciting compounds, which are compounds that are molecules behaving as magnets. So a single molecule can behave as a magnet, and this is shown by the presence of a hysteresis loop. When we have a hysteresis loop, we have a memory effect. If we have a memory effect, such compounds can be employed to store the information. And this is the example that is always presented by us, now to show in what audience our compounds are interesting. But in order to be employed, such compounds should show these properties at accessible temperatures, because the very first molecular magnet was
observed about 2 Kelvin. And actually, there are only 2 compounds behaving like single molecule magnets at 80 Kelvin. Beyond this necessity to apply our results, it is the importance for the basic science, because the study of such compounds led to very important knowledge in science. For example, the discovery for the first time of the quantum tunneling of the magnetization. Because this is a classical picture. We have the 2 molecules separated by an energy barrier. The energy barrier depends on the spin, of course, and on the magnetic angular momentum. So we apply magnetic field, the molecules are magnetized, then we switch off the field, and we have to keep the magnetization as long as possible. But there are some mechanisms leading to the so-called slow relaxation of the magnetization. And this can be achieved above the barrier, and this is described by a classical Arrhenius law, or by quantum. There are many other mechanisms, but this one is very interesting. It is the quantum tunneling of the magnetization, and this was discovered for the first time in this family of compounds. And this is emphasized by these steps that you see here. So, another application, so first of all, we are interested in such compounds because they can store information. And on the other hand, they can be employed as principles. And these systems illustrate the quantum principle of superposition of states. In a classical beat, we have 0, 1 values, while in such system, any combination between the 2 spins which are oriented on the Bloch field can act as qubits. So we can do simultaneously much more operations in the same time. So we have to design such compounds. They have been obtained in your field, mainly in solid state physics by IWMP. Those are not molecular compounds. What I can present now are molecular compounds. So, I will insist mainly on this on compounds which are constructed using the radicals as partners for the metal ions. So we can have a radical and 2 metal ions, a radical and another metal ion. And such radicals should be stable molecules are persistent radicals. We can do chemistry with them because they are stable, and they can also act as ligands. There are various family of ligands, but of high interest for us are the so-called nitroxide molecules. They are very versatile as ligands. So they can act as terminal ligands, as bridging ligands through 2 different amino acid groups, or through 1 oxygen arising from 1 amino acid group. So there are many possibilities that opens the door to serendipity, and then we have to go beyond and try to control synthesis. Controls molecules can act as ligands. So there are many. The synthesis is very good. It's not complicated. It's not easy. So they are obtained in our group following the Woodman procedure. And this is a matter of imagination. You need aldehydes. Or you need people sterilizing aldehydes without taking physics. And or we can cooperate with organic chemists to synthesize such molecules. Because we have this platform that is important from the parametric point of view, because it's a radical, and then you can change everything here according to your interest. It's a very rich chemistry, and most of these compounds are not predictable, but their properties are very, very interesting. So, together with Andrei Petrashko, who is here, we wanted to our experience in the so-called compartmental ligands. So these are molecules containing 2 compartments. So if the compartments are different, you can accommodate 2 different metal ions. The compartments are similar. You have scrambling of the metal ions that do not have any control of the on the synthetic. So we wanted to design such compounds. So we have one compartment for a metal ion, the other compartment for a second metal ion, and the pre-existing pattern. So on the other hand, because we are interested in combining 3D metal ions with lanthanides, the second compartment should be larger and containing oxygen atoms because the lanthanide has no oxygen. So we take advantage on this properties of the lanthanide. So these are the ligands. So this is a Mannich reaction. So in the first step, so this is aldehyde. In the first step, we obtain a Mannich base, which is the first compartment, and then the oxidation, and we get the second compartment. So this compartment will be for this compartment will be for the 3D metal ion, and this one for the lanthanide. The strategy works very nicely because if you react this compound with only the 3D metal ion, the 3D metal ion likes the two compartments, and we obtain the compound containing polychloride. If we react this regard with the lanthanide doesn't like the nitrogen atoms, and the accompanied by this compartment here containing nitrogen atoms. And if we react simultaneously with 3D and 4D, each one goes to its compartment. So here is the lanthanide, it's coupled, here is the lanthanide. The problem is that from the magnetic point of view, the compound was not yourself magnetic property, but performance was lower than in the case of binary compound. So it was a disaster from this point of view, but from the synthetic point of view, it was, I think, an important contribution of Andre, because he showed that we can control the number of the metal ions in such a system. I mean, one radical, one CD, and one four. Then the idea was to change, to force somehow the metal ions to interact simultaneously. And by removing one nitrogen atom, these groups are forced to act as bridges. So this is a chiral ligand. I don't insist on this, but it's a nice story because we have stereoisomers, and we can obtain crystals which are enantiomer crystals for the compound. And this is shown. So in this case, we have changing the sign are ligand. I mean, only one nitrogen instead of two nitrogen atoms. The amino acid group acts as a bridge, so we have this interaction. The other one is 3D4A, and then CD and radical. This is the first time when amino acid group acts as a bridge between two different metal ions. So, for the first family of compounds, we had a linear topology. So 2p does not interact with each other. So no with cobalt. So no single molecule target behavior. In the second case, we have a triangle, and indeed we synthesized a compound with a blocking temperature of 28 Kelvin. So this was emphasized by AC magnetic measurements. And in order to prove that we have a synergy between these three interaction pathways, we replace one of the metal ions by a diamagnetic one. So we have cobalt 2 that is paramagnetic, when we have zinc. So the blocking temperature is lower than in the first case. So it was proof that we have a synergy between the interaction. So now we have to explain what happens in this. So it's not so easy because actually we need two anisotropy axes because cobalt and the lanthanide are strongly anisotropic. We have two anisotropy axes. We can have oriented like this. That is not good. We have we like to have this orientation, and actually for the two families of compounds, the angle is almost the same. So this is not the explanation. The explanation is here, and was done by our collaboration with and Matteo has shown that the strong cobalt radical interaction, the cobalt radical is stronger here than here. This has an important effect or the Kramer's doublet of the lanthanide. And this explains why the triangular topology is much more important than this one. So this was one story, and then we enlarged this family with other compounds. This is all done by and we use dialdehyde or monoaldehyde. They are very familiar in our group. And during the study, he was able to show to isolate a rarely characterized intermediate, an organic molecule containing N oxide and hydroxyl amino. And it was very interesting because this compound should be colorless or yellow, but the crystals were red. So this was quite intriguing, and we measured several crystals. So I showed it just, I present all the crystallographic data just to show that this position can be or cannot be occupied by an oxygen atom. So the occupation factor for this oxygen 4 is 0.8. So we can have this, but we cannot have. When it is not here, the oxygen atom, this is a radical. And this is a radical, and it is carbon. And indeed, for this molecule, we have shown the signature in EPR, showing the 7 lines which are characterized for amino nitroxide and this is finally, he succeeded to isolate this compound in so with this radical, he synthesized the bionuclear compound containing lanthanides. So the powder X-ray diffraction data show that these compounds are and another properties actually are not very interesting because we didn't observe any exciting chain interaction or something anti-ferromagnetic. So from this point of view, these compounds are not. There are some information in literature showing that either the radicals can act as spin tubes, and such measurements are done in pulse CPR spectroscopy. So pulse CPR spectroscopy is very familiar in NMR. But recently, this technique becomes very popular using EPR spectroscopy. As far as I know, you have such equipment. So, actually, we have to, so everything we have learned in organic chemistry about T1 and T2 can be transformed and deployed in EPR spectroscopy. So, we need also the spin echo, and this is classical pattern showing how it works, and then how to calculate T2. So you can calculate T2 according to this tenders of the echo. And our compound is a spin, and this is a spin echo. We have the 3 observer positions which belong to the 2 lanthanides. And this is the radical. And much more, and this is the sequence important employed to determine the spin echo and then T1 and T2. I mean the phase memory time, where you have this coherence between the 2 states. Then you lose the coherence, and your compound is no more a spin tube. And another test is to see whether the rapid oxidation observed. This is the case. So this is the dependence on the field attenuation of the rapid frequencies for the 2 systems, and the phase memory time is not so bad for each observer position. Then this is the chemical part. We are very excited about this part because Mikhail was lucky to to functionalize, starting from the dialdehyde, only one group here, and it works nicely in high yield, and you can have a 100% control on the nature of the resulting compound. So you can functionalize both of them. It was already done, published many years ago, but you can stop here. And if you have this hydrocarbon, this is available for shift reactions. You can use primary amines to further develop your ligand, like this one. So we have one compartment, another compartment, another compartment here. Or you can add another type of radical. In this case, this is classical 10. But these systems are important because the two spin areas are not equivalent, and this can lead to quantum gates because you need systems with different symmetries in this case. And it was looked by inside 10,000 lab. So this is this compound showing the system of and in this case, we synthesize compounds containing only one alkali. This is interesting because this is free, this is one half, and here you have the radical and another metal ion. And if the metal ion is diamagnetic, so the system becomes dissymmetric and can also be employed the quantum gate. These measurements are will be done soon. So these are ligands and their complexes. And this is the last structure obtained about 1 month ago, showing that we can also synthesize five other ligands with different compartments. One compartment here, but more exciting is the fact that we have three nitroxide moieties attached to the type of the material. The nitrogen the starting material is a very accessible molecule that's generated huge and spectacular chemistry. And we went back to 2p 3D complexes. So in this case, a radical and 3D metal ion. So we have chosen nickel, and I will show you why, zinc, and manganese. So in this case, we have three crystal structures. Here are the magnetic properties. This is important because you have see this large plateau that showing that this ground state is stabilized. So we have a small spin that is preferred when we are looking for spin qubits. We have, on the other hand, in the case of manganese, the ground state again the plateau is for S equal to, and this system was rarely characterized by ER spectroscopy. It's very complex spectrum. So it's a nice and useful model to investigate ER spectroscopy of S equal to. So the magnetic properties that we investigate, we see interaction electromagnetic by strong, it was supported by magnetic calculation, and once again, we get this plateau. And preliminary ER spectroscopy shows that at room temperature, we see the radical are independent. By decreasing the temperature there on the plateau here, we see the signature of the spin 1/2. And for the thing radical, the same because the thing is diagonal. So these are the spectra recorded for X1 and Q1 for the systems. And this is the quite rare spectrum for this regular compound of this. So for a compound containing manganese and the radical. And this is the G factor, and this is the two anisotropic factors that is responsible for factor. Let's see whether these compounds act as spin. So spin echo has been detected for both compounds. And there is another important thing here. So both the two compounds are spin 1/2. that zinc is diamagnetic, the radical is 1/2. Strong anti-ferromagnetic interaction, the results were related to Q 1/2. 1/2 here, 1/2 there, and the two spin echoes. See, this is structure, this is not. And the explanation is the fact that here the electron is localized on the radical, and the electron sees the nitrogen atom. And you have the hyperfree interaction between nitrogen and the electron, while here the electron is mainly localized on nickel, and you don't see this picture observed here. So these are the observed positions. And the variation with temperature T1 and T2 for this compound. And there is a big difference because we have here an exchange coupling system and a strong decrease of T1 that influences the decrease of T2, while here it's almost constant and T1 stays constant up to 100 Kelvin. So this is another system that acts some other problems investigated because you lose coherence when the molecule is not rigid, when we have rotation, for example. It's very dangerous. The interaction between the molecules. Then another important factor to be considered is the hyperthin interaction for nitrogen atom connected close to the spin 1/2 is not good. We have in all these compounds fluorine atoms, and fluorine atoms can interact with. So this is a whole study we are developing now with Floriana Tuno, my former student, now in Manchester, to investigate all these factors which can influence the coherence in the spectrum. So the Rabi oscillations. Then we enlarge a little bit our families of nitrogen with this molecule and its complex. This compound to be synthesized by Christian Spruno, and another family of 2p3b4f complexes is this one. You remember that I presented the triangular compounds. So these triangular compounds were very excited for us because we have shown that they act in a synergistic way. And this family has been obtained by rational design. This family has been obtained by serendipity. So we started from this compound I already presented. And it reacts with nitrogen nitroxide. And during the reaction with the 2-hexafluoroacetylacetonates, these are our precursors. We have to use hexafluoroacetylacetonates to increase the metal ions because the nitrogen nitroxides are not good ligands. So we have to help them to interact with the metal ions. And during the synthesis, we observed that each factor will be in part decomposed, leading to 3-fluoroacetate. And this is very dangerous because you have to show that the synthesis are producing. We have various aspects we cannot control. We cannot control the composition of this particles. And we cannot control the fact that the nitroxide is decomposed into the immunonitroxide. So that's why we synthesize 3 different compounds. We determined the crystal structure of all of them, and they were strictly isostructural. And the next step, and the final one, and the most important one, we call it the powder X-ray extraction to show that the pattern of the bulk is the same with a single crystal. So these compounds are reliable. And again, so we have 2 triangles now. 2 triangles which are connected like this. So we have 2 alkalides, metal in this case, nickel, and again, this very rare aminoxyl group bridging 2 different metal ions. And the magnetic properties are here. The problem is that this compound does not act as a single magnet. So the one I presented before was a triangle containing 2 bonds. So we chemical. And then we will go back to our chemistry. We have to go back to wet already. We synthesize triangular compound containing nickel. And now we are measuring this compound just to explain the difference between cobalt and nickel. And I suspect that the main difference arises from the fact that we have a strong spin orbit coupling in cobalt 2, while the nickel 2, the isotopy is strong. Anyway, this behavior is very clear. So we have an overall ferromagnetic interaction, and this arises from the interaction that nickel by the others are by. So this was the story I wanted to present you. It's, so there are materials who can be materials, but the material has to work. While in our case, we have compounds showing chemistry properties. So I so we have a two contact attraction skip, this is clean, very balanced Kalancha was a postdoc, the Dora Mamukan, involved in sorting many structures, and even in around planning cooperation, Maria Van, Mariana Tuna, I mentioned before, she was my student, Eva Reiter, that is for giving applications.
Thank you, Professor Andrew. If there are comments or questions, yes, please. Thank you, Florentita, for the very nice introduction, and thanks for the organizing committee to invite me here. It's really an honor and humble to be here to talk about my research on biomass valorization with electro and mechanochemistry to make hydrogen and sustainable chemicals. For many of you probably don't know me, I'm a fairly early career researcher. Like my research career started about 8 years ago when I started my PhD on carbon dose for solar hydrogen production. And after that, I switched to doing a postdoc on electrochemical biomass conversion. And after 3 years in the postdoc, I thought I could have a taste on how industry works. And then I transited to working in a green hydrogen company. And very recently, I transited back in academia, working, starting my own research in University of Surrey. And very coincidentally, Romania have marked my career trajectory because last time I was here was last September, shortly after I transited to industry for a very dear friend's wedding. And now I'm here just 2 weeks after I transited back to academia for my own research. And I hope I don't need another career change to be here again. Enough about me. So let's talk about why do I want to focus my research on waste. So like Florentina said before, I was part of the Titirisi group led by Professor Magda Titirisi. And the group is mainly focused on turning waste into resources, mainly for the application for energy storage and conversion. So essentially, we take the biomass and plastic wastes and convert that into carbon materials, which have is abundant, is low cost, sustainable, and have quite good stability. And as mentioned before, my PhD was mainly focusing on carbon dose materials. So carbon dose is a quite unique 0D material that have quite intriguing optical and electronic properties, which can be used in, for example, like photo chemistry. And my PhD was mainly focusing on to study the mechanism of how they fluorescent and also use them for like photocatalysis and photoelectrocatalysis. I was also fortunate, forgot to mention the carbon dose are derived from bio-waste derived materials such as glucose and ketosome. And during my stay in the Titirisi group, I was also fortunate enough to be involved in other waste to resource conversion projects. For example, one of them is to use the craft lignin to produce nanocarbon fibers, which can be used for like a supercapacitor and sodium-ion batteries in the energy storage applications. Another one is to transform plastics into also battery electrodes. So one of them is to use in the nylon, which basically like you can see in everyday life. And apart from the energy storage work, there are also some other conversion studies going on. So one of the work I was involved is to transform the waste, which is hemoglobin, and that's stays in the blood, so that gives you the iron source that you need, and use that to make the iron single atom catalysts, which can be used to catalyze biomass molecule conversion. And also, those single atoms can also be used for like energy conversion applications such as oxygen reduction and CO2 reduction. So, but today I'm gonna mainly talk about how I'm gonna use waste materials in my future studies, which is to use them in the electrochemistry and mechanochemistry for the hydrogen and chemical production. So the first topic I want to talk about is electrolysis, so for bio-waste valorization, which is a biomass electrolysis concept. So for those of you working in water electrolysis, this is not so unfamiliar to you. So it pretty much resembles how water electrolysis works. But instead of you putting only water into your electrolyzer, we put biomass solutions in there. And on the cathode, you still have the water reduction for hydrogen production. But on the anode, you have the biomass oxidation into useful chemicals. Why do we use that? Is because the biomass is much easier to oxidize than water, so you have a much favorable thermodynamic reaction. But the drawback is it normally have a sluggish kinetics. So that's also part of the reason why I want to study is to increase the kinetics and increase the selectivity towards the product that you want. And the biomass that you can work with are quite versatile, ranging from lignin, which comes from the wood. You can turn it into a variety of benzene chemicals. You can work with glucose or HMF, which comes from the cellulose. And then my research are mainly focused on to turning glycerol into some biomass chemicals. So why do we want to use biomass? Well, firstly, it's widely abundant. If you look around, anything green, that's pretty much biomass. And they have very high proton content, meaning you can derive quite a lot of hydrogen from it. And the biomass molecules normally have inherent high complexity, which means you don't need very complex steps to functionalize them. And the value chain for biomass treatment is pretty much mature, so you can take what's already commercially available and make them to even more valuable products. And it has the potential to replace fossil fuel feedstocks. The other concept in this study is we call it e-synthesis, or some other people call it e-refinery, but that's essentially is to using electricity to convert the molecule conversions. And that because we have now the decreased price for renewable electricity, it can serve as an energy storage. And because it happens in water, so you don't need very hazardous reagents to drive the reaction, and with the potential you get a better reaction control and you get green hydrogen as a bonus. And so that's why nowadays people are more and more towards shifting to using electrochemical synthesis to make the chemicals we used to produce with the petrochemical, so that we can shift quicker to a zero carbon, like a net zero emission world. The catalyst requirement for those kind of like biomasses are kind of similar to what you would require for water electrolysis. So on the cathode side, it's pretty much the benchmark platinum carbon catalyst, because the requirement is really the you need a low overpotential and high current density. It is the anode side that you would need a unique catalyst. So for OER reaction, normally you have the state-of-the-art iridium oxide, because it have a low overpotential and high stability. But for biomass electrolysis, the currently works best at the bi or trimetallic platinum-based catalyst, such as platinum ruthenium. Depending on whether you want to fully convert your biomass into CO2 to get most of the hydrogen out, you can have a high Faraday efficiency, you can have a like low overpotential and high CO tolerance, or if you want to partially oxidizing your biomass molecules, and then you want a high Faraday efficiency and tunable selectivity. So here is also a diagram of how this kind of reaction compared to the water splitting in terms like lower energy, lower gyps-free energy requirement and higher energy efficiency. So one study we did was to study the platinum nickel-based bimetallic electrocatalyst for glycerol oxidation. So in this work, we tuned the nickel content in the platinum nickel systems, and we found that as you increase in the nickel content, the preferred reaction happening on the catalyst surface can be different. To get optimal reaction going on like that can have a better selectivity to your desired products, you normally need a moderate content of nickel in terms like you would have the optimal CO and OH binding energy and also a faster kinetics towards complete reactions. And you also have need to have a high CO tolerance because you're gonna produce CO no matter what. So in this study, we found that with a moderate nickel content, we can actually selectively get a C3 product coming out of the reaction. So the experimental setup is also very similar to what the water electrolysis use. So it is MEA setup combined with two parastatic channels and a PID controller to control the temperature, and you just apply potential to split the biomass molecules into hydrogen and chemicals. And using this type of setup, we did two kind of case studies. So one of them is to convert glycerol into lactic acid and hydrogen. So for many of you probably not familiar with lactic acid, it is a monomer for the polylactic acid, which is a flat shape bioplastic that's nowadays being used to replace some of the thermoplastics. And the conventional way of producing lactic acid is pretty much using fermentation, and that you need to rely on the bacteria to do the job. You know, bacteria, they need really conditions that make them happy. So you need very strict temperature and pH, and even with that, the productivity is quite low. So normally you would get 1 to 3 grams per liter per hour. So if we want to scale up the production of bioplastics, this is quite obvious that would be the bottleneck of the low productivity. So one of the alternative way of making them is proposed by Professor Javier Perez Ramirez group, which is a cascade reaction. Well, the first part is still transforming glycerol to dihydroxyacetone intermediate using the fermentation method. And then after that, you use a thermal catalysis way to produce lactic acid. But still that requires that you have to separate out your DHA intermediate. So the way we propose to use is the electrochemical way, which using the electrolysis method that I introduced, and then just feed glycerol and water into the system, and at the end you get hydrogen and the lactic acid out. So, well, easy to say, but actually it's quite challenging to do. So if you look at the reaction pathway for turning glycerol to lactic acid, it's quite complex. So normally you have a dual reaction pathway going on. First, you need to convert the glycerol into the two major intermediates, the dihydroxyacetone and the glyceridide. And then the dihydroxyacetone would go through the dehydration pathway and finally getting lactic acid, while the other one would go through an oxidation pathway to transform into like glyceric acid or formic acid. And it is well known that the first dehydrogenation step
the platinum is the best catalyst so far. So we thought, okay, we just use platinum and see what happens. It turns out it doesn't happen that easily. As you see, for the selectivity to lactic acid with platinum itself is quite low. So you can only get like over 30% of lactic acid out. And the reason for that, we did some DFT studies, and that's because at the reaction potential happening where the platinum is active, the reaction would preferably happen for the oxidation pathway because they are mainly electrochemical steps. So as you hold the potential there, the reaction for this one is pretty much downhill. So you would preferably transforming the glycerol into your oxidation products. While on the other side, the pathway towards glycerol, lactic acid is a mixture of electrochemistry and chemical steps. So that's why the platinum itself doesn't work the best. So we thought, okay, there is kind of a heterogeneous catalysis going on, so why don't we take some inspirations from the heterogeneous catalysis? And that's how we come up with a tandem catalytic system. So in the heterogeneous catalysis, people tend to use some metal oxides with some Lewis acidity sites to catalyze this type of reaction. And the reason why is because those acidity sites would preferably bind the dihydroxyacetone molecule, and then it just helps transformation to another intermediate peroxide, and then that's transformed into lactic acid in the solution phase as a Cannizzaro reaction. So with this, we just combine the platinum with the metal oxide and hoping the reaction would happen at the interface to improve the selectivity towards lactic acid. And that's what our hypothesis kind of got verified by the experimental results. So with the combining of platinum carbon with the metal oxides, we managed to increase the selectivity to lactic acid to more than 60%. So that's 2 times higher than what we used with platinum standalone. And the cell voltage, because it's easier to oxidize than water, the cell voltage can maintain at below 1 volt. So if you transform that into the energy consumption for hydrogen production, that's about 26 kilowatts per kilogram of hydrogen compared to the state-of-the-art 51.2 for the water electrolysis. And also we did some DFT work to explain why the metal oxides would work so well. So with that, like some collaborators did some work to calculate out the absorption energy for the 2 intermediates, and we managed to establish a selectivity descriptor, which is the absorption difference between dihydroxyacetone and glyceridazide. So if you have a larger difference between these two, in another word is if you can bind dihydroxyacetone stronger, and then you normally have a higher selectivity to lactic acid. And that's what we found in our study. So we screened 3 different kinds of metal oxides with different Lewis acidity sites. And we see there's nearly a linear relationship between the lactic acid selectivity and this descriptor. So we believe this descriptor can help us with screening more like catalysts that can further improve the selectivity to lactic acid. So, and until this point, people might ask, like, are there enough glycerol to help you convert enough hydrogen and lactic acid out? So the answer is, I don't know, but we can
use another feedstock that might be more abundant. So that's another case study I did, which is converting plastic waste. So as we all know that plastic waste has been a global challenge for many years. So over 9 billion tons of plastics has been produced to date, and even less than 30% of them has been recycled. But because they are made from petrochemicals, the CO2 emission associated to this will exceed 2.8 gigaton per year by 2050. So to tackle this challenge, the solution we propose is we're gonna use the plastic waste and upcycling it into the pure monomer, which can be reused to make virgin plastics. And what's left in the reaction would be used to produce green hydrogen, similar like what we did for the glycerol. So the feedstock is essentially low cost and widely abundant. So how we depolymerize the plastic? In this case, we studied the PET plastic. And for that, it's going to be introducing another topic of my research, which is mechanochemistry. So I'm really happy that Professor Andrew Rappi has already introduced mechanochemistry to you. So it is a really promising field, but over the years has been underestimated. But nowadays we see there's a emerging trend of reusing this fantastic technique to do a lot of chemical reactions. So mechanochemistry is disruptive chemistry. In this case, you just apply some mechanical forces into your feedstock, and then they would break certain bonds to help the depolymerization. So in my case, it is depolymerizing the PET chain to get it into terephthalic acid and ethylene glycol. And the devices that can be used for this type of reaction are quite simple. So you can either use a ball mill or you can use acoustic mixer, which both can supply the mechanical strengths required. So what's unique about this type of reaction is, well, first of all, you can have a circular economy for the plastics, and because the reaction happens at solid states, so you can save the solvent, and because it's also, and the reaction normally happens in a few minutes, so the energy saving here is also unique, and you can have precise control by putting exactly amount of the catalyst or water needed for the reaction, and because it can be entirely electrified. So if you combine with renewable electricity, you can also have a zero carbon emission for this type of reaction. And with that, we managed to convert the plastic waste that we gathered from Starbucks or like even water bottles, and had more than 90% of the plastic waste conversion with more than 95% of the TPA yield and more than 75% of the ethylene glycol yield. So if you look at the NMR spectrum, that's pretty much what we get from the reaction. So it's the products you get out is also ultra high pure. And with disodium terephthalate, you can very easily separate them out by just tuning the pH, and they would just precipitate. And what's left in the reaction, ethylene glycol, you can just feed it into the electrolyzer that I talked before, and then you would get hydrogen and some other chemicals out. So we all know that PET is a relatively easy plastic to work with, but beyond PET, what else we can work with? So so that would be the future topic of my research, which is a catalytic mechano and electrochemistry. So one of the very good tool in the mechanochemistry is simulation work called COJEF. So the confined geometry external force method, which can use to predict the mechanochemistry activity. So it can simulate the effects of mechanostrengths on the molecules. That's called mechanophore. So that's the small build like block that you can cut the polymer chains and enable the prediction of mechanochemistry activity. So with those in mind, that we may be able to extend the amount, the variety of plastics that we can work with. So for example, we can work with polyamides, such as like nylon or polyurethane, or like polyesters that's similar like PET, and some polycarbonates. And with the catalytic mechanochemical process, we can get a variety of chemicals out, such as like amides, alcohols, acids, and aromatics. And for those ones that useful on its own, like commodity molecules, and then you just separate them out and sell them. And what's lower value, you can just feed that into a e-synthesis method to make the chemical and fuels that we want to work with. So the vision for this kind of work is that we really want to move away from petrochemistry. So I really like this diagram, because if you think of everything we have during our nowadays, if you source them back, it normally ends up like sourcing from crude oil or natural gas. But if we can manage to replace them with some waste valorizations, we can maybe shift away from the petrochemistry to a more sustainable world. And once the products made from your waste feedstocks, and they can just circle back to make more products. So the conclusion and outlook of my talk today is, so the circular economy really calls for a changed mindset of how we build waste materials, which stimulating new research areas. And also an emerging research direction is to couple green hydrogen production with sustainable clean chemical generation with electrolysis, and mechanochemistry holds great potential in the future for chemical synthesis. So with that, I'd like to thank all my collaborators, and also thank you for your attention. I'm ready to take questions. Okay, thanks for the question. Well, the first part with a mixed like plastic part, I guess it would rely on both. One is like people's awareness of sourcing them out when they recycle them, and but yeah, that's an external factor. The other factor is once we have a fundamental understanding of how this works, we would look at have a mixture of plastic and see how they would work all together. I know there are already some research in the field that are looking at a mixture of plastics. So I'm hoping once we take the, but they normally use as a chemical catalyzed process with high temperatures or very hazardous solvents. But we hope with mechanochemistry, if we manage to catalyze most of the plastics, we might be able to also work with mixtures. And the other one about the selectivity part, yes, so until this point, on the electrochemistry part, we haven't been able to optimize the selectivity. All the work I have done was on optimizing the metal oxide part and also the reaction conditions that helps this heterogeneous catalysis pathway. But for that other part, I think I have learned a lot from today's research and also the research that's going to be introduced for the next 2 days. We would come up with ideas to changing, for example, the morphology or the electronic structure of the metal catalyst, and hoping that would play a role in improving the selectivity. Thank you.
The next speaker is Aurelia Bisha, which is senior researcher at Coriolano Drăgulescu Institute of Chemistry in Timișoara, which is part of Romanian Academy. She is also associated member at Interdivision Chemistry on Green and Sustainable Chemistry at IUPAC. Her focus are on green synthesis of coordination polymers.
Thank you very much, Florentina, for very nice introduction, as well for the kind invitation to be part of this amazing workshop. Thank you to all the organizers, and I will try to be as fast as I can to go through this and have also the coffee break. I will start with the outline of my talk, the application and material, how we choose the material in order to do our research. We stop to metal organic frameworks. I will speak about the UPAC and international collaboration, MOF synthesis. We stop at green synthesis of these materials, application and outlooks. This is the institute that I'm coming from in Timișoara, as Florentina mentioned. And the need of new material with new properties and to be part of the new application, it's driven the effort of many research groups to study the multifunctional solid material. The solid materials are inorganic, organic, hybrids, metals, and glasses. We stop at inorganic organic hybrids to coordination polymer and MOF in our research. What are MOFs? MOFs, based on UPAC definition, are coordination polymers or alternatively coordination network with an open framework containing potential voids. This is the general formula of MOFs, but before starting with it, I will stop to a quote of Professor Omar Yaghi, the father of this amazing field. It's saying like diversity of thinking is the heart of discovery. Indeed, diversity is really important in all the things that we are doing, but also diversity in our synthesis, it's important, and the MOFs materials are really diverse because they start with metal ions and together with the organic linkers form a coordination bond and then make a network. Network can be monodimensional, two-dimensional, or three-dimensional, and and the metal ions can be very varied because we use monovalent, divalent, trivalent, as well as tetravalent metal ions, and the organic linkers can be both carboxylates, but unconventional MOFs use phosphonate, boron, sulfones, or heteroatomic compounds. Here are this one is the first MOF developed in the literature. Now it's commercially available, but one can see that changing the metal nodes and changing the linker, or even increasing the number of ligands used, the molecules can accommodate different materials, different gases or capture CO2 inside. Because as Florentina mentioned, I'm part of UPAC, and I want to share very quickly two projects very dear to me. I'm part of Green Chemistry Summer School, the project that we develop and are doing every year. I'm very glad to see that in the audience are a lot of young chemists that can apply for this summer school. We are having the school with a diverse number of countries as well as a balance between females and males. And here is the Professor Pietro Tundo. He's the father of green chemistry in Europe. The second project that I work on, it's based on system thinking. What is this system thinking? It's helping us to understand and to do the research and to think in to connect parts between and to think all our research and our work into a system. In this project, we are divided in three working groups. I'm dealing with sustainability and chemistry education. Our work is based in writing articles, doing material for teachers, as well as we are thinking to integrate two very important frameworks, the United Nations Sustainable Development Goals, as well as planetary boundaries, into the curricula and to show the people and to realize how important it's to make the synthesis on green chemistry, based on green chemistry principle. So these are our partners, and now going to research. The 12th principle of green chemistry we use in our synthesis of MOFs, and we are thinking at environment, human health, economy, sustainability, and science, and do all of this in order to develop novel strategy for facile and rapid synthesis. And how we are doing this, we try to optimize the energy and to design safer chemicals. Let's go to work. So designing safer chemicals, since more than 70% of reactions need solvents, toxicity survey of the solvents was done, and here is the diagram. And we recommend to be used the solvents on the green column, and try to avoid the highly toxic solvents that are on the red columns. Of course, if it's possible, it's even better to avoid to use solvent or use water solvent, or greener alternatives, supercritical fluids, or ionic liquids. Also, to save the energy, we design our materials and make the synthesis in sonochemical methods, microwave and mechanochemical. And thanks to the previous speaker, Professor Rapp and Dr. Lowe, to introduce this, it's easier for me to speak about. And if you are looking for fundamental insights, and if you need to develop new material and to have the crystal structure, then use hydrosolvothermical method, because here you can obtain crystals, but the other methods you obtain it's easier, it's very hard to isolate single crystal. You mostly have powders. Just very quickly, solvent-based and mechanochemical methods. Here are the advantages of mechanical method. I will not stop to it. Just say that we can save time, and also it's cost efficient. So our goal is to bridge the green synthesis and application to achieve the greatest positive environmental impact. as I mentioned, the ligands are diverse. We are using in our research phosphonates because phosphonates are versatile ligands, and they are having 3 oxygen in the coordination moiety of phosphorus, can be doubly esterified and double deprotonated based on the reaction pH. And all these features increase the possibility to access novel structure. In our research, we vary the ligands that we use and try to apply our materials as water purification material, corrosion protection catalyst, and humidity sensors. How we perform the synthesis? Of course, start with very small amounts, optimizing the reaction condition. We optimize the pH, the temperature, the ratio of the compounds, of the reagents, the one that we use. We perform on water bath, autoclave, as well as sonochemical, microwaves, and mechanochemistry. And once we have the condition, the optimization of the parameters, we make the reaction in upper scale in order to obtain the micrograms, because we multigrams, because we need multigrams in order to give to our collaborator for the application. And these are, we of course use infrared as first characterization method, and then make it X-ray, thermal gravimetry, and of course single crystal structure. We saw how our compounds are structured, how they behave, if they are what's the dimensionality of them, and then use for in most of the cases for pollutant removal from wastewater. For this we use for toxic substances like lead, mercury, cadmium, phenols, chlorine compounds. Our material were used to remove pollutant, as you can see the metal uptake, and we use lead, cadmium, chrome, nickelus. The best results are obtained for the lead. We also investigate the absorption of dyes in our compounds. Of course, the collaborator who performed this modified the initial pH, the contact time, the initial concentration of it, and we compared the maximum absorption capacity with the one present in the literature, and one can observe that they are comparable, or in some cases even better results. I will stop with the subject that we are working right now. There are bisphosphonates, and out of bisphosphonates we stop to 1-hydroxyethylidene 1,1-diphosphonic acid. It's the compound, it's having 2 conformation, a W rigid and a eclipse conformation, and the compounds that we synthesized, we perform research with zinc, nickel, and cadmium. We use imidazole as a coligand, and these compounds are used further from our collaborator in University of Malaga, and they test, they make electrocatalytic study electrocatalytic properties of these compounds for hydrogen evolution reaction, oxygen evolution reaction, and oxygen reduction reaction. And it's observed that the nitrogen doped metylphosphine are giving better results in the electrochemical performance. The outlook, I will just very fast go on it. It's a project that we are just developing right now. Don't have too many results, but we decide to combine the advantages of ionic liquids with MOF compound. There are only some 2,000 references in the literature, so it's a good domain to work on it. We make the composites and analyze them for absorption of pollutants from water. we use in the conclusion, we use 12 principles of green chemistry for the synthesis of MAFs. The phosphonite metal organic framework exhibit a variety of application. We use the composite absorbent material, and I will not finish without thanking to my colleagues, the person that are work close to me. Without other, I cannot do the research, and the results will not be like this. My collaborator and friend, Bianca Maranescu, she's in the audience. Thanks, Bianca. She's very smart and hardworking people. And thanks to my colleagues for, from Venice, Professor Tunda and Fabio Arricco, Malaga University, and University of Crete, Irini Armacola. She was one of Erasmus students in my research group. And before closing my presentation, I would like to invite you in Timișoara. We have a conference in September, but not only for the conference. Timișoara, it's the European Captain of Culture. We have also a lot of science. We have 4 Nobel Prize that visiting us, and of course, a lot of cultural events. I will be happy to welcome you to Timișoara, and thank you very much for your kind attention.
Thank you very much. There.
Thank you very much. Thank you very much. I will be more than happy to discuss with you about this subject.
Are there any other? If not, we can take a coffee break of 30 minutes. And we'll continue. which is a project officer at European Innovation Council, where she works on supporting the EIC Pathfinder program since September 2027. She worked for about 7 years for European Research Council as a scientific officer in the field of material science and engineering. And before joining the European Commission, she was a scientist here in Romania at the University of Iași, where she was continuously involved in translating scientific results in end-user products. Thus, she has a vast knowledge and experience in R&D management, industrial development, pharmaceutical technology, and scientific research in the field of nanomaterials for application in health and environmental cleaning. So, Alina, today I think you'll present something about the European Innovation Council.
Thank you, Florentina, for your nice introduction. Hello, everybody. I'm very happy to be here to present to you the funding offer of the European Scientific Council. As Florentina said, I am a project officer at European Innovation Council, and I think, if I'm not mistaken, this is one of the first presentations in Romania about the European Innovation Council. So the European Innovation Council is the major novelty of Horizon Europe. It was set by the European Commission in actually before 2021 as a pilot, funding only a small program for small innovative companies. But in 2021, the Commission set the European Innovation Council as part of Horizon Europe under Pillar 3 Innovative Europe, together with the European Institute for Technology and European Innovation Ecosystems. European Innovation Council represents Europe's most ambitious innovative initiatives. For the time being, we have, it was set for the duration of Horizon Europe a budget of 10 billion euro, in order to bridge the gap between the frontier research funded by European Research Council and all the funding programs for startups, SMEs, and scale-ups. So the objective of European Innovation Council is to fund breakthrough innovation stemming out from frontier research. It enhances the European innovation ecosystems in partnership with European Research Council and with AIT regions. The first work program in 2021 ran with a budget of 1.5 billion euros, which slowly increases in Horizon Europe. Now, how a European Innovation Council works. The strategy and its implementation, it's steered by an AIC board of advisors, who are entrepreneurs, investors, researchers, innovation ecosystem partners, and so on. And their role is to advise the AIC on its strategy to follow, on the work program and implementation, and on broader innovation policy. Then we have a group of 10 program managers hired by European Innovation Council, who are experienced technology developers, scientists, and entrepreneurs in different fields covered by Horizon Europe. And their role is to develop strategic visions for technology breakthroughs, to manage portfolios of projects in an interactive way to achieve breakthroughs, to pull through research results towards their commercialization, and to build ecosystems of researchers, investors, innovators, corporates, and so on, in specific fields.
Then, in conjunctions with these two boards, we have European Innovation Council and SMEs Executive Agency, who is the implementing operational body of the work program established by the European Innovation Council. So actually the agency runs the entire evaluation, grant monitoring, policy feedback, and so on, all the operational futures. Now, about the funding schemes offered by European Innovation Council, there are three very important funding schemes. The first one being Pathfinder, where we fund projects very early in research, but with a very important component on breakthrough technologies. We consider that this is the next step after the European Research Council Frontier Research Science funded. These Pathfinder projects are in general destined to consortia. And for example, for bottom-up projects, minimum three beneficiaries have to be part of the consortium, while to top-down challenges program, two or even one single SME beneficiary can apply for a Pathfinder project. You have to know that these projects are very early in the development, meaning that the technology readiness level is very low, 1 to 4. Then we have the transition grants, which are destined for consortia or single researchers or companies. But then you have to have a proof of concept, a validation of your proof of concept. So the technology readiness level is already from level 3 to level 6. You can receive up to 2.5 million euros. And there are also two types of grants, bottom-up open or top-down challenges. The third scheme of funding is under the accelerator program, who is destined only for individual companies. And the technology is already at a higher development and scale-up level. It's already technology readiness level 6 to 9. Here you can receive, as a small company, grants up to 2.5 millions and a bank investment of up to 15 million euro. You also have to know that under the accelerator, as a small startup, you have to demonstrate that you are not bankable. This meaning that you have looked for investment in banks and they have refused because your technology is too and your innovation is too risky and they don't believe you. So the European bank will give you money for this, while other banks will not give you money for this. Okay, what is the European Innovation Council Pathfinder program? So the Pathfinder program is focused on funding brilliant research ideas that underline technological innovation. So we are funding research to develop scientific basis to underpin breakthrough technologies in any scientific area or technological area. We support earliest stages of science technology and deep tech research and development with a technological maturity of TRL 1 to 4. And with the aims to build on new cutting-edge directions in science and technology to disrupt a field or a market. European Innovation Council Pathfinder Open Program, as I said, it's destined to any field of science and technology or application without predefined thematic priorities, while the Pathfinder Challenges program is it supports coherent portfolios of projects with predefined thematics area, which we are calling a challenge. And there are 5 challenges in the 2023 work program, and I will talk to you about a bit later. Now, the 2023 AIC Pathfinder Open Call. The vision of the Pathfinder Open program is to support bold ideas for radically new technology. So we are looking for visionary thinking in technologies. We are funding high-risk, high-gain science towards technology breakthrough. We are looking for interdisciplinary cutting-edge science collaborations. That's why consortia can apply for it. And it's extremely important to know that it's any field of science, technology, of application, without predefined thematic areas. Now, who can apply for an open Pathfinder project? Minimum, it has to be a consortium of minimum 3 beneficiaries from 3 different countries, from any member states of associated country, but at least one of the partners has to be in a member state. Not all 3 can be from associated countries. At least one can be needs to be from member states. Beneficiary from countries which are not member states of associated country can participate as associated partners in the project, but they have to contribute with their own budget. They will not be part of the costs incurred in the grant. From the point of view of what kind of beneficiaries can apply for a Pathfinder Open project, universities, research institutes, SMEs, being SMEs performing research or innovation activities, or even consultancies, but here we have limited participation, meaning that limited type of task can be assigned to an SME performing consultancy, startups, industrial partners, or even natural persons. You have to know that research teams of each beneficiary and infrastructure is part of the evaluation, so you have to choose your partners extremely careful. We are looking for collaborative work of the consortium partner when we evaluate the project. We are looking for interdisciplinary work between the area that is covered by the project, and of course we are looking for the gender balance in the team's compositions. The gatekeepers of the Pathfinder Open program is the long-term vision of a radically new technology. We are looking for concrete, novel and ambitious science towards technology breakthrough, for high-risk, high-gain research approach and methodology. And you have to, as I said, you have to very well define your partners and define the consortium and how you will work together. What we expect when we choose and we fund a certain type of projects under the Pathfinder Open, what do we expect from them is that at the end of the project they will have a proof of concept of the main ideas of the envisaged technology, which are feasible. We are not looking for the final marketable idea, but the proof of concept should be there. We are looking for top-level scientific publications in open access. As I said, we are still funding scientific research at this level in the Pathfinder program. So we are expecting top-level scientific publications. At the same time, being so much focused on technology readiness and involvement, we expect that our beneficiaries will take formal protection of the generated intellectual property. We are encouraging you to involve and empower in your team key actors that could become potential future leaders. This means focus on the early career stage researchers and promising high-tech SMEs. And we are encouraging to empower female researchers in technology development to achieve gender balance among the work package leaders. What support will you receive in case your proposal is funded? You will receive a grant for a research and innovation action to cover your eligible costs. You can request up to 3-4 million euros, but with the right motivation, you can go up even beyond this amount. We don't have a fixed amount for the Pathfinder Open grant. We will fund 100% of the eligible costs, and you will benefit from many other services to accelerate your business or the interaction with the AIC. We facilitate the interaction with the AIC program managers who, as I said, they are very well connected in the field, and especially in your field of interest. Why you should apply? First of all, because you have an ambitious vision for a radically new technology and you need support. Because you receive more than just financial support for your ideas, you will find partners. You will receive a lot of advice on the economical growth of your business and so on. You will benefit from the next generation innovation talent scheme, which was set up by the European Commission to boost the participation of young researchers and innovators in grants. And you will benefit from non-financial support through the AIC Business Acceleration Services, meaning coaching, mentoring, how to develop your business, how to translate your results from research to business, and so on. Projects funded under the AIC Pathfinder schemes are also eligible to receive AIC Booster grants, which means that through these grants you will benefit from more advice on commercialization of specific parts of your project, or, for example, if you are part of a portfolio activity. You will also receive counseling and the chance to submit for an AIC transition proposal, or we can, if your project goes very well, we will encourage you to even go to an AIC accelerator proposal via a fast-track scheme which was put in place by the AIC, especially for those innovative ideas that are going significantly beyond what they expected. Okay, now how do you apply? Do you apply via the funding and tender opportunities portal, like for any Horizon program? You will be informed about the evaluation results within 5 months from the call deadline, and if you were successful, we will sign the grants within 8 months from the call deadline. For the 2023 program, the Pathfinder Open program is closed now. The deadline was on 7th of March, and the next call will be open in March 2024. Will be open in December 2023 and closed in March 2024. I want to tell you very shortly on the Pathfinder Challenges call and what is the difference with the Open. The big difference between the Open and the Challenges call is the fact that when you apply for a Challenges call, then you apply in an already established thematic area. And the project manager is looking for to establish a portfolio of projects in a certain area. These areas for 2023 were set as clean and efficient cooling, architecture, engineering and construction digitalization for a novel triad of design, fabrication and materials, precision nutrition, responsible electronics, and in-space solar energy harvesting for innovative space application. Challenges, for the Pathfinder Challenges program, you will find more information on the website of ERC, where we have a specific guidelines for how to apply for a challenge and when to apply for a challenge call. Who can apply for a Pathfinder Challenges? This time, single legal entities established in a member state or associated country, or consortia of two entities who should be two independent legal entities from two different member states or associated countries, or consortia of three or more entities where at least one of the entity has to be established in a member state. The legal entities can be university, research institution, SME, startups, industrial partners, or natural persons. Comparing to open calls, what we will expect that the projects funded under a challenges call will participate together in some common portfolio activities in order to boost this challenge as it was taught about the project managers. You will receive a grant. Also under the Research and Innovation Action, you might consider a project of up to 4 million euro, but even more if it's duly justified. Again, we will fund 100% of your eligible costs. The indicative total budget in 2023 is 163.5 million euro. And you will also benefit from the business acceleration services and the AIC program managers actions. Just shortly, just to remind you, there is a difference in between the two challenges the two Pathfinder calls, and they open at different times in a year, and there are specific different templates for the projects to apply. I want just to very shortly show you some statistics from the 2021 and 2022 Pathfinder calls. For example, in 2021, the most proposals that were funded were in physical sciences, while in 2022, most proposals were funded in medicine and medical engineering. In Romania, in 2022, we had 41 proposals applying with only 5 coordinators. Unfortunately, none was funded in Romania. And in Pathfinder Challenges, we had participants, 17 participants as beneficiaries and 6 as coordinators. And again, none was funded. The only projects which are funded in Romania by AIC are under accelerator grant, who are for SMEs. Thank you very much.
Thank you, Alina. So if there are any questions, please. I can give it to the organizers, and then they will distribute it only to the participants of this conference. In advance and sewage. In the AIC grants, no. There is not such, no. The difference between the Pathfinder transitions and accelerator grants is in where is your technology development? How well is developed the technology? Is at the beginning or is more advanced? This is the difference, but not in the age or the academic age of the participant. And the difference with the ARC is that here we sign with the host institution, where the team has a very important role, while in ERC you sign with the person and the institution comes adiacently to support the person. But in ERC you fund the person,
While in AIC, in Innovation Council, we fund the institution with the team that they propose. But the team can be changed. While in ERC, not. In ERC, you cannot change the person. The person takes the grant and goes wherever, but you cannot change the person in ERC grants. But in EIC, yes, you can change the team or the person who leads a work package. You're welcome. Yes. So from the point of view of countries, AIC, comparing to many other funds offered by the European Commission, we don't have country quotas. So whatever project is the best, this is what we are funding. Now, why, especially in EU 13 countries, the number is so low? First of all, it's a low number of applications. So therefore, no success rate or very low success rate. But we have to encourage the people to apply, first of all. Second of all, I think, and that's why I wanted to underline at the beginning that I think this is the first time when in Romania AIC is presented, because I think there is a lack of information, especially in EU 13 countries. It's not that the information is not there, everybody can look for it, but it's different when you hear it again and again and again with so much insights and so on. So I think the information is lacking, the courage also to apply is lacking, and indeed you have to choose your consortium, and you have to build a consortium from 3 different countries. They can be all Balkanic ones or EU 13 countries. As long as your idea is good and it's breakthrough technological development, we don't care from what country the consortium comes. Only that I personally believe that the information is different in the West Europe than in the East Europe. Thank you.
So,
I think the lady in white.
Was Ștefan.
Common mistakes when writing grant proposal. First of all is the lack of enough information on how you will do. I mean, sometimes we focus so much on writing well all the buzzwords, you know, but then we lose from the scientific insight. And in Pathfinder, comparing to accelerator or transition, in Pathfinder we still look for science. So it has to be a lot of scientific jargon there. And I think this is one of the common, we lose in writing the buzzwords in implementation and so on, but you have to convince with the scientific enough information that you deserve the money. And second, I think it's in general, it's the idea. So it depends very much how you really convinced the panel and the evaluators that your idea is a breakthrough, that it's high risk, high gain, that is breakthrough, and that Europe will gain something afterwards. You know, that truly we will want to push you towards an accelerator grant and so on, and Europe will gain something. For the time being, UK can apply as any other country from the member states, because for the time being, UK hasn't said we are out or in. Horizon Europe. There are still discussions, you know. So for the time being, UK institutes are eligible to apply. We evaluate the grants with UK in. If at the moment of the funding date, still the agreement is not signed, then the consortium is requested to replace the UK partner, or if the consortium is built in such a way that they still have 3 partners from member states, to keep the UK partner, but the UK partner will come with their own money. We can keep also the, even if they don't have 2 member states, but they have to bring another partner still to fill in the eligibility with 3 partners from member states. So for the time being, the UK host institutions are eligible to apply. Yeah. Yeah. They are taken in consideration in Brussels, yes. Yes, they are taken in consideration in Brussels. But in the end, so there are two dimensions. In Horizon 2020, the open access publication was, I mean, it was still the obligation to publish in open access, and the to pay the fee for an open access publication, it was an eligible cost, which in Horizon Europe is not anymore an eligible cost. You can publish in whatever journals you can publish. We do not forbid to publish in hybrid journals. Only that the cost for paying the open access, not the publication fee. So if it is a journal that asks for publication fee, the publication fee is eligible cost, but the open access is not an eligible cost. So this is the difference, first of all. Second, actually, it's not against this measure of the Commission. It's not against the researchers. Actually, they want to connect more the researchers to open the data, to open the information and so on to everybody. The Commission, this measure of the Commission goes against the publishers. Actually, they want to force the publishers not to have such high open access fee. This is the idea. And there are countries like Netherlands, for example, who they went against this trend of the publishers to have such a high fees and so on. So, for example, in Netherlands, there is a law that overrides, and us in European Commission, we have to obey the national laws, which overrides the Commission open access fee, non-eligible costs, and so on. And this law says that any cost from any grant funded in Netherlands through any national or European funding are considered eligible costs. You know, so from this point of view, they are forcing our hand still to pay, but they are forcing at the same time the hand of the publishers not to have such high publication fees. And we had, for example, in the conference in Lisbon, in the biggest chemistry conference in Lisbon last year. It was such a big discussion with so many people involved in this open science. And the problem is that one is open science and the other are these publishing so high publishing fees. And so my answer, also as a ex-scientist and also as a representative of AIC, is that no, we do not encourage you to publish in not well-respected journals, but we have to find a way in between us and the publishers, and not to pay businesses, you know, but to open the research and the data to everybody to have access to. And for example, there is also for example, lately, even Nature, you know, with Horizon 2020, because before Nature was having, okay, you pay this huge amount for a publication to be open access, and you have an embargo period of 12 months. With Horizon Europe, Horizon 2020 diminishing the embargo period to 6 months, we forced also their hands, and they also put okay with an embargo period of 6 months. So now we are trying with the Commission, with the big research institutes from Europe and so on, also to open up this embargo period not to be anymore, and this publishing fee not to be, because it's, you know, it's not okay. We still have to open good quality research. We don't want to open not good quality research. We don't want that the high quality research still to be highly paid and still close to the open public. Thank you.
Okay, let's thanks Alina again. For other discussion, we can find for the breaks. The next session is dedicated to our sponsors. I think they will present their companies better than me. So I'll invite Liana Socaciu-Sibert from SPECS to present NAP XPS instrumentation and application.
Yes, hello. Okay, so yeah, thank you very much. Want to the organizer for giving me the opportunity to show you some of our latest developments. And of course, I would like to thank you for being still here at the last session of the day. And I would like to start with saying a few words about the company. So SPECS company is located in Berlin, almost in the center, a little bit north from Alexanderplatz, in the former building of the AEG company. So in the same production halls where more than 100 years ago AEG produced huge turbines and motors, we are producing now components and systems for surface photoelectron spectroscopy and surface microscopy. So we are developing, producing, selling and installing, servicing our own products all over the world with the help of our branches in US and China, and also with the help of our partners. And here in Romania, our partner, is the company Hysteresis. So today I would like to talk about the near ambient pressure XPS instrumentation and application. And I would like to start a bit with the basics. So let us take a look what is the difference between, let's say, standard XPS, so standard in UHV, and near ambient pressure. So in the standard XPS, you have the X-ray source shining on the sample, you emit photoelectrons, and the photoelectrons are analyzed by using energy analyzer. So, but in the near ambient pressure conditions, so you have the same X-ray, the sample emits photoelectrons, but the photoelectrons undergo collisions with the gas molecules, which means they will be scattered, and we will analyze just a part of the emitted photoelectrons. So what do we need in order to be able to measure near ambient pressure XPS signal? So we have to catch the electrons before most of them are inelastically scattered, which means We need short electron and X-ray travel lengths, differential pumping stages. We need to cross the pressure gap, which means we have to build analytical components that are able to work in wide pressure ranges. We have to control the sample environment, and we have to be fast. And this is what we did in the last, let's say, 15 years. And meanwhile, we have a very large product portfolio for components like electron analyzer, different X-ray and UV sources, corresponding software, gas inlet, also combination with near ambient pressure, scanning probe microscope, IFM and STM, or even combination with infrared spectroscopy. So the main part, the heart of every system and every experiment is the photoelectron analyzer, and in our case is the Phoibos 150 near ambient pressure, which has 4 differential pumping stages, so that the detector will be always in vacuum conditions, and here in front of the nozzle you can have a pressure up to, I don't know, 25, 30, 50, even higher pressures if we reduce the opening of the nozzle. So also what is important for the analyzer is that you have a very large acceptance angle, so 44 degrees, so that you can catch most of the electrons which are emitted from the surface. We have a very large portfolio not only for components but also for systems, and meanwhile we can say we have different type of systems. So near ambient pressure systems with in situ cell, which means that only this small cell acts as a reactor. Only this cell is filled with gases, and this cell is inserted into an analysis chamber, which always stays in UHV conditions. We have system with backfilling configuration where the entire analysis chamber is filled with gases, and also systems with exchangeable chamber. This is usually for synchrotrons, where you have a multi-user experiment. So you have a multi-user regime, and you have to be able to exchange the analysis chamber between different users. So also we added, so we launched 2 years ago the series Provenix system. Provenix comes from proven experience, which means that the systems is the are the quintessence of our experience in building near ambient pressure XPS systems, and this is for backfilling configuration and DeviSim in situ cell configuration. Also, a few years ago, we thought, okay, let's make this technique available to, let's say, to everybody, and we launched the first and still unique, fully automated near ambient pressure XPS systems in the world, the EnviroSCA, which is actually meant for high throughput analysis, so measuring 24/7. So actually what we did here, so we took the components from the open systems, we just put them together, we added a nice cover and the full automation, and this is how it looks. So I would say the big advantage of the EnviroSCA is you have no lot lock, which means you do not have to transfer the sample first inside the lot lock, then into analysis chamber. Here actually you just have a sliding door, you open the door, put the sample inside, whatever the sample is. We measure everything from Coca-Cola to, I don't know, tomatoes, I will show you later, and close the door. In 1 minute, you will have the first XPS spectrum. And our Enviro family is growing. So the latest addition to our portfolio is the Envirometros. So we launched it at AVS conference last November. And so it's again fully automated and is equipped with, let's say, classical surface analysis technique for UHV, but also it is possible to work in gases up to, let's say, 50 millibar. So I'm sure you are asking yourself, what is now the difference between EnviroSCA and Envirometros? So let's say the EnviroSCA is for analyzing everything, all dirty electrolytes, all dirty stuff. You can just put it inside and you can measure. The envirometers are more for UHV analysis and gaseous environments, no liquids. So everything, let's say, worked very nice for us, so that in the beginning of 2023, we have kind of 86 systems and analyzer installed all over the world, and about 23 systems in production currently. So I would say the application of the near ambient pressure XPS are practically limitless. So you can measure everything which doesn't require UHV, which means practically everything, from catalysis to biological materials to liquids to polymers and plastic to gases and liquid environments, and so on and so on. Even astrochemistry and astrobiology. So I mean, the atmosphere on Mars is 5 millibars, so practically you can simulate what is happening on Mars. And I will try to give you some examples of applications. For example, operando studies of catalytical process. So these are a bit older measurements, but I find it very nicely performed in Sweden. So the CO oxidation reaction on platinum-111, and we could see here very nicely when you increase the temperature in the presence of oxygen and CO, we can see that the CO2 peak is appearing. So you can monitor operando a catalytical process. Of course, it's good to have an ambient pressure XPS spectrum, but it's also very interesting to see the surface while you are measuring the ambient pressure XPS spectra. And for example, it's very nice to have a scanning probe microscope. The working principle is similar to the in situ cell. You have here the kind of small reactor where you can put gases inside and you can measure IFM and STM under gases while the analysis chamber still is in vacuum. And for example, just to give you an example, so these are measurements performed in the group of Dario Stacchiola. They just took pictures for CO oxidation reaction on copper 111, and also very nice experiments in the group of Itsui in China. So they observed, so they performed combined SPM and XPS measurements, and they took images of graphene on iridium and XPS spectra during oxygen in oxygen atmosphere. So they investigated oxygen intercalation in, let's say, real time. So, okay, what we can do? Operando studies of reactions at gas-solid interface. So this is an older example that I really like to show it. So we see the dissociation of C2H2 on nickel silicon dioxide on silicon sample, and these measurements are snapshot measurements. So the integration time is just 1 second. So in between two measurements is, okay, 2.4 seconds. So you can see live how your carbon peak is increasing on the surface. Another example, so all the measurements that I'm showing you, so our own measurements were performed at Specs Laboratory with our demo system, with our demo EnviroSK. For example, we measured vanadium oxide, single crystal, and when we heat it up, we saw the apparition from vanadium 5 plus to vanadium 4 plus, and when we added oxygen, we saw again the oxidation back to vanadium 5 plus. What else? We can analyze liquids. So this is also with EnviroSK measure. This is our sample. This is what I mentioned. You just open the door, put the whatever recipient you have inside, full of whatever you want, and you can measure. So this is our sample, and this is actually a movie. You see the nozzle of the analyzer. This is the water surface, and you see some impurities here flowing around. This is a movie, and you can distinguish very nicely between the oxygen in the gas phase and the oxygen in the liquid. We measure all kinds of liquid solutions, for example, sodium chloride or nanosilver, different pressures from few millibar up to 20 millibar. And for example, in the EnviroSCA, it's very easy to analyze liquids. Open the sliding door, put the sample inside, closing, measuring. But when you have an open system, you have to use some tricks to be able to form liquids on the sample. And for example, in the case of, so this is the system that we have installed at the Soleil synchrotron, the tempo beam line. So what we are doing, we use a Peltier cooling. So you put inside vapors which are condensing on the sample, and you form water droplets on the sample surface. And this is how you can measure, you can investigate liquids. Okay, what can you do? What else? Analysis of liquid-solid interface. And when you say analysis of liquid-solid interface, the first thing that you think of is operando study of electrolyte interfaces, electrochemical cells. Why? We also heard today in the nice talk about water electrolysis. So, of course, I think, it's a worldwide problem to how to produce green energy, energy storage. And for example, here is a cell for water electrolysis, and the research, the ongoing research is actually improving and searching for the right catalyst to maximize and improve the oxygen evolution reaction or hydrogen evolution reaction. And I would like to show you, let's say, the pioneering experiments which were performed at ALS synchrotron and with the so-called dip and pull method. And what does it mean? So you have the working electrode, so you dip it into electrolyte, you pull it out, and when you pull it out, you form here a thin film of liquid, so which is thin enough so that you, with your X-ray sources, you can see through the liquid film and analyze the liquid solid interface. And I always like to show this picture because you see here, this is the fully corroded nozzle of our analyzer. It's looking really bad, but it's working very nice. So meanwhile, the electrochemical cells, so the field of electrochemistry near ambient pressure is increasing very rapidly. So there are many research groups which are building their own electrochemical cell. And in this paper of Juan Velasco Velez, it's a very nice overview of the existent electrochemical cells currently available. So we also developed our own electrochemical cell. So it's a kind of similar with a dip and pull. So what you have here is a 3-electrode cell. The working electrode is mounted here. The cell is filled with electrolyte. And when you turn the manipulator, you will have something like half of the working electrode immersed into the electrolyte, half of the electrode outside. And in between, you will have an area where the liquid film is so thin that you can really see it through. And this is also the cell that we developed for the EnviroSCA. You see it here, the same working principle. You have a tilted, let's say, working electrode in this case, where you can have it half immersed, half outside, and we can measure a very nice electrochemical process. And these are the measurements that we performed at SPECS. And first of all, we measured, let's say, the normal electrochemical cell in a beaker with 3 electrodes, and with our 3-electrode cell, and we see that cyclic voltammograms are really nice. And practically what we can see here is that at positive voltages, we see the platinum oxidation, and this is what we measure. This is how it looks like. We have cameras, so the nozzle of the analyzer inside the EnviroSCA, and when we approach it in the measurement position, measured at 20 millibar, and we could measure the platinum signal at different voltages. So we started from minus 600 millivolt, minus 255, and when we go to plus voltage, we see the apparition of platinum oxide, and we could even quantify how much platinum oxide was formed on the electrode during the cyclic voltammogram. Okay, what else we did? Operando study of lithium-ion batteries. Again, a very, how to say, modern subject, very is important for energy storage. And what we did actually, so this is the experiment, it's a kind of quick and dirty experiment. So we use lithium phosphohexafluoride in ECDMC battery grade solvent, and we just measure the spectrum, and then we took a vanadium oxide, piece of vanadium oxide, we just put it into the solvent. So please keep in mind there is no voltage, there is nothing applied, just quick and dirty experiment. And then when we measure this, of course, we see the vanadium signal. And after that, to our surprise, so we took out the vanadium oxide, we rinse it and dry it, and we put it inside the machine. And to our surprise, we saw lithium on vanadium oxide, which means that lithium ions transport was already taking place from the electrolyte to vanadium oxide. And this, as I said, just quick and dirty, without any voltage, anything applied. Okay, we had fun. So we study, let's say, all kinds of different stuff, like, for example, corrosion, operando studies of corrosion. So what we did, excuse me, so we took just a normal paper clip and we put it inside vinegar, acetic acid for 12 hours, and we measure in UHV. So before corrosion, and we saw nickel peaks, and after corrosion, and we saw iron. So our paper clip actually is made of iron with a coating of nickel. And okay, we thought, let's see what if we see something when we measure this operando. And this is the nozzle of the EnviroESCA. You see here the paper clip in the vinegar, and this is in the measurement position. And what we see is that after 2 hours of corrosion at 9 millibar, the nickel peak is really decreasing. And after 3 hours, we have to decrease the pressure in order to be able to measure. And we see that the iron is appearing. So with near ambient pressure XPS, you can really follow operando live all these processes. And I think this is the strongest point for the ambient pressure XPS method. And just at the end, for fun, food. So you can also use it as food analysis, food quality, and I told you we put everything in our EnviroESCA machine, not in the machines for customers, only in ours. We measured also Coca-Cola and Christmas candies and autumn leaves and everything. Italian cheese also. And here is, we put a tomato inside. So you see here, tomato inside the UHV machine. You see a bit is bubbling, is boiling a bit, because we measure at 10 millibar, but still we can investigate, and we can measure oxygen and nitrogen in different on different parts of the tomato. So, but also of course make the quantitative analysis. So yeah, I try to hurry up a bit to not to keep you longer before the poster session. So I hope I could give you a flavor of what is possible to do with the near ambient pressure XPS. I think it's an extremely powerful technique, and practically, yeah, there is nothing you cannot do with it. So thank you very much for your attention, and open for questions.
Thank you very much. Questions? Please.
Yes. Pardon? So in principle, yes. So what we use here, we use potassium hydroxide, so copper electrodes, but as long as this is liquid, it can work. I mean, there is no material that is, of course, immune to or inert to any corrosion or any materials. And I think it's depending, you can do it, but it's depending if you work with this kind of nasty substances 24 hours a day, 7 days a week, or if you work once in a while. It's also depending on the concentration you have. I mean, everything gets corroded, but I would say it's working. Yes. Yeah, I mean, it's of course the membrane. So I think the electrochemical cells with graphene membrane, with holy membranes. I think they were used also at Bessie. I would say so. These were developed at Bessie. I do not know. Maybe you know better. So from the membrane is of course always. It's not so easy to do it because you have first let's say a mask with holes, and then you grow graphene of these holes, and then on the rear side of graphene you have to deposit your electrode, your working electrode, and it's very tricky to do it. Of course, when you use a closed cell, you do not have the danger that everything, the liquid goes into your device because it's closed, but it's very difficult to do it. We prefer to work with open. It's easier to work with, and it's easier also to prepare it. I mean, our analyzer in our EnviroSK, I mean, it was soaked. I do not even want to know what everything went on this analyzer. I see the colleagues that are doing measurement that sometimes they just, clean the nozzle, but it's working. So I think it's a matter of how we prefer to do it. So we prefer to do it in an open. So the pressure is, I mean, usually with this, so we can go up to, let's say, 50 millibar pressure inside the cell. So the idea is you have to, the intensity of your signal is decreasing exponentially with the pressure. So the idea is to find the minimum pressure with your, where your investigated process is taking place, and to find the minimum pressure that you have the maximum signal intensity. I would say in our case, it's always a, counterplay of course, we can make the entrance of the analyzer a smaller nozzle, so you can have larger pressure, but your signal intensity will decrease. So yes. So this is actually so all these in situ cells are inserted inside a vacuum chamber. So as I said, I would say also for laboratory system, you can go up to 50 millibar. For higher pressure, you can go from the cell and from the analyzer, but then you need a more intense X-ray source. And this you have at synchrotrons. So for laboratory, so with our laboratory, so for laboratory sources, 50 millibar, I think this is, so 20 millibar we can measure just daily. Excuse me, maybe just coming back to your, so in our cases, what we use an open cell, we have the analyzer vertical. So which means the cell can be open. But the cell used at synchrotrons, it's difficult to have the synchrotron vertical. So which means that your analyzer will be horizontal, and which means your cell has to be like this. So that's why it's, I would say for synchrotrons, it's, if you do not have dip and pull, then you have this kind of closed cells. Sorry, this was your question?
Okay, thank you. Let's thank our speaker.
Thank you.
And I will invite the last speakers, Ahmed Difawi from Geol, presenting the Geol NMR.
I'll try. Thank you for the introduction. Okay, of course, first let me say my many thanks to organizers for giving me this opportunity. Okay. Then I'll introduce myself. I'm a Difawi, and I'm a project officer in GOL, but to be honest, I was, because starting from this morning, I was appointed as the head of the group. So for sure, I will remember this trip, this very first trip to Romania. You can guess why. Anyway, so this is quite dense presentation, so I will try to make it light. And I'm very happy to share with you our latest development for NMR in GOL. So I will not make the complete timeline of NMR inside GOL, but what I want to highlight is that GOL is a Japan Electron-Optics Laboratory. It's a Japanese company, and we announced our first NMR since 1956. So we have a very long expertise with NMR. However, since several years, NMR was dedicated to the domestic market. It means Japan and Asia. And since August 2014, we announced this plan of expansion in Europe and in US. And since August 2014, actually we succeed to install almost 200 magnets in Europe. This very first NMR actually was capable of reaching up to 32 megahertz, which was at that time a very high field. And if we compare the spectra obtained on that time with the current spectra of ethanol, we can very easily discover that even at that time, it was a very robust and very good instrumentation. And of course, I want again to highlight that we have a very long expertise on this field. So I'm part of GEL Europe SAS, managing 22 countries from Paris. And what I want to highlight actually is that we have more than 1,000 instruments running, installing and running, involving mass spec, NMR, ESR, and of course microscopes. This gives you a solid and strong idea on the quality of our after-sales service. So also we set up a European demonstration center in Wilwing Garden City in UK. We have 400 megahertz system installed and 600 megahertz installed. So if you have any NMR project, you will be more than welcome to test your own samples in our devices before setting up officially your projects. So let me summarize what is NMR. Even I guess several persons know already about NMR, but okay, NMR is nuclear magnetic resonance, and I need to highlight 4 different points, or 4 main points. First is that it's a not separative technique, unlike chromatography. It's a non-destructive technique, unlike mass spec. Still very sensitive technique, like LC, and of course, we can make quantitative NMR. So thanks to these 4 main points, we can say that NMR is a very powerful analytical tool for structural analysis, but also for dynamic, for nice dynamic information. From instrumentation point of view, what is NMR? NMR is a superconducting magnet. So we place the sample inside the superconducting magnet. We send a radio frequency signal through this probe, you see in the bottom. And of course, we measure back the signal obtained after creating this spin population imbalance. We enhance the signal using a preamp. And of course, everything is controlled under the console. This is from instrumentation point of view. Now from the technique point of view, we need to apply a very short radio frequency and to collect what we call the FID, the free indication decay. And using mathematics, we can go from time scale to chemical shift scale using Fourier transform. So we obtain NMR spectra. From the NMR spectrum, we can catch actually four main information. The first one is the position of the signal in the scale, what we call the chemical shift actually. And then we can understand the environment surrounding the nuclei we are observing or we are irradiating. The second information is what we call the G coupling. So the number of signals, it can be singlet, it can be doublet, it can be triplet, it can be multiplet. So the number of the signal can be a very good indication to understand the interaction through the chemical bonds, of course, between the nuclei we are observing and the environment of the nuclei. Third information is the line width. Actually, this is a very good indication for the dynamics, of course, but also for the good magnetic homogeneity of magnetic field. Very last one is the integration, but this is only possible with proton spectra. We can, of course, understand the number of proton bounded on the nuclei we are observing. So we use NMR in a very wide range of application. It can be fine chemistry, like pharmacy or cosmetics, but it can also be used in heavy application like physics, like geology, like petrochemicals. So the idea is to say that this is a very powerful tool and can federate different disciplines. It can be for chemists, for physics, for geology, for biology, and so on. Yeah, I will go through this example of application to talk directly about this new generation we very recently announced. This is the ECZ Luminous series. Actually, we have three different models of this series, the S model, the R model, and the G model. The S model is S like standard. Actually, this is for routine open access, typically for organic chemistry or analytical chemistry, for synthesis, characterization, and so on. So it's only available for 400 megahertz, and it can only perform solution NMR, liquid NMR. Then the second model is the ECZ-R, R like research. So then we can go up to 600 megahertz, and we can have these hybrid spectrometers. Actually, they can perform at the same time solution NMR, liquids NMR, and solid state NMR. The last one is the G, so GRAN. Then if you have a very sophisticated applications, actually, we can go up to 900 megahertz as a standard, but of course, we can develop on demand some solution to fulfill some applications, so we can go more than 900 megahertz. And of course, it's dedicated for hybrid use solution and the solid state NMR. And then we can, of course, integrate and add a second channel, third channel, and so on. So it gives really a good opportunity. What I want also to highlight is that you can start with one configuration and upgrade it in the future. This is completely possible. So in terms of communication, please know that inside the console there is a processor, there is another computer actually. So we have this double storage capability, and if you are using two different spectrometers from GOL, you can have access from one working station, and if you are using one spectrometer, you can also have several access. And please know that all our additional licenses are free of charge. So compared to other solutions in the market, every part of the electronic is managed with one board. With our solution, everything is managed with only one board. It means that we can speed up the diagnostic and we can repair very, very quickly. In the worst case, it will be one board to change. So as standard, we have 2 channels for emission and one for reception, one receiver. And please note that in every single channel for emission, we have 4 different sequencers. So it means a total of 8 frequencies that we can emit and detect them with one receiver. This allows us to have different possibility of combination of different nuclei and to cover a broadband use of nuclei. In terms of magnet, we announced this new series, but unfortunately today is available only for 400 megahertz system, what we call year hold. This is offer autonomy of helium of 1 year, 365 days autonomy of helium. As we already know, there is a big crisis for liquid helium availability, so it can be a very, very nice solution. For liquid nitrogen, autonomy is 15 days, 2 weeks. And very recently, actually 2 weeks ago, we announced this unique product on the market, what we call cryogen reclamation system. Actually, no need to refill periodically with liquid nitrogen and liquid helium. There are 2 different levels or floors in top of the magnet, and everything is really refined. So no need to refill anymore with liquid nitrogen and with liquid helium. Then, in terms of probes, please know that all our probes are auto-tuned, and we can offer, in terms of solution NMR, 3 millimeter probe, 5 millimeter probes, and 10 millimeter probes. Our standard probe, let's say it's a combination, it's 2 probes in one, because what you need to know is when the sample is when the closest coil to the sample is dedicated to proton, we call this probe inverse probe. When the farthest coil to the sample is dedicated to the proton, we call these probes inverse probe. So the Royal probe, it's 2 probes in one, because it can be considered as inverse probe, as we have the proton in the high frequency channel, but we also have the fluor in the high frequency channel, so we can also consider that it's an inverse probe. So instead of buying 2 different probes in the lab, you can buy 1 probe, much less lower price. Okay, then this is a request coming from Japan, actually from pharmaceutical world in Japan. They got a lot of impurities with fluor compound. So they add this peripheral coil, what we call the Idler coil, and this coil allows us to see the RLC circuit following AND or logic. If we see proton or fluorine, we are on single tube. And if we say proton and fluorine, we are on dual tube. And this allows us to perform triple resonance using only 2 channels. And this is with patent and a unique product in the market. Actually, with the competitor, if you need to perform triple resonance experiments, you need 3 channels. But with this nice solution, you can perform triple resonance probe using only 2 channels. 1 channel dedicated to proton fluor, and the other channel is dedicated to all heteronucleus of the periodic table between P31 and nitrogen 15. So this is some examples. If we observe, if we irradiate carbon 13 without decoupling, we cannot have any information from the spectrum. So if we, here we observe the carbon 30. We cannot have any information from the spectra actually. But if we observe the carbon 30 decoupling the proton, we start to have some information. If we observe carbon 13 decoupling fluor, we have some additional information. But if we decouple at the same time proton fluor while observing carbon 13, actually we can have all information that we need. And this is not only dedicated to carbon 13, it concerns all heteronucleus, as I said, of the periodic table between phosphorus 31 and nitrogen 50. And this is an example of P31. if we observe nothing, we decouple proton some information, we decouple fluor some other information, but if we decouple both at the same time, you see the triplet going to singulate. This is not only for 1D experiments, it's also for 2D experiments, and we see in HNQC experiments the two slots going in one slot. Here the same thing. So, if we want to increase the sensitivity, we need to cool electronics to actually have better signal on noise ratio, so we increase the sensitivity. We have two kind of cooled probe, cryo probes actually. We have nitrogen cooled probe and helium cooled probe. For the nitrogen cooled probe, it's 3 times better sensitivity than the room temperature probes. And for the helium cooled probe, it's more than 4 times better sensitivities than the room temperature. So for solid state, we cover also a very wide range, starting from 0.75 millimeter rotor up to 8 millimeter rotor. And also this is a competitive advantage against the competitor because our main competitor stops at 7 millimeter. So for the 0.75 millimeter and 1 millimeter, this is what we call fast NMR. Please know that we can speed up to 120 kilohertz. This is the highest value in the market. But you can also guess when we speed in such very high speed, we can damage the probe. So what we developed here is a bench spinner. This is a tester in the bench top actually. So before putting your sample inside the probe, you can just test it in the bench spinner, and if the bench spinner is damaged, it's just a matter of some repair and very, very quick repair. But if the probe is damaged, this can really be particularly problematic. So all NMR users for liquid state know that automation is working well with all brands. But what we developed in GOL is that now we can have this automation for solid state NMR. So here you have the autosampler, and please know that the same autosampler can be used for solution NMR and for solid state NMR. No need to change the autosampler if you go from one application to another. If you use solution NMR, you just insert a tube. If you are solid state user, you just insert the rotor inside the carrier and you put it on the autosampler, and everything is automated, auto-tune, auto-match, everything is controlled through the software. We have also some other nice product for solid state NMR. We have this low frequency box for what we call the low gamma. Low gamma are the nuclei with a very, very low frequency. And no need to have a dedicated probe to perform low gamma. Actually, with GOL, we just clips this low frequency unit to the existing probe, so no need to buy a new probe. We also have some cryogenic probes for solid state NMR. This VT extended probe, also unique product in the market because it covers a very wide temperature range, starting from -100 up to +200. And of course, for the semi-solid, we can also offer what we call field gradient magic angle spinning probes. So it's dedicated to polymerists actually to deal with gel, creams, rubber, and so on. So in terms of autosamplers, we have two different kinds of autosampler. So in top of the magnet, available on 24 position, and at main weight, available on 30, 64, and 100 position. Please know that for the 30 position one, it can be pre-cooled for some biological use, if you are dealing with biopsies, for example. And if you are polymerist, you need to have to keep the sample preheated. It can be also equipped with the preheat module, and you can perform your analysis at high temperature. So for the low temperature measurement, we can simply, as the competitor, offer some DWARs, 10 liter DWAR or 30 liter DWAR, but sometimes you have to perform long-term carbon-13 analysis, and sometimes it can take all the weekend. So nitrogen is no more a good solution. In that case, we offer this other solution called the air jet cooler. we can reach minus 40 degrees or minus 90 degrees. This last solution, what we call vortex, is just to have this 0 degree. Actually, it's not 0 degree, it's 25 degrees lower than the room temperature. So regarding the software, we have two different software. The first one is free of charge, open access software. But please know that all additional modules are included with the software, unlike the competitor. So you have the non-uniforming sampling capabilities, and also you can quantify the QNMR, quantitative NMR. And of course, it's, as I said, free of charge. Then we very recently announced one more software. This is to have some more capabilities, and you need to have to pay some license for this. This is just to have, for example, access to libraries or to predict with the predict NMR. Thank you for your attention, and I'm open for your questions.
It was 20 minutes. Yes, please.
Yes, please. Actually, it depends on what you want to look for, but I know that conventional field for this kind of application is 400 or 500 megahertz system, because when you go to 500 megahertz system, you can win resolution and sensitivity at the same time. But it will, of course, depend on the use. Both. It can be a hybrid solution, as I explained, 500 megahertz hybrid solution, liquid and solid. Same console can perform both applications. Of course, you need to change the probe to put solution probe when you are dealing with the solution NMR and solid probe when you are dealing with solid state. You're very welcome.
If not, Michaela give us some. Thanks to
Thank
the
you.
speaker again. So.
So I'm inviting you to the poster session, and then at 7 o'clock, the bus will wait for you to go to the restaurant. So please be there at 7 o'clock. The one that came with the bus, please go with the bus. Thank you. See you at the posters. And thank you to all the speakers for today.